Quantum Computation and Quantum Information by Michael A. Nielsen and Isaac L. Chuang. Part 1. Fundamental Concepts. Chapter 1. Introduction and Overview. Science offers the boldest metaphysics of the age. It is a thoroughly human construct, driven by faith that if we dream, press to discover, explain, and dream again, thereby plunging repeatedly into new terrain, the world will somehow come clearer, and we will grasp the true strangeness of the universe. And the strangeness will all prove to be connected and make sense. Edward O. Wilson. Information is physical. Rolf Landauer. What are the fundamental concepts of quantum computation and quantum information? How did these concepts develop? To what use may they be put? How will they be presented in this book? The purpose of this introductory chapter is to answer these questions by developing in broad brushstrokes a picture of the field of quantum computation and quantum information. The intent is to communicate a basic understanding of the central concepts of the field, perspective on how they have been developed, and to help you decide how to approach the rest of the book. Our story begins at section 1.1 with an account of the historical context in which quantum computation and quantum information has developed. Each remaining section in the chapter gives a brief introduction to one or more fundamental concepts from the field. Quantum bits, section 1.2, quantum computers, quantum gates, quantum circuits, and quantum gates and quantum circuits, section 1.3, quantum algorithms, section 1.4, experimental quantum information processing, section 1.5, and quantum information and communication, section 1.6. Along the way, illustrative and easily accessible developments such as quantum teleportation and some simple quantum algorithms are given, using the basic mathematics taught in this chapter. The presentation is self-contained and designed to be accessible even without a background in computer science or physics. As we move along, we give pointers to more in-depth discussions in later chapters, where references and suggestions for further reading may also be found. If, as you read, you're finding the going rough, skip on to a spot where you feel more comfortable. At points we haven't been able to avoid using a little technical lingo which won't be completely explained until later in the book. Simply accept it for now, and come back later when you understand all the terminology in more detail. The emphasis in this first chapter is on the big picture, and with the details to be filled in later. 1.1. Global Perspectives. Quantum computation and quantum information is the study of the information processing tasks that can be accomplished using quantum mechanical systems. Sounds pretty simple and obvious, doesn't it? Like many simple but profound ideas, it was a long time before anybody thought of doing information processing using quantum mechanical systems. To see why this is the case, we must go back in time and look in turn at each of the fields which have contributed fundamental ideas to quantum computation and quantum information: quantum mechanics, computer science, information theory, and cryptography. As we take our short historical tour of these fields, think of yourself first as a physicist, then a computer scientist, then as an information theorist, and finally as a cryptographer, in order to get some feel for the disparate perspectives which have come together in quantum computation and quantum information. 1.1.1 History of quantum computation and quantum information. Our story begins at the turn of the 20th century, when an unheralded revolution was underway in science. A series of crises had arisen in physics. The problem was that the theories of physics at the time, now dubbed classical physics, were predicting absurdities such as the existence of an ultraviolet catastrophe involving infinite energies or electrons spiraling inexorably into the atomic nucleus. At first, such problems were resolved with the addition of ad hoc hypotheses to classical physics. But as a better understanding of atoms and radiation was gained, these attempted explanations became more and more convoluted. The crisis came to a head in early 1920s after a quarter century of turmoil and, resulted in the creation of the modern theory of quantum mechanics. Quantum mechanics has been an indispensable part of science ever since and has been applied with enormous success to everything under and inside the Sun, including the structure of the atom, nuclear fission in stars, superconductors, and the structure of DNA, and the elementary particles of nature. What is quantum mechanics? Quantum mechanics is a mathematical framework or set of rules for the construction of physical theories. For example, there is a physical theory known as quantum electrodynamics, which describes with fantastic accuracy the interaction of atoms and light. Quantum electrodynamics is built up within the framework of quantum mechanics, but it contains specific rules not determined by quantum mechanics. The relationship of quantum mechanics to specific physical theories like quantum electrodynamics is rather like the relationship of a computer's operating system to specific application software. The operating system sets certain basic parameters and modes of operation, but leaves open how the specific tasks are accomplished by the applications. The rules of quantum mechanics are simple, but even experts find them counterintuitive, and the earliest antecedents of quantum computation and quantum information may be found in the long-standing desire of physicists to better understand quantum mechanics. The best-known critic of quantum mechanics, Albert Einstein, went to his grave unreconciled with the theory he helped invent. Generations of physicists since have wrestled with quantum mechanics in an effort to make its predictions more palatable. One of the goals of quantum computation and quantum information is to develop tools which sharpen our intuition about quantum mechanics and make its prediction more transparent to human minds. For example, in the early 1980s, interest arose in whether it might be possible to use quantum effects to signal faster than light, a big no-no according to Einstein's theory of relativity. The resolution of this problem turns out to hinge on whether it's possible to clone an unknown quantum state, that is, construct a copy of a quantum state. If cloning were possible, then it would be possible to signal faster than light using quantum effects. However, cloning, so easy to accomplish with classical information, consider the words in front of you and where they came from, turns out not to be possible in general in quantum mechanics. This no-cloning theorem, discovered in the early 1980s, is one of the earliest results of quantum computation and quantum information. Many refinements of the no-cloning theorem have since been developed, and we now have computational tools which allow us to understand how well a necessarily imperfect quantum cloning device might work. These tools in turn have been applied to understand other aspects of quantum mechanics. A related historical strand contributing to the development of quantum computation and quantum information is the interest dating to the 1970s of obtaining complete control over single quantum systems. Applications of quantum mechanics prior to the 1970s typically involved a gross level of control over a bulk sample containing an enormous number of quantum mechanical systems, none of them directly accessible. For example, superconductivity has a superb quantum mechanical explanation. However, because a superconductor involves a huge, compared to the atomic scale, sample of conducting metal, we can only probe a few aspects of its quantum mechanical nature, with the individual quantum system constituting the superconductor remaining inaccessible. Systems such as particle accelerators do allow limited access to individual quantum systems, but again provide little control over the constituent systems. Since the 1970s, many techniques for controlling single quantum systems have been developed. For example, methods have been developed for trapping a single atom in an atom trap, isolating it from the rest of the world and allowing us to probe many different aspects of its behavior with incredible precision. The scanning tunneling microscope has been used to move single atoms around, creating designer arrays of atoms at will. Electronic devices whose operation involves the transfer of only single electrons have been demonstrated. Why all this effort to attain complete control over single quantum systems? Setting aside the many technological reasons and concentrating on pure science, the principal answer is that researchers have done this on a hunch. Often the most profound insights in science come when we develop a method for probing a new regime of nature. For example, the invention of radio astronomy in the 1930s and 1940s led to a spectacular sequence of discoveries, including the galactic core of the Milky Way galaxy, pulsars, and quasars. Low-temperature physics has achieved its amazing success by finding ways to lower the temperatures of different systems. In a similar way, by obtaining complete control over single quantum systems, we are exploring untouched regimes of nature in the hope of discovering new and unexpected phenomena. We are just now taking our first steps along these lines, and already a few interesting surprises have been discovered in this regime. What else shall we discover as we obtain more complete control over single quantum systems and extend it to more complete systems? Quantum computation and quantum information fit naturally into this program. They provide a useful series of challenges at varied levels of difficulty for people devising methods to better manipulate single quantum systems and stimulate the development of new experimental techniques and provide guidance as to the most interesting directions in which to take experiment. Conversely, the ability to control single quantum systems is essential if we are to harness the power of quantum mechanics for application to quantum computation and quantum information. Despite this intense interest, efforts to build quantum information processing systems have resulted in modest success to date. Small quantum computers capable of doing dozens of operations on few quantum bits, or qubits, represent the state of the art in quantum computation. Experimental prototypes for doing quantum cryptography, a way of communicating in secret across long distances, have been demonstrated and are even at the level where they may be useful for some real-world applications. However, it remains a great challenge to physicists and engineers of the future to develop techniques for making large-scale quantum information processing a reality. Let us turn our attention from quantum mechanics to another of the great intellectual triumphs of the 20th century, computer science. The origins of computer science are lost in the depths of history. For example, cuneiform tablets indicate that by the time the Hammurabi, circa 1750 BC, the Babylonians had developed some fairly sophisticated algorithmic ideas, and it is likely that many of those ideas date to even earlier times. The modern incarnation of computer science was announced by the great mathematician Alan Turing in a remarkable 1936 paper. Turing developed in detail an abstract notion of what we now call the programmable computer, a model for computation now known as the Turing machine in his honor. Turing showed that there is a universal Turing machine that can be used to simulate any other Turing machine. Furthermore, he claimed that the universal Turing machine completely captures what it means to perform a task by algorithmic means. That is, if an algorithm can be performed on any piece of hardware, say a modern personal computer, then there is an equivalent algorithm for a universal Turing machine which performs exactly the same task as the algorithm running on the personal computer. This assertion, known as the Church-Turing thesis, in honor of Turing and another pioneer of computer science, Alonzo Church, asserts the equivalence between the physical concept of what class of algorithms can be performed on some physical device with the rigorous mathematical concept of a universal Turing machine. The broad acceptance of this thesis laid in the foundation for the development of a rich theory of computer science. Not long after Turing's paper, the first computers constructed from electronic components were developed. John von Neumann developed a simple theoretical model for how to put together, in a practical fashion, all the components necessary for a computer to be fully as capable as a universal Turing machine. Hardware development truly took off in 1947 when John Bardeen, Walter Brattain, and Will Shockley developed the transistor. Computer hardware has grown in power at an amazing pace ever since, so much so that the growth was codified by Gordon Moore in 1965 in what has become to be known as Moore's Law, which states that computer power will double for a constant cost roughly once every 2 years. Amazingly enough, Moore's Law has approximately held true in all decades since the 1960s. Nevertheless, most observers expect that this dream run will end sometime during the first 2 decades of the 21st century. Conventional approaches to the fabrication of computer technology are beginning to run up against the fundamental difficulties of size. Quantum effects are beginning to interfere with the functioning of electronic devices as they are made smaller and smaller. One possible solution to the problem posed by the eventual failure of Moore's Law is to move to a different computing paradigm. One such paradigm is provided by the theory of quantum computation, which is based on the idea of using quantum mechanics to perform computations instead of classical physics. It turns out that while an ordinary computer can be used to simulate a quantum computer, it appears to be impossible to perform the simulation in an efficient fashion. Thus, quantum computers offer an essential speed advantage over classical computers. This speed advantage is so significant that um, many researchers believe that no conceivable amount of progress in classical computation would be able to overcome the gap between the power of a classical computer and the power of a quantum computer. What do we mean by efficient versus inefficient simulation of a quantum computer? Many of the key notions needed to answer this question were actually invented before the notion of a quantum computer had even arisen. In particular, the idea of efficient and inefficient algorithms was made mathematically precise by the field of computational complexity. Roughly speaking, an efficient algorithm is one which runs in polynomial in complexity. Roughly speaking, an efficient algorithm is one which runs in time polynomial in the size of the problem solved. In contrast, an inefficient algorithm requires superpolynomial, typically exponential, time. What was noticed in the late 1960s and early 1970s was that it seemed as though the Turing machine model of computation was at least as powerful as any other model of computation, in the sense that a problem which could be solved efficiently in some model of computation could also be solved efficiently in the Turing machine model. By using the Turing machine to simulate the other model of computation, this observation was codified into a strengthened version of the Church-Turing thesis. Any algorithmic process can be simulated efficiently using a Turing machine. The key strengthening in the strong Church-Turing thesis is the word efficiently. If the Church-Turing thesis is correct, then it implies that no matter what type of machine we use to perform our algorithms, that machine can be simulated efficiently using a standard Turing machine. This is an important strengthening as it implies that for the purposes of analyzing whether a given computational task can be accomplished efficiently, we may restrict ourselves to the analysis of the Turing machine model of computation. One class of challenges to the strong Church-Turing thesis comes from the field of analog computation. In the years since Turing, many different teams of researchers have noticed that certain types of analog computers can efficiently solve problems believed to have no efficient solution on a Turing machine. At first glance, these analog computers appear to violate the strong form of the Church-Turing thesis. Unfortunately for analog computation, it turns out that when realistic assumptions about the presence of noise in analog computers are made, their power disappears in all known instances. They cannot efficiently solve problems which are not efficiently solvable on a Turing machine. This lesson, that the effects of realistic noise must be taken into account in evaluating the efficiency of in a computational model was one of the great early challenges of quantum computation and quantum information, a challenge successfully met by the development of a theory of quantum error correcting codes and fault-tolerant quantum computation. Thus, unlike analog computation, quantum computation can in principle tolerate a finite amount of noise and still retain its computational advantages. The first major challenge to the strong Church-Turing thesis arose in the mid-1970s, when Robert Solovay and Volker Strassen showed that it is possible to test whether an integer is prime or composite using a randomized algorithm. That is, the Solovay-Strassen test for primality used randomness as an essential part of the algorithm. The algorithm did not determine whether a given integer was prime or composite with certainty. Instead, the algorithm could determine that a number was probably prime or else composite with certainty. By repeating the Solovay-Strassen test a few times, it's possible to determine with near certainty whether a number is prime or composite. The Solovay-Strassen test was of special significance at the time it was proposed, as no deterministic test for primality was then known, nor is one known at the time of this writing. Thus, it seemed as though computers with access to a random number generator would be able to efficiently perform computational tasks with no efficient solution on a conventional deterministic Turing machine. This discovery inspired a search for other randomized algorithms, which has paid off handsomely, with the field of blossoming into a thriving area of research. Randomized algorithms pose a challenge to the strong Church-Turing thesis, suggesting that there are efficiently solvable problems which nevertheless cannot be efficiently solved on a deterministic Turing machine. This challenge appears to be easily resolved by a simple modification of the strong Church-Turing thesis. Any algorithmic process can be simulated efficiently using a probabilistic Turing machine. This ad hoc modification of the strong Church-Turing thesis should leave you feeling rather queasy. Might it not turn out at some later date that yet another model of computation allows one to efficiently solve problems that are not soluble within Turing's model of computation? Is there any way that we can find a single model of computation in which is guaranteed to be able to efficiently simulate any other model of computation? Motivated by this question, in 1985, David Deutsch asked whether the laws of physics could be used to derive an even stronger version of the Church-Turing thesis, instead of adopting ad hoc hypotheses. Deutsch looked to physical theory to provide a foundation for the Church-Turing thesis that would be as secure as the status of that physical theory. In particular, Deutsch attempted to define a computational device that would be capable of efficiently simulating an arbitrary physical system. Because the laws of physics are ultimately quantum mechanical, Deutsch was naturally led to consider computing devices based upon the principles of quantum mechanics. These devices, quantum analogues of the machines defined 49 years earlier by Turing, led ultimately to the modern conception of a quantum computer used in this book. At the time of writing, it is not clear whether Deutsch's notion of a universal quantum computer is sufficient to efficiently simulate an arbitrary physical system. Proving or refuting this conjecture is one of the great open problems of the field of quantum computation and quantum information. It is possible, for example, that some effects of quantum field theory, or even more esoteric effect based in string theory, quantum gravity, or some other physical theory may take us beyond Deutsch's universal quantum computer, giving us a still more powerful model for computation. At this stage, we simply don't know. What Deutsch's model for a quantum computer did enable was a challenge to the strong form of the Church-Turing thesis. Deutsch asked whether it's possible for a quantum computer to efficiently solve computational problems which have no efficient solution on a classical computer, even a probabilistic Turing machine. then constructed a simple example suggesting that indeed quantum computers might have computational powers exceeding those of classical computers. This remarkable first step taken by Deutsch was improved in the subsequent decade by many people, culminating in Peter Shor's 1994 demonstration that two enormously important problems, the problem of finding the prime factor of an integer and the so-called discrete logarithm problem, could be solved efficiently on a quantum computer. This attracted widespread interest because these two problems were and still are widely believed to have no efficient solution on a classical computer. Shor's results are a powerful indication that quantum computers are more powerful than Turing machines, even probabilistic Turing machines. Further evidence for the power of quantum computers came in 1995 when Love Grover showed another important problem, the problem of conducting a search through some unstructured search space could also be sped up on a quantum computer. While Grover's algorithm did not provide as spectacular a speedup as Shor's algorithms, the widespread applicability of search-based methodologies has excited considerable interest in Grover's algorithm. At about the same time as Shor's and Grover's algorithms were discovered, many people were developing an idea Richard Feynman had suggested in 1982. Feynman had pointed out that there seemed to be essential difficulties in simulating quantum mechanical systems on classical computers, and suggested that building computers based on the principles of quantum mechanics would allow us to avoid those difficulties. In the 90s, several teams of researchers began fleshing this idea out, showing that it is indeed possible to use quantum computers to efficiently simulate systems that have no known efficient simulation on a classical computer. It is likely that one of the major applications of quantum computers in the future will be performing simulations of quantum mechanical systems too difficult to simulate on a classical computer, a problem with profound scientific and technological implications. What other problems can quantum computers solve more quickly than classical computers? The short answer is that we don't know. Coming up with a good quantum algorithm seems to be hard. A pessimist might think that that's because there's nothing quantum computers are good for other than the applications already discovered. We take a different view. Algorithms designed for quantum computers is hard because designers face two difficult problems not faced in the construction of algorithms for classical computers. First, our human intuition is rooted in the classical world. If we use that intuition as an aid to the construction of algorithms, then the algorithmic ideas we come up with will be classical ideas. To design good quantum algorithms, one must turn off one's classical intuition for at least part of the design process, using truly quantum effects to achieve the desired algorithmic end. Second, to be truly interested, it is not enough to design an algorithm that is merely quantum mechanical. The algorithm must be better than any existing classical algorithm. Thus, it is possible that one may find an algorithm which makes use of truly quantum aspects of quantum mechanics. That is nevertheless not of widespread interest because classical algorithms with comparable performance characteristics exist. The combination of these two problems makes the construction of new quantum algorithms a challenging problem for the future. Even more broadly, we can ask if there are any generalizations we can make about the power of quantum computers versus classical computers. What is it that makes quantum computers more powerful than classical computers? Assuming that this is indeed the case, what class of problems can be solved efficiently on a quantum computer, and how does that class compare to the class of problems that can be solved efficiently on a classical computer? One of the most exciting things about quantum computation and quantum information is how little is known about the answers to these questions. It is a great challenge for the future to understand these questions better. Having come up to the frontier of quantum computation, let's switch to the history of another strand of thought contributing to the quantum computation and quantum information theory. At the same time computer science was exploding in the 1940s, another revolution was taking place in our understanding of communication. In 1948, Claude Shannon published a remarkable pair of papers laying the foundation for the modern theory of information and communication. Perhaps the key step taken by Shannon was to mathematically define the concept of information. In many mathematical sciences, there is considerable flexibility in the choice of fundamental definitions. Try thinking naively for a few minutes about the following question: how would you go about mathematically defining the notion of an information source? Several different answers to this problem have found widespread use. However, the definition Shannon came up with seems to be far and away the most fruitful in terms of increased understanding, leading to a plethora of deep results and a theory with a rich structure which seems to accurately reflect many, though not all, real-world communication problems. Shannon was interested in two key questions related to communication of information over a communications channel. First, what resources are required to send information over a communications channel? For example, telephone companies need to know how much information they can reliably transmit over a given telephone cable. Second, can information be transmitted? Uh, can information be transmitted in such a way that is protected against noise in the communications channel? Shannon answered these two questions by providing the two fundamental theorems of information theory. The first, Shannon's noiseless channel coding theorem, quantifies the physical resources required to store the output from an information source. Shannon's second fundamental theorem, the noisy channel coding theorem, quantifies how much information it is possible to reliably transmit through a noisy communications channel. To achieve reliable transmission in the presence of noise, Shannon showed that error-correcting codes could be used to protect the information being sent. Shannon's noisy channel coding theorem gives an upper limit on the protection afforded by error-correcting codes. Unfortunately, Shannon's theorem does not explicitly give a practically useful set of error-correcting codes to achieve that limit. From the time of Shannon's papers until today, researchers have constructed more and better classes of error-correcting codes in their attempts to come closer to the limit set by Shannon's theorem. A sophisticated theory of error-correcting codes now exists, offering the user a plethora of choices in their quest to design a good error-correcting code. Such codes are used in a multitude of places, including, for example, compact displays, computer modems, and satellite communication systems. Quantum information theory has followed in similar developments. In 1995, Ben Schumacher provided an analog to Shannon's noiseless coding theorem, and in the process defined the quantum bit or qubit as the tangible physical resource. However, no analog to Shannon's noisy channel coding theorem is yet known for quantum information. Nevertheless, in analogy to their classical counterparts, a theory of quantum error correction has been developed, which, as already mentioned, allows quantum computers to compute efficiently in the presence of noise, and also allows communication over noisy quantum channels to take place reliably. Indeed, classical ideas of error correction have proved to be enormously important in developing and understanding quantum error correcting codes. In 1996, two groups working independently, Robert Calderbank and Peter Shor and Andrew Steen, discovered an important class of quantum codes known as the CSS codes after their initials. This work has since been subsumed by the stabilizer codes, independently discovered by Robert Calderbank, Eric Rains, Peter Shor, and Neil Sloan, and by Daniel Gottsman. By building upon the basic ideas of classical linear coding theory, these discoveries greatly facilitated a rapid understanding of quantum error-correcting codes and their application to quantum computation and quantum information. The theory of quantum error-correcting codes was developed to protect quantum states against noise. What about transmitting ordinary classical information using a quantum channel? How efficiently can this be done? A few surprises have been discovered in this arena. In 1992, Charles Bennett and Stephen Weisner explained how to transmit two classical bits of information, while only transmitting one quantum bit from sender to receiver, or is a result dubbed superdense coding. Even more interesting are the results in distributed quantum computation. Imagine you have two computers networked trying to solve a particular problem. How much computation is required to solve the problem? Recently, it has been shown that quantum computers can require exponentially less communication to solve certain problems than would be required if the networked computers were classical. Unfortunately, as yet these problems are not especially important in a practical setting and suffer some desirable technical restrictions. A major challenge for the future of quantum computation and quantum information is to find problems of real-world importance for which distributed quantum computation offers a substantial advantage over distributed classical computation. Let's return to information theory proper. The study of information theory begins with the properties of a single communications channel. In applications, we often do not deal with a single communication channel, but rather with networks of many channels. The subject of networked information theory deals with the information carrying properties of such networks of communication channels, and has been developed into a rich and intricate subject. By contrast, the study of networked quantum information theory is very much in its infancy. Even for very basic questions, we know little about the information carrying abilities of networks of quantum channels. Several rather striking preliminary results have been found in the past few years. However, no unifying theory of networked information theory exists for quantum channels. One example of networked quantum information theory should suffice to convince you of the value of such a general theory would have. Imagine that we are attempting to send quantum information from Alice to Bob through a noisy quantum channel. If that channel has zero capacity for quantum information, then it is impossible to reliably send any information from Alice to Bob. Imagine instead that we consider two copies of the channel operating in synchrony. Intuitively, it is clear and can be rigorously justified that such a channel also has zero capacity to send quantum information. However, if we instead reverse the direction of one of the channels, as illustrated in Figure 1.1, it turns out that sometimes we can obtain a non-zero capacity for the transmission of information from Alice to Bob. Counterintuitive properties like this illustrate the strange nature of quantum information. Better understanding the information-carrying properties of networks of quantum channels is a major open problem of quantum computation and quantum information. Let's switch fields one last time, moving to the venerable old art and science of cryptography. Broadly speaking, cryptography is the modern problem of doing communication or computation involving two or more parties who may not trust one another. The best known cryptographic problem is the transmission of secret messages. Suppose two parties wish to communicate in secret. For example, you may wish to give your credit card number to a merchant in exchange for goods, hopefully without any malevolent third party intercepting your credit card number. The way this is done is to use a cryptographic protocol. We'll describe in detail how cryptographic protocols work later in the book, but for now it will suffice to make a few simple distinctions. The most important distinction is between private key crypto systems and public key crypto systems. The way a private key crypto system works is that two parties, Alice and Bob, wish to communicate by sharing a private key, which only they know. The exact form of the key doesn't matter at this point. Think of a string of zeros and ones. The point is that this key is used by Alice to encrypt the information she wishes to send to Bob. After Alice encrypts, she sends the encrypted information to Bob, who must now recover the original information. Exactly how Alice encrypts the message depends upon the private key, so that to recover the original message, Bob needs to know the private key. in order to undo the transformation Alice applied. Unfortunately, the private key crypto systems have some severe problems in many contexts. The most basic problem is how to distribute the keys. In many ways, the key distribution problem is just as difficult as the original problem of communicating in private. A malevolent third party may be eavesdropping on the key distribution, and then use the intercepted key to decrypt some of the message transmission. One of the earliest discoveries in quantum computation and quantum information was that quantum mechanics can be used to do key distribution in such a way that Alice and Bob's security cannot be compromised. This procedure is known as quantum cryptography or quantum key distribution. This basic idea is to exploit the quantum mechanical principle that observation in general disturbs the system being observed. Thus, if there is an eavesdropper listening in, as Alice and Bob attempt to transmit their key, the presence of the eavesdropper will be visible as a disturbance of the communications channel Alice and Bob are using to establish the key. Alice and Bob can then throw out the key bits, and Alice and Bob oh, Al- Alice and Alice and Bob can then throw out the key bits established while the eavesdropper was listening in and start over. The first quantum cryptographic ideas were proposed by Stephen Weisner in the late 1960s, but unfortunately were not accepted for publication. In 1984, Charles Bennett and Gilles Brassard, building on Weisner's earlier work, proposed a protocol using quantum mechanics to distribute keys between Alice and Bob without any possibility of a compromise. Since then, numerous quantum cryptographic protocols have been proposed and experimental prototypes developed. At the time of this writing, the experimental prototypes are nearing the stage where they may be useful in limited-scale real-world applications. The second major type of cryptosystem is the public key cryptosystem. Public key cryptosystems don't rely on Alice and Bob sharing a secret key in advance. Instead, Bob simply publishes a public key, which is made available to the general public. Alice can make use of this public key to encrypt a message which she sends to Bob. What is interesting is that a third party cannot use Bob's public key to decrypt the message. Strictly speaking, we shouldn't say cannot. Rather, the encryption transformation is chosen in a very clever and non-trivial way so that it is extremely difficult, though not impossible, to invert, giving only knowledge of the public key. To make inversion easy, Bob has a secret key matched to his public key, which together enable him to easily perform the decryption. The secret key is not known to anybody other than Bob, who can therefore be confident that only he can read the contents of Alice's transmission, to the extent that it is unlikely that anybody else has the computational power to invert the encryption, given only the public key. Public key cryptosystems solve the key distribution problem by making it unnecessary for Alice and Bob to share a private key before communicating. Rather remarkably, public key cryptography did not achieve widespread use until the mid-1970s, when it was proposed independently by Whitfield Diffie and Martin Hellman, and by Ralph Merkle, revolutionizing the field of cryptography. A little later, Ronald Rivett and Adi Shamir and Leonard Adleman developed the RSA cryptosystem, which at the time of writing is the most widely developed public key cryptosystem, believed to offer a fine balance of security and practical usability. In 1997, it was disclosed that these ideas, public key cryptography, the Diffie-Hellman and RSA cryptosystems, were actually invented in the late 1960s and early 1970s by researchers working at the British intelligence agency GCHQ. The key to the security of public key cryptosystems is that it should be difficult to invert the encryption stage if only the public key is available. For example, it turns out that inverting the encryption stage of RSA is a problem closely related to factorizing. Much of the presumed security of RSA comes from the belief that factorizing is a problem hard to solve on a classical computer. However, Shor's fast algorithm for factoring on a quantum computer could be used to break RSA. Similarly, there are other public key cryptosystems which can be broken in a fast algorithm for solving a discrete logarithm problem, like Shor's quantum algorithm for discrete logarithm were. This practical application of quantum computers to the breaking of cryptographic codes has excited much of the interest in quantum computation and quantum information. We have been looking at the historical antecedents of quantum computation and quantum information. Of course, as the field has grown and matured, it has sprouted its own subfield of research. Those antecedents lie mainly within quantum computation and quantum information. Perhaps the most striking of these is the study of quantum entanglement. Entanglement is a uniquely quantum mechanical resource that plays a key role in many of the most interesting applications of quantum computation and quantum information. Entanglement is iron to the classical world's Bronze Age. In recent years, there has been a tremendous effort trying to better understand the properties of entanglement, considered as a fundamental resource of nature of comparable importance to energy, information, entropy, or any other fundamental resource, although there is as yet no complete theory of entanglement. Some progress has been made in understanding the strange property of quantum mechanics. It is hoped by many researchers that further study the properties of entanglement will yield insights that facilitate the development of new applications in quantum computation and quantum information. 1.1.2 Future Directions. We've looked at some of the history and present status of quantum computation and quantum information. What of the future? What can quantum computation and quantum information offer to science, to technology, and to humanity? What benefit does science, information theory, or what are the key open problems of quantum computation and quantum information? We will make a few very brief remarks about these overarching questions before moving on to more detailed investigations. Quantum computation and quantum information has taught us to think physically about computation, and we have discovered that this approach yields many new and exciting capabilities for information processing and communication. Computer scientists and information theorists have been gifted with a new and rich paradigm for exploration. Indeed, in the broadest terms, we have learned that any physical theory, not just quantum mechanics, may be used as the basis for a theory of information processing and communication. The fruits of these explorations may one day result in information processing devices with capabilities far beyond today's computing and communication systems, which with concomitant benefits and drawbacks for society as a whole. Quantum computation and quantum information certainly offer challenges aplenty to physicists, but it is perhaps a little subtle what quantum computation and quantum information offers to physics in the long term. We believe that just as we have learned to think physically about computation, we can also learn to think computationally about physics. Whereas physics has traditionally been a discipline focused on understanding elementary objects and simple systems, many interesting aspects of nature arise only when things become larger and more complicated. Chemistry and engineering deal with such complexity to some extent, but, are, but, most, offer, but most often in a rather ad hoc fashion. One of the messages of quantum computation and information is that new tools are available for traversing the gulf between the small and relatively complex. Computation and algorithms provide systematic means for constructing and understanding such systems. Applying ideas from these fields is already beginning to yield new insights into physics. It is our hope that this perspective will blossom in years to come into a fruitful way of understanding all aspects of physics. We've briefly examined some of the key motivations and ideas underlying quantum computation and quantum information. Over the remaining sections of this chapter, we give a more technical but still accessible introduction to these motivations and ideas, with the hope of giving you a bird's eye view of the field as it is presently poised. Chapter 1.2 Quantum Bits. The bit is the fundamental concept of classical quantum computation and classical information. Quantum computation and quantum information are built upon an analogous concept, the quantum bit, or qubit for short. In this section, we introduce the properties of single and multiple qubits, comparing and contrasting their properties to those of classical bits. What is a qubit? We're going to describe qubits as mathematical objects with certain specific properties. But hang on, you say. I thought qubits were physical objects. It is true that qubits, like bits, are realized as an actual physical system, but in section 1.5 and chapter 7, we describe in detail how this connection between the abstract mathematical point of view and real systems is made. However, for the most part, we treat qubits as abstract mathematical objects. The beauty of treating qubits as abstract entities is that it gives us the freedom to construct a general theory of quantum computation and quantum information which does not depend upon a specific system for its realization. What then is a qubit? Just as a classical bit has a state either 0 or 1, a qubit also has a state. The two possible states for a qubit are the states ket 0 and ket 1, which, as you might guess, correspond to the states 0 and 1 for a classical bit. Notation like ket is called the Dirac notation, and we'll be seeing it often, as is the standard notation for states in quantum mechanics. The difference between bits and qubits is that a qubit can be in a state other than 0 or 1. It is also possible to form linear combinations of states, often called superpositions, as shown in equation 1.1. The numbers alpha and beta are complex numbers, although for many purposes not much is lost by thinking of them as real numbers. Put another way, the state of a qubit is a vector in a two-dimensional complex vector space. The special states ket 0 and ket 1 are known as computational basis states, and form an orthonormal basis for this vector space. We can examine a bit to determine whether it is in the state 0 or 1. For example, computers do this all the time when they retrieve the contents of their memory. Rather remarkably, we cannot examine a qubit to determine its quantum state, that is, the values of alpha and beta. Instead, quantum mechanics tells us that we can only acquire much more restricted information about the quantum state. When we measure a qubit, we get either the result 0 with probability of the absolute value of alpha squared, or the result 1 with the probability of the absolute value of beta squared. Naturally, these two probabilities should sum to 1, since the probability. Geometrically, we can interpret this as the condition that the qubit's state must be normalized to length 1. Thus, in general, a qubit's state is a unit vector in a two-dimensional complex vector space. This dichotomy between the unobservable state of a qubit and the observations we can make lies at the heart of quantum computation and quantum information. In most of our abstract models of the world, there is a direct correspondence between elements of the abstraction and the real world. Just as an architect's plans for a building are in correspondence with the final building, The lack of this direct correspondence in quantum mechanics makes it difficult to intuit the behavior of quantum systems. However, there is an indirect correspondence for qubit states. Correspondence. For qubit states can be manipulated and transformed in ways which lead to measurement outcomes which depend indistinctly on the different properties of the state. Thus, these quantum states have real, experimentally verifiable consequences, which we shall see are essential to the power of quantum computation and quantum information. The ability of a qubit to be in a superposition state runs counter to our common sense understanding of the physical world around us. A classical bit is like a coin, either heads or tails up. For imperfect coins, there may be an intermediate state like having it balanced on an edge, but those can be disregarded in an ideal case. By contrast, a qubit can exist in a continuum of states between ket 0 and ket 1 until it is observed. Let us emphasize again that when a qubit is measured, it only ever gives 0 or 1 as the measurement result, probabilistically. For example, a qubit can be in the state shown in equation 1.2, which, when measured, gives the result 0 50% of the time, and the result 1 50% of the time. We will often return to this state, which is sometimes denoted ket plus. Despite the strangeness, qubits are decidedly real. Their existence and behavior, extensively validated by experiments discussed in section 1.5 and chapter 7, and many different physical systems can be used to realize qubits. To get a concrete feel for how a qubit can be realized, it may be helpful to list some of the ways this realization may occur, as the two different polarizations of a photon, as the alignment of nuclear spin and a uniform magnetic field, as the two states of an electron orbiting a singular atom, as shown in figure 1.2. In the atom model, the electron can exist in either the so-called ground or excited states, which we'll call ket 0 and ket 1 respectively. By shining light on the atom with appropriate energy, and for an appropriate length of time, it is possible to move the electron from the ket 0 state to the ket 1 state and vice versa. But more interestingly, by reducing the time we shine the light and the electron initially in the state ket 0 can be moved halfway between ket 0 and ket 1 into the ket plus state. Naturally, a great deal of attention has been given to the meaning or interpretation that might be attached to superposition states, and of the inherently probabilistic nature of observation on quantum systems. However, by and large, we shall not concern ourselves with such discussions in this book. Instead, our intent will be to develop mathematical and conceptual pictures which are predictive. One picture, useful in thinking about qubits, is the following geometric representation. Because the absolute value of alpha squared plus the absolute value of beta squared is equal to 1, we may rewrite equation 1.1 as equation 1.3, where theta, phi, and gamma are real numbers. In chapter 2, we will see that we can ignore the factor of e to the power of I times gamma out the front, because it has no observable effects, and for that reason, we can effectively write equation 1.4. The numbers theta and phi define a point on the unit three-dimensional sphere, as shown in figure 1.3. The sphere is often called the Bloch sphere. It provides a useful means of visualizing the state of a single qubit, and often serves as an excellent testbed for ideas about quantum computation and quantum information. Many of the operations on single qubits, which we describe later in this chapter, are neatly described within the Bloch sphere picture. However, it must be kept in mind that this intuition is limited because there is no simple generalization of the Bloch sphere known as multiple qubits. How much information is represented by a qubit? Paradoxically, there are an infinite number of points on the unit sphere, so that in principle one could store an entire text of Shakespeare within the infinite binary expansion of theta. However, this conclusion turns out to be misleading because of the behavior of the qubit when observed. Recall that measurement of a qubit will give only either 0 or 1. Furthermore, measurement changes the state of a qubit, collapsing it from its superposition of ket 0 and ket 1 to a specific state consistent with the measurement results. For example, if measurement of ket plus gives 0, then the post-measurement state of the qubit will be ket 0. Why does this type of collapse occur? Nobody knows. As discussed in Chapter 2, this behavior is simply one of the fundamental postulates of quantum mechanics. What is relevant for our purposes is that from a single measurement, one obtains only a single bit of information about the state of the qubit, thus resolving the apparent paradox. It turns out that only if the indefinitely many identically prepared qubits were measured would one be able to determine alpha and beta for a qubit in a state given in equation 1.1. Represented by a qubit if we... But even more interesting question to ask may be, how much information is represented by a qubit if we do not measure it? This is a trick question, because how can one quantify information if it cannot be measured? Nevertheless, there is something conceptually important here, because when nature evolves a closed system of the qubits, not performing any measurements, she apparently does keep track of all the continuous variables describing the state, like alpha and beta. In a sense, this is the state of a qubit. Nature conceals a great deal of hidden information. And even more interestingly, we will see shortly that the potential amount of this extra information grows exponentially with the number of qubits. Understanding this hidden quantum information is a question that we grapple for much of this book, and which lies at the heart that makes quantum mechanics a powerful tool for information processing. 1.1.2 Multiple qubits. Hilbert space is a big space. Carlton Caves. Suppose we have 2 qubits. If these were 2 classical bits, then we would have 4 possible states, 00, 01, 10, and 11. Correspondingly, a 2-qubit system has 4 computational basis states, denoted 00, 01, 10, 11, all in kets. A pair of qubits can also exist in superpositions of these 4 states, so the quantum state of 2 qubits involves associating a complex coefficient, sometimes called an amplitude, with each computational basis state, such that the state vector describing the 2 qubits is as shown in equation 1.5. Similar to the case for a single qubit, the measurement result x occurs with probability alpha x, absolute value of alpha x squared. With the state of the qubits of the measurement being ket x, the condition that probability sum to 1 is therefore expressed by the normalization condition that we sum alpha x magnitude of alpha x squared over x as a subset of 0, 1 squared. Is equal to 1, where the notation set 0, 1 squared means that the set of strings of length 2, with each letter being either 0 or 1. For a 2-qubit system, we could measure just a subset of the qubits, say the first qubit, and you can probably guess how this works, meaning the first qubit alone gives 0 with probability alpha 0, 0 squared plus alpha 0, 1 squared, magnitude alpha 0, 0 squared plus magnitude alpha 0, 1 squared, leaving the post-measurement state as shown in equation 1.6. Note how the post-measurement state is renormalized by the factor in the denominator so that it still satisfies the normalization condition, just as we expect for a legitimate quantum state. An important 2-qubit state is the Bell state, or EPR's pair, as shown in equation 1.7. This innocuous-looking state is responsible for many surprises in quantum computation and quantum information. It is the key ingredient in quantum teleportation and superdense coding, which we'll come to in section 1.3.7 and section 2.3 respectively, and the prototype for many other interesting quantum states. The Bell state has the property that upon measuring the first qubit, one obtains two possible results, 0 with the probability half, leaving the post-measurement state ket phi prime is equal to ket 00, and 1 with probability half, leaving ket phi prime is equal to ket 11 as a result. A measurement of the second qubit always gives the same result as the measurement of the first qubit. That is, the measurement outcomes are correlated. Indeed, it turns out that other types of measurement can be performed on the Bell state by first applying some operations to the first or second qubit, and that interesting correlations still exist between the result of a measurement of the first and second qubit. These correlations have been subject of intense interest ever since a famous paper by Einstein, Podolsky, and Rosen, in which they first pointed out the strange properties of states like the Bell state. EPR's insights were taken up and greatly improved by John Bell, who proved an amazing result. The measurement corrections in the Bell state are stronger than could ever exist between classical systems. These results, described in detail in section 2.6, were the first intimation that quantum mechanics allows information processing beyond what is possible in the classical world. More generally, we may consider a system of n qubits. The computational basis states for this system are of the form ket x1 to xn, and so a quantum state of such a system is specified by n squared amplitudes for n equals 500. This number is larger than the estimated number of atoms in the universe. Trying to store all these quantum numbers would not be possible on any conceivable classical computer. Hilbert space is indeed a big space. In principle, however, nature manipulates such enormous quantities of data, even for systems containing only a few hundred atoms. It is as if nature were keeping 2 to the power of 500 hidden pieces of scratch paper on the side, on which she performs her calculation as the system evolves. This enormous potential computational power is something we would very much like to take advantage of, but how can we think of quantum mechanics as computation? 1.3 Quantum computation. Changes occurring to a quantum state can be described using the language of quantum computation, analogous to the way a classical computer is built from an electrical circuit containing wires and logic gates. A quantum computer is built from a quantum circuit containing wires and elementary quantum gates to carry around and manipulate the quantum information. In this section, we describe some simple quantum gates and present several example circuits illustrating their applications, including a circuit which teleports qubits. 1.3.1 Single qubit gates. Classical computer circuits consist of wires and logic gates. The wires are used to carry information around the circuit, while the logic gates perform manipulations of the information, converting it from one form to another. Consider, for example, classical single-bit logic gates. The only non-trivial member of this class is the NOT gate, whose operation is defined by the truth table, where 0 goes to 1 and 1 goes to 0. That is, the 0 and 1 states are interchanged. Can an analogous quantum NOT gate for qubits be defined? Well, imagine that we have some processes which took the state ket 0 and the state ket 1, and vice versa. Such a process would obviously be a good candidate for a quantum analog to the NOT gate. However, Specifying the action of the gate on the states 0 and 1 does not tell us what happens to the superpositions of the states of 0 and 1. Without further knowledge about the properties of quantum gates, in fact, the quantum NOT gate acts linearly. That is, it takes the state shown in equation 1.8 to the corresponding state in which the role of ket 0 and ket 1 have been interchanged, as shown in equation 1.9. Why the quantum NOT gate acts linearly and not in some nonlinear fashion is a very interesting question, and the answer is not at all obvious. It turns out that this linear behavior is a general property of quantum mechanics and very well motivated empirically. Moreover, nonlinear behavior can lead to apparent paradoxes such as time travel, faster than light communication, and violations of the second law of thermodynamics. We'll explore this point in more depth in later changes, but for now we'll just take it as given. There is a convenient way of representing the quantum NOT gate in matrix form, which follows directly from the linearity of quantum gates. Suppose we define a matrix X to represent the quantum NOT gate as follows, shown in equation 1.10. The notation X for the quantum NOT gate is used for historical reasons. If the quantum state alpha ket 0 plus beta ket 1 is written as a vector notation as shown in equation 1.11, with the top entry corresponding to the amplitude for ket 0 and the bottom entry the amplitude for ket 1, then the corresponding output from the quantum NOT gate is as shown in equation 1.12. Notice that the action of the NOT gate is to take the state ket 0 and replace it by the state corresponding to the first column of the matrix X. Similarly, the state ket 1 is replaced by the state corresponding to the second column of the matrix X. So quantum gates on a single qubit can be described by two matrices. Are there any constraints on what matrices may be used as quantum gates? It turns out that there are. Recall that the normalization conditions require the magnitude of alpha squared plus magnitude of beta squared is equal to 1 for a quantum state alpha ket 0 plus beta ket 1. This must also be true for the quantum state ket psi prime is equal to alpha prime ket 0 plus beta prime ket 1 after the gate has acted. It turns out that the appropriate condition on the matrix representing the gate is that the matrix U describing the single qubit gate be unitary. That is, adjoint of U times U is equal to the identity matrix, where the adjoint of U is the adjoint of U, obtained by transposing and then complex conjugating U, and I is the 2x2 identity matrix. For example, for the NOT gate, it is easy to verify that adjoint of X multiplied by X is equal to the identity matrix. Amazingly, this unitary constraint is the only constraint on quantum gates, and a unitary matrix specifies a valid quantum gate. The interesting implication is that in contrast to the classical case, where only the non-trivial single-bit gate exists, the NOT gate There are many non-trivial single quantum gates. The two important ones, which we shall use later, are the Z gate, as shown in equation 1.13, which leaves ket 0 unchanged and flips the sign of ket 1 to give minus ket 1, and the Hadamard gate, as shown in equation 1.14. This gate is sometimes described as being like a square root of NOT gate, in that it turns a ket 0 into the ket plus, the first column of H, halfway between ket 0 and ket 1, and turns ket 1 into ket minus, second column of H, which is also halfway between ket 0 and ket 1. Note, however, that H squared is not a NOT gate, as simple algebra shows that h squared is equal to identity, and thus applying h twice to a state does nothing to it. The Hadamard gate is one of the most useful quantum gates, and it is worth trying to visualize its operation by considering the Bloch sphere picture. In this picture, it turns out that single qubit gates correspond to rotations and reflections of the sphere. The Hadamard operation is just a rotation of the sphere about the y-axis by 90 degrees, followed by a rotation about the x-axis by 180 degrees, as illustrated in Figure 1.4. Some important single qubit gates are shown in Figure 1.5 and contrasted with the classical case. There are infinitely many 2x2 unitary matrices, and thus infinitely many single qubit gates. However, it turns out that the properties of the complete set can be understood from the properties of a much smaller set. For example, as explained in Box 1.1, an arbitrary single qubit unitary gate can be decomposed as a product of rotations, shown in equation 1.15, and a gate which we'll later understand as being a rotation about the z-axis, as shown in equation 1.16. Together with a global phase shift, a constant multiplier of the form e to the power of I times alpha. These gates can be broken down further. We don't need to be able to do these gates for arbitrary alpha, beta, and gamma, but can build arbitrarily good approximations to such gates using only special fixed values of alpha, beta, and gamma. In this way, it is possible to build up an arbitrary single quantum gate using a finite set of quantum gates. More generally, an arbitrary quantum computation on any number of qubits can be generated by a finite set of gates that is said to be universal for quantum computation. To obtain such a universal set, we first need to introduce some quantum gates involving multiple qubits. Box 1.1, decomposing a single qubit operation. In section 4.2, starting on page 174, we prove that an arbitrary 2x2 unitary matrix may be decomposed as equation 1.17, where alpha, beta, gamma, and delta are real valued. Notice that the second matrix is just an ordinary rotation. It turns out the first and last matrices can also be understood as rotations in a different plane. This decomposition can be used to give an exact prescription for performing an arbitrary single qubit quantum logic gate. 1.3.2 Multiple qubit gates. Now let us generalize from one to multiple qubits. Figure 1.6 shows 5 notable multiple bit classical gates, the AND, OR, XOR, and NAND and NOR gates. An important theoretical result is that any functional bits can be computed from the composition of NAND gates alone, which is thus known as a universal gate. By contrast, the XOR alone, or even together with the NOT gate, is not universal. One way of seeing this is to note that applying an XOR gate does not change the total parity of the bits. As a result, any circuit involving NOT and XOR gates will, if two inputs x and y have the same parity, give outputs with the same parity, restricting the class of functions which may be computed and thus precluding universality. The prototypical multi-qubit quantum logic gate is the controlled NOT or CNOT gate. This gate has two input qubits, known as the control qubit and the target qubit. Respectively, the circuit representation of the CNOT is shown in the top right of Figure 1.6. The top line represents the control qubit, while the bottom line represents the target qubit. The action of the gate may be described as follows. If the control qubit is set to 0, then the target qubit is left alone. If the control qubit is set to 1, then the target qubit is flipped. In equations, ket 00 goes to ket 00, ket 01 goes to ket 01, ket 10 goes to ket 11, and ket 11 goes to ket 10. as shown in equation 1.18. Another way of describing the C0 is as a generalization of the classical XOR gate, since the action of the gate may be summarized as ket A, B to ket A, B addition modulo 2 of A, where the target plus sign is addition modulo 2, which is exactly what this XOR gate does. That is, the control qubit and the target qubit are XORed and stored in the target qubit. Yet another way of describing the action of the C0 gate is to give the matrix representation as shown in the bottom right of figure 1.6. You can easily verify that in the first column of Cn describes the transformation that occurs to 00, ket 00, and similarly for the other computational basis states ket 01, ket 10, and ket 11. As for the single qubit case, the requirement that the probability be conserved is expressed in the fact that U subscript Cn is a unitary matrix, that is, the adjoint of UCn times UCn is equal to the identity matrix. We noticed that the C0 gate can be regarded as a type of generalized XOR gate. Can other classical gates, such as the NAND or the regular XOR gate, be understood as unitary gates in a similar sense to the way the quantum NOT gate can be represented as the classical NOT gate? It turns out that this is not possible. The reason is because the XOR and NAND gates are essentially irreversible or non-invertible. For example, given the output A plus modulo 2B, for example, given the output A plus B modulo 2 from an XOR gate, it is not possible to determine the inputs A and B were. It is not possible to determine what the inputs A and B were. There is an irreversible loss of information associated with the irreversible action of the XOR gate. On the other hand, unitary quantum gates are always invertible, since the inverse of a unitary matrix is also a unitary matrix, and thus a quantum gate can always be inverted by another quantum gate. Understanding how to do classical logic in this reversible or invertible sense will be a crucial step in understanding how to harness the power of quantum mechanics for computation. We'll explain the basic idea of how to do reversible computation in section 1.4.1. Of course, there are many interesting quantum gates other than the controlled NOT. However, in a sense, the controlled NOT and single qubit gates are prototypes for all other gates, because the following remarkable universality result that any multiple qubit logic gate may be computed from C0 and single qubit gates. The proof is given in section 4.5 and is the quantum parallel of the universality of the NAND gate. Measurements and bases other than the computational basis. We've described quantum measurement for a single qubit in the state alpha ket 0 plus beta ket 1 as yielding the result 0, 1, and leaving the qubit in the corresponding state ket 0, ket 1, with respective probabilities of the absolute value of alpha squared and absolute value of beta squared. In fact, quantum mechanics allows somewhat more versatility in the class of measurements that may be performed, although certainly nowhere near enough to recover alpha and beta from a single measurement. Note that the states ket0 and ket1 represent just one of many possible choices of basis states for a qubit. Another possible choice is the set ket plus and ket minus. An arbitrary state ket psi is equal to alpha ket0 plus beta ket1 can be re-expressed in terms of the states ket plus and ket minus, as shown in equation 1.19. It turns out that it is possible to treat the ket plus and ket minus states as though they were computational basis states, and measure with respect to this new basis. Naturally, measuring with respect to the ket plus ket minus basis results in the result plus with probability of the magnitude of alpha plus beta squared over 2, and results minus with the probability of absolute value of alpha minus beta squared over 2, with corresponding post-measurement states ket plus and ket minus respectively. More generally, given any basis states ket A and ket B for a qubit, it is possible to express an arbitrary state as a linear combination of alpha ket A plus beta ket B for those states. Furthermore, provided the states are orthonormal, it is possible to perform a measurement with respect to the ket A ket B basis, giving the results A with probability magnitude alpha squared and B with probability magnitude beta squared. The orthonormality constraint is necessary in order that magnitude alpha squared plus magnitude beta squared is equal to 1, as we expect for probabilities. In an analogous way, it is possible in principle to measure a quantum system for many qubits with respect to an arbitrary orthonormal basis. However, just because it is possible in principle does not mean that such a measurement can be done easily, and we return later to the question of how efficiently a measurement in an arbitrary basis state can be performed. There are many reasons for using this external formalism for quantum measurements, but ultimately the best one is this. The formalism allows us to describe observed experimental results, as we will see in our discussion of the Stern-Gerlach experiment in section 1.5.1, and even more sophisticated and convenient but essentially equivalent formalism for describing quantum measurements is described in the next chapter in section 2.2.3. 1.3.4 Quantum circuits. We've already met a few simple quantum circuits. Let's look in a little more detail at the elements of a quantum circuit. A simple quantum circuit containing 3 quantum gates is shown in figure 1.7. The circuit is used to be read from left to right. Each line in the circuit represents a wire in the quantum circuit. This wire does not necessarily correspond to a physical wire. It may correspond instead to the passage of time, or perhaps to a physical particle such as a photon, a particle of light moving from one location to another through space. It is conventional to assume that the state input to the circuit is a computational basis state, usually the state consisting of all ket zeros. This rule is broken frequently in the literature on quantum computation and quantum information, but it is considered polite to inform the reader when this is the case. The circuit in figure 1.7 accomplishes a simple but useful task. It swaps the states of 2 qubits. To see that the circuit accomplishes the swap operation, note that the sequence of gates has the following sequence of effects on a computational basis state: ket alpha comma b, a comma b, as shown in equation 1.20. Where all additions are done modulo 2, the effect of the circuit, therefore, is to interchange the state of the 2 qubits. There are a few features allowed in classical circuits that are not usually present in quantum circuits. First of all, we don't allow loops, that is, feedback from one part of the quantum circuit to another. we say the circuit is acyclic. Second, classical circuits allow wires to be joined together, an operation known as fan-in, with the resulting single wire containing the bitwise OR of the inputs. Obviously, this operation is not reversible and therefore not unitary, so we don't allow fan-in in our quantum circuits. Third, the inverse operation fan-out, whereby several copies of a bit are produced, is also not allowed in quantum circuits. In fact, it turns out that quantum mechanics forbids the copying of a qubit, making the fan-out operation impossible. We'll see an example of this in the next section when we attempt to design a circuit to copy a qubit. As we proceed, we'll introduce new quantum gates as needed. It's convenient to introduce another convention about quantum circuits at this point. This convention is illustrated in figure 1.8. Suppose U is any unitary matrix acting on some number n of qubits, so U can be regarded as a quantum gate on those qubits. Then we can define a controlled U gate, which is a natural extension of the controlled NOT gate. Such a gate has a single control qubit, indicated by the line with the black dot, and n target qubits, indicated by the boxed U. If the control qubit is set to 0, nothing happens to the target qubits. If the control qubit is set to 1, then the gate U is applied to the target qubits. The prototypical example of the controlled U gate is the controlled NOT gate, which is a controlled U gate with the U equals X, as illustrated in figure 1.9. An important operation is measurement, which we represent by a meter symbol, as shown in figure 1.10. As previously described, this operation converts a single qubit state, ket psi, as alpha ket 0 plus beta ket 1 into a probabilistic classic bit M, distinguished from a qubit by drawing it as a double-line wire, which is 0 with probability magnitude alpha squared or 1 with probability magnitude beta squared. We shall find quantum circuits useful as models of all quantum processes, including but not limited to computation, communication, and even quantum noise. Several simple examples illustrate this below. 1.3.5 Qubit copying circuit. The CNOT gate is useful for demonstrating one particularly fundamental property of quantum information. Consider the task of copying a classical bit. This may be done using a classical CNOT gate, which takes in a bit to copy in some known state X, and a scratch pad bit initialized to 0, as illustrated in figure 1.11. The input is 2 bits, both of which are in the same state X. Suppose we try to copy a qubit in the known state ket psi and a ket 0 plus b ket 1 in the same manner by using a CNOT gate. The input state of 2 qubits may be written as shown in equation 1.21. The function of CNOT is to negate the second qubit when the first qubit is 1, and thus the output is simply a ket 00 and b ket 11. Have we successfully copied psi, ket psi? That is, have we created the state ket psi times ket psi in the case where ket psi is ket 0 or ket psi is ket 1? That is indeed what the circuit does. It is possible to use quantum circuits to copy classical information encoded as a ket 0 or a ket 1. However, for a general state ket psi, we see that equation 1.22 holds. Comparing with a ket 00 plus b ket 11, we see that unless a times b equals 0, the copying circuit above does not copy the quantum state input. In fact, it turns out to be impossible to make a copy of an unknown quantum state. This property, that qubits cannot be copied, is known as the no-clouding theorem, and it is one of the chief differences between quantum and classical information. The no-cloning theorem is discussed in more length in the box 12.1 on page 532. The proof is very simple and we encourage you to skip ahead and read the proof now. There is another way of looking at the failure of the circuit in figure 1.11 based on the intuition that a qubit somehow contains hidden information, not directly accessible to measurement. Consider what happens when we measure one of the qubits of the state A ket 00 plus B ket 11. As previously described, we obtain either 0 or 1 with probabilities magnitude A squared and magnitude B squared. However, once the qubit is measured, the state of the other one is completely determined and no additional information can be gained about A and B. In this sense, the extra hidden information carried in the original qubit, ket psi, was lost in the first measurement and cannot be regained. If, however, the qubit has been copied, then the state of the other qubit should still contain some of that hidden information. Therefore, a copy cannot have been created. 1.36 Example: Bell states. Let's consider a slightly more complicated circuit shown in figure 1.12, which has a Hadamard gate followed by a CNOT and transforms the four computational basis states according to the table given. As an explicit example, the Hadamard gate takes the input ket 00 to ket plus, and then ket plus times ket 0, and then the CNOT gives the output state ket plus plus. Note how this works. First, the Hadamard transform puts the top qubit in superposition. This then acts as a control input to the CNOT, and the target gets inverted only when the control is 1. The output states, as shown in equations 1.23 to 1.26, are known as the Bell states, or sometimes the EPR states, or EPR pairs. After some of the people, Bell and Einstein, Podolsky, and Rosen, who first pointed out the strange properties of states like these, the mnemonic notation ket beta 00, ket beta 01, ket beta 10, ket beta 11 may be understood via the equation shown in equation 1.27, where y bar is the negation of y. 1.3.7 Example: Quantum teleportation. We will now apply the techniques of the last few pages to understand something non-trivial, surprising, and a lot of fun: quantum teleportation. Quantum teleportation is a technique for moving quantum states around, even in the absence of a quantum communications channel linking the sender of the quantum state to the recipient. Here's how quantum teleportation works. Alice and Bob met long ago but now live far apart. While together, they generated an EPR pair, each taking one bit of the EPR pair when they separated many years later. Bob is in hiding, and Alice's mission, should she choose to accept it, is to deliver a qubit ket psi to Bob. She does not know the state of the qubit and moreover can only send classical information to Bob. Should Alice accept the mission? Intuitively, things look pretty bad for Alice. She doesn't know the state of ket psi of the qubit she has to send to Bob, and the laws of quantum mechanics prevent her from determining the state when she only has a single copy of ket psi in her possession. What's worse, even if she did know the state ket psi, determining it precisely takes an infinite amount of classical information, since ket psi takes values in a continuous space. So even if she did know ket psi, it would take forever for Alice to describe the state to Bob. It's not looking good for Alice. Fortunately, for Alice, quantum teleportation is a way of a way of utilizing the entanglement. Fortunately for Alice, quantum teleportation is a way of utilizing the entangled EPR pair in order to send Kepsi to Bob, with only a small overhead of classical communication. In outline, the steps of the solution are follows. Alice interacts the qubit Kepsi with her half of the EPR pair, and then measures the two qubits in her possession, obtaining one of four possible classical results: 00, 01, 10, and 11. She sends this information to Bob. Depending on Alice's classical message, Bob performs one of four operations on his half of the EPR pair. Amazingly, by doing this he can recover the original state of Kepsi. The quantum circuit shown in figure 1.13 gives a more precise description of quantum teleportation. The state to be teleported is Kepsi, which is equal to alpha ket 0 plus beta ket 1, where alpha and beta are unknown amplitudes. The state input into the circuit, Kepsi naught, is equal to Kepsi times Kep beta 00, as shown in equation 1.28. And equation 1.29. Where we use the convention that the first two qubits on the left belong to Alice and the third qubit to Bob. As we explained previously, Alice's second qubit and Bob's qubit start out as an EPR pair. Since Alice sends her qubit through a CNOT gate, obtaining equation 1.30, she then sends the first qubit through a Hadamard gate, obtaining equation 1.31. This state may be rewritten in the following way simply by regrouping terms, as shown in equation 1.32. This expression naturally breaks down into four terms. The first term has Alice's qubits in the state ket 00 and Bob's qubit in the state alpha 0, alpha ket 0 plus beta ket 1, which is the original state Kepsi. If Alice performs a measurement and obtains the result 00, then Bob's system will be in the state Kepsi. Similarly, from the previous expression, we can read off Bob's post-measurement state given the results of Alice's measurement, as shown in equations 1.3 to 1.6. Depending on Alice's measurement outcome, Bob's qubit will end up in one of these four possible states. Of course, to know which state it is in, Bob must be told the result of Alice's measurement. We will show later that it is this fact which prevents teleportation from being used to transmit information faster than light. Once Bob has learned the measurement outcome, Bob can fix up his state by recovering Kepsi by applying the appropriate quantum gate. For example, in the case where the measurement yields 00, Bob doesn't need to do anything. If the measurement is 01, then Bob can fix up his state by applying the X gate. If the measurement is 10, then Bob can fix up his state by applying the Z gate. If the measurement is 11, then Rishi can fix up his state by applying the X and now the Z gate. Summing up, Sam needs to apply the transformation Z to the power of m1, X to the power of m2. Note how the time goes from left to right in circuit diagrams, but in matrix products, terms on the right happen first to his qubit, and he will recover the state Kepsi. There are many interesting features of teleportation, some of which we shall return to later in this book. For now, we content ourselves with commenting on a couple of aspects. First, Doesn't teleportation allow one to transmit quantum states faster than light? This would be rather peculiar, because the theory of relativity implies that faster than light information transfer could be used to send information backwards in time. Fortunately, quantum teleportation does not enable faster than light communication. Because to complete the teleportation, Alice must transmit her measurement results to Bob over a classical communications channel. We will show in section 2.4.3 that without this classical communication, teleportation does not convey any information at all. The classical channel is limited by the speed of light, so it follows that quantum teleportation cannot be accomplished faster than the speed of light, resolving the apparent paradox. A second puzzle about teleportation is that it appears to create a copy of the quantum state being teleported. This apparent violation of the no-cloning theorem, discussed in section 1.3.5, this violation is only illusory, since after the teleportation process, only the target qubit is left in the state ket psi, and the original data qubit ends up in one of the computational basis states, ket 0 or ket 1, depending upon the measurement result of the first qubit. What can we learn from quantum teleportation? Quite a lot. It's much more than just a neat trick that one can do with quantum states. Quantum teleportation emphasizes the interchangeability of different resources in quantum mechanics, showing that one shared EPR pair together with two classical bits of communication is a resource at least the equal of one qubit of communication. Quantum computation and quantum information has revealed a plethora of methods for interchanging resources, many built upon quantum teleportation. In particular, in Chapter 10 we explain how teleportation can be used to build quantum gates which are resistant to the effects of noise. And in Chapter 12 we show that teleportation is intimately connected with the properties of quantum error-correcting codes. Despite these connections with other subjects, it is fair to say that we are only beginning to understand why it is that quantum teleportation is possible in quantum mechanics. In later chapters, we endeavor to explain some of the insights that make such an understanding possible. 1.4 Quantum Algorithms. What class of computations can be performed using quantum circuits? How does that class compare with the computations which can be performed using classical logical circuits? Can we find a task which a quantum computer may perform better than a classical computer? In this section, we investigate these questions, explaining how to perform classical computations on quantum computers, giving some examples of problems for which quantum computers offer an advantage over classical computers, and summarizing the known quantum algorithms. 1.4.1 Classical computations on a quantum computer. Can we simulate a classical log circuit using a quantum circuit? Not surprisingly, the answer to this question turns out to be yes. It would be very surprising if this were not the case, as physicists believe that all other aspects of the world around us, including classical logic circuits, can ultimately be explained using quantum mechanics. As pointed out earlier, the reason quantum circuits cannot be used to directly simulate classical circuits is because unitary quantum logic gates are inherently reversible, whereas many classical logic gates, such as the NAND gate, are inherently irreversible. Any classical circuit can be replaced by an equivalent circuit containing only reversible elements by making use of the reversible gate known as the Toffoli gate. The Toffoli gate has 3 input bits and 3 output bits, as illustrated in figure 1.14. To two of the bits are control bits that are unaffected by the action of the Toffoli gate. The third bit is a target bit that is flipped if both control bits are set to 1, and otherwise is left alone. Note that applying the Toffoli gate twice to a set of bits has the effect that A, B, C goes to A, B, C plus AB modulo 2, which then goes back to A, B, C, and thus the Toffoli gate is a reversible gate since it has an inverse itself. The Toffoli gate can be used to simulate NAND gates as shown in figure 1.15, and can also be used to do fan-out as shown in figure 1.16. With these two operations, it becomes possible to simulate all other elements in a classical circuit, and thus an arbitrary classical circuit can be simulated by an equivalent reversible circuit. The Toffoli gate has been described as a classical gate, but it can also be implemented as a quantum logic gate. By definition, the quantum logic implementation of the Toffoli gate simply permutes the computational basis states in the same way the classical Toffoli gate. For example, the quantum Toffoli gate acting on the state ket 110 flips the third qubit because the first two are set, resulting in the state ket 111. It is tedious but not difficult to write this transformation out as an 8x8 matrix, U, and verify explicitly that U is a unitary matrix, and thus the Toffoli gate is a legitimate quantum gate. The quantum Toffoli gate can be used to simulate irreversible classical logic gates. Just as the classical Toffoli gate was, and ensures that quantum computers are capable of performing any computation which a classical deterministic computer may do. What if the classical computer is non-deterministic? What if it has the ability to generate random bits to be used in the computation? Not surprisingly, it is easy for a quantum computer to simulate this. To perform such a simulation, it turns out to be sufficient to produce random fair coin tosses, which can be done by preparing a qubit in the state 0, ket 0, sending it through a Hadamard gate to produce ket plus, and then measuring the state. The result will be either ket 0 or ket 1 with 50-50 probability. This provides a quantum computer with the ability to efficiently simulate a non-deterministic classical computer. Of course, if the ability to simulate classical computers were the only feature of quantum computers, there would be little point in going to all the trouble of exploiting quantum effects. The advantage of quantum computing is that much more powerful functions may be computed using qubits and quantum gates. In the next few sections, we explain how to do this, culminating in the Deutsch-Jozsa algorithm, our first example of a quantum algorithm able to solve a problem faster than any classical algorithm. 1.4.2 Quantum Parallelism. Quantum parallelism is a fundamental feature of many quantum algorithms. Heuristically, and at the risk of oversimplifying, quantum parallelism allows quantum computers to evaluate a function f of x for many different values of x simultaneously. In this section, we explain how quantum parallelism works and explain some of its limitations. Suppose f of x is defined as set 0, 1 to set 0, 1, is a function with a 1-bit domain and a range. A convenient way of computing this function on a quantum computer is to consider a 2-qubit quantum computer which starts in the state ket x, y. With an appropriate sequence of logic gates, it is possible to transform the state into ket x, y plus f of x modulo 2. The first register is called the data register, and the second register the target register. We give the transformation defined by the map ket x, y to ket x, y plus f of x modulo 2 a name u of f, and note that it is easily shown to be unitary. If y is equal to 0, then the final state of the second qubit is just the value of f of x. In section 3.2.5, we show that given a classical circuit for computing f, there is a quantum circuit of comparable efficiency which computes the transformation of u of f on a quantum computer. For our purposes, it can be considered to be a black box. Consider the circuit shown in figure 1.17, which applies u of f to an input not in the computational basis. Instead, the data register is prepared in the superposition ket plus, which can be created with a Hadamard gate acting on ket 0. Then we apply u of f, resulting in the state ket 0, f of 0 plus ket 1, f of 1 over root 2, as shown in equation 1.37. This is a remarkable state. The different terms contain information about both f0 and f1. It is almost as if we have evaluated f of x for two values of x simultaneously, a feature known as quantum parallelism. Unlike classical parallelism, where multiple circuits each built to compute f of x are executed simultaneously, here, a single f of x circuit is employed to evaluate the function for multiple values of x simultaneously. By exploiting the ability of a quantum computer to be in superpositions of different states, this procedure can easily be generalized into functions on an arbitrary number of bits by using a general operation known as the Hadamard transform, or sometimes the Walsh-Hadamard transform. This operation is just n Hadamard gates acting in parallel on n qubits. For example, shown in figure 1.18, is the case n equals 2, with qubits initially prepared as ket 0, which gives equation 1.38 as output. We write h superscript tensor 2 to denote the parallel action of two Hadamard gates, and read the circled cross as tensor. More generally, the result of performing the Hadamard transform on n qubits initially in all ket 0 the ket 0 state is equation 1.39, where the sum is over all possible values of x, and we write h superscript tensor n to denote this action. That is, the Hadamard transform produces an equal superposition of all computational basis states. Moreover, it does this extremely efficiently, producing a superposition of 2 to the power of n states using just n gates. Quantum parallel evaluation of a function with an n-bit input x and 1-bit output f of x can thus be performed in the following manner. Prepare the n plus 1 qubit state ket 0 superscript tensor n ket 0, then apply the Hadamard transform to the first n qubits, followed by the quantum circuit implementing u of f, This produces the state shown in equation 1.40. In some sense, quantum parallelism enables all possible values of the function f to be evaluated simultaneously, even though we apparently only evaluated f once. However, this parallelism is not immediately useful. In our single qubit example, measurement of the state gives only either ket 0, f0 or ket 1, f1. Similarly, in the general case, measurement of the state sum over x ket x, f of x would give only f of x for a single value of x. Of course, a classical computer can do this easily. Quantum computation requires something more than just quantum parallelism to be useful. It requires the ability to extract information about more than one value of f of x from superposition states like sum over x ket x, f of x. Over the next two sections, we investigate examples of how this may be done. One point 4.3 Deutsch's algorithm. A simple modification of the circuit in Figure 1.17 demonstrates how quantum circuits can outperform classical ones by implementing Deutsch's algorithm. We actually present a simplified and improved version of the original algorithm. See history and further reading at the end of the chapter. Deutsch's algorithm combines quantum parallelism with a property of quantum mechanics known as interference. As before, let us use the Hadamard gate to prepare the first qubit as the superposition ket plus, but now let us prepare a second qubit y as the superposition ket minus, using the Hadamard gate applied to the state ket 1. Let us follow the states along to see what happens in this circuit, shown in figure 1.19. The input state, ket psi naught is equal to 0 ket 01, as shown in equation 1.41, is sent through two Hadamard gates to give equation 1.42. Little thought shows that if we apply u of f to the state x times ket minus, then we obtain the state minus 1 to the power of f of x ket minus. Applying u of f to ket psi of 1 therefore leaves us with one of two possibilities, shown in equation 1.43. The final Hadamard gate on the first qubit thus gives us equation 1.44. Realizing that f0 plus f1 modulo 2 is 0 if f0 equals f1 and 1 otherwise, we can rewrite the result concisely as equation 1.45. So by measuring the first qubit, we may determine f0 plus f1 over modulo 2. This is very interesting indeed. The quantum circuit has given us the ability to determine a global property of f of x, namely f0 plus f1 modulo 2, using only one evaluation of f of x. This is faster than is possible with a classical apparatus, which would require at least two evaluations. This example highlights the difference between quantum parallelism and classical randomized algorithms. Naively, one might think that the state ket 0, ket f of 0 plus ket 1 ket f of 1 corresponds rather closely to a probabilistic classical computer that evaluates f0 with probability 1/2 or f1 with probability 1/2. The difference is that in a classical computer, these two alternatives forever exclude one another. In in a quantum computer, it is possible for the two alternatives to interfere with one another to yield some global property of the function f by using something like the Hadamard gate to recombine the different alternatives, as was done in Deutsch's algorithm. The essence of the design of many quantum algorithms is that clever choice of function and final transformation allows efficient determination of useful global information about the function, information which cannot be attained quickly on a classical computer. 1.4.4 The Deutsch-Jozsa algorithm. Deutsch's algorithm is a simple case of a more general quantum algorithm, which we shall refer to as the Deutsch-Jozsa algorithm. The application known as Deutsch's problem may be described as the following game. Alice, in Amsterdam, selects a number z from 0 to 2 to the power of n minus 1 and mails it in a letter to Cyrus. In Boston, Bob calculates some function f of x and replies with the result, which is either 0 or 1. Now Bob has promised to use a function f which is of one of two kinds. Either f of x is constant for all values of x, or else f of x is balanced, that is, equal to 1 for exactly half of all the possible x and 0. For the other half, Luxana's goal is to determine with certainty whether Bob has chosen a constant or balanced function, corresponding with him as little as possible. How fast can she succeed? In the classical case, Alice may only send Bob one value of x in each letter. At worst, Alice will need to query Bob at least 2 to the power of n divided by 2 plus 1 times, since she may receive 2 to the power of n over 2 zeros before finally getting a 1, telling her that Bob's function is balanced. The best deterministic classical algorithm she can use therefore requires 2 to the n over 2 plus 1 queries. Note that in each letter, Sophia sends Bob n bits of information. Furthermore, in this example, physical distance is being used to artificially elevate the cost of calculating f of x, but this is not needed in the general problem, where f of x may be inherently difficult to calculate. If Bob and Alice were able to exchange qubits instead of just classical bits, and if Bob agreed to calculate f of x using a unitary transform u of f, then Alice could achieve her goal in just one correspondence with Bob, using the following algorithm. Analogously to Deutsch's algorithm, Alice has an n-qubit register to store her query in, and a single qubit register which she will give to Bob to store the answer in. She begins by preparing both her query and answer registers in a superposition state. Bob will evaluate f of x using quantum parallelism and leave the result in the answer register. Alice then interferes states in the superposition using Hadamard transform on the query register and finishes by performing a suitable measurement determining whether f was constant or balanced. The specific steps of the algorithm are depicted in figure 1.20. Let us follow the states through the circuit. The input state, shown in equation 1.46, is similar to that of equation 1.41, but here the query register describes the state of n qubits all prepared in the ket0 state. After the Hadamard transform on the query register and the Hadamard gate on the answer register, we have equation 1.47. The query register is now a superposition of all states, and the answer register is an evenly weighted superposition of 0 and 1. Next, the function f is evaluated by Bob using u of f as defined by ket of x comma y going to ket of x comma y plus f of x modulo 2, giving equation 1.48. Alice now has a set of qubits in which the result of Bob's function evaluated Bob's function evaluation is stored in the amplitude of the qubit superposition state. She now interfaces terms in the superposition using a Hadamard transform on the query register to determine the result of the Hadamard transform. It helps to first calculate the effect of the Hadamard transform on a state ket x. By checking the case x equals 0 and x equals 1 separately, we see that for a single qubit, the Hadamard gate ket x is equal to the sum over z minus 1 to the power of x times z ket z over 2. Thus, equation 1.49. This can be summarized more succinctly in the very useful equation 1.50, where x dot z is a bitwise inner product of x and z modulo 2. Using this equation and equation 1.48, we can now evaluate ket psi of 3, as shown in equation 1.51. Alice now observed the query register. Note that the amplitude for the state ket 0 to the power of tensor n is the sum over x of minus 1 to the power of f of x over 2 to the n. Let's look at the two possible cases, f constant and f balanced, to discern what happens. In the case where f is constant and the amplitude for ket 0 superscript tensor n is plus 1 or minus 1, depending on the constant value f takes. Because ket psi 3 is of unit length, it follows that all the other amplitudes must be 0, and an observation will yield zeros for all qubits in the query register. If f is balanced, then the positive and negative contributions to the amplitude for ket 0 to the power of tensor n cancel, leaving an amplitude of 0, and a measurement must yield a result other than 1 on at least one qubit in the query register. Summarizing, if Alice measures all 0, then the function is constant. Otherwise, the function is balanced. The Deutsch-Jozsa algorithm is summarized below. Algorithm Deutsch-Jozsa. Inputs 1. A black box U of f which performs the transformation ket x ket y to ket x ket y plus f of x over, modulo 2 for x as a member of the set 0 to n plus 2 minus 1, and f of x as the member of the set 0 to 1. It is promised that f of x is either constant for all values of x, or else f of x is balanced, that is, equal to 1 for exactly half of all the possible x and 0 for all the other half. Outputs 0 if and only if f is constant. Runtime, one evaluation of UF always succeeds. Procedure: initialize state, create superposition using Hadamard gates, calculate function f using U of f, perform Hadamard transformation, and measure to obtain final output z. We've shown that a quantum computer can solve Deutsch's problem with one evaluation of the function f compared to the classical requirement for 2 to the n over 2 plus 1 evaluations. This appears impressive, but there are several important caveats. First, Deutsch's problem is not an especially important problem. It has no known applications. Second, the comparison between classical and quantum algorithms is in some ways an apples and oranges comparison, as the method for evaluating the function is quite different in the two cases. Third, if Alice is allowed to use probabilistic classical computer, then by asking Bob to evaluate f of x for a few randomly chosen x, she can very quickly determine with high probability whether f is constant or balanced. This probabilistic scenario is perhaps more realistic than a deterministic scenario we have been considering. Despite these caveats, the Deutsch-Jozsa algorithm contains the seed for more impressive quantum algorithms, and is enlightening to attempt to understand the principles behind its operation. Exercise 1.1 Probabilistic Classic Algorithm. Suppose that the problem is not to distinguish between the constant and balance function with certainty, but rather with some probability of error uh, epsilon is less than half. What is the performance of the best classical algorithm for this problem? Hmm. 1.4.5 Quantum algorithms summarized. The Deutsch-Jozsa algorithm suggests that quantum computers may be capable of solving some computational problems, such as problems much more efficiently than classical computers. Unfortunately, the problem it solves is of little practical interest. Are there more interesting problems whose solutions may be obtained more efficiently using quantum algorithms? What are the principles underlying such algorithms? What are the ultimate limits of quantum computers' computational power? Broadly speaking, there are three classes of quantum algorithms which provide an advantage over known classical algorithms. First, there is the class of algorithms based upon quantum versions of the Fourier transform, a tool which is also widely used in classical algorithms. The Deutsch-Jozsa algorithm is an example of this type of algorithm, as are Shor's algorithms for factoring and discrete logarithm. The second class of algorithm is quantum search algorithms, and the third class of algorithms is quantum simulation, whereby a quantum computer is used to simulate a quantum system. We now briefly describe each of these classes of algorithms, and then summarize what is known or suspected about the computational power of quantum computers. Quantum algorithms based upon the Fourier transform. The discrete Fourier transform is naturally described as transforming a set x0 to xn of n complex numbers into a set of complex numbers y0 to yn minus 1, defined in equation 1.52. Of course, this transformation has an enormous number of applications in many branches of science. The Fourier transformed version of a problem is often easier than the original problem, enabling a solution. The Fourier transform was proved to be so useful that a beautiful generalized theory of Fourier transform has been developed, which goes beyond the definition of 1.52. This general theory involves some technical ideas from the character theory of finite groups, and we will not attempt to describe it here. What is important is that the Hadamard transform used in the Deutsch-Jozsa algorithm is an example of this generalized class of Fourier transforms. Moreover, many of the other important quantum algorithms also involve some type of Fourier transform. The most important quantum algorithms, known Shor's fast algorithms for factorizing and discrete logarithm, are two examples of algorithms based upon the Fourier transform described in equation 1.5. The equation 1.52. The equation 1.52 does not appear terribly quantum mechanical in the form we have written it. Imagine, however, that we describe a linear transformation U on n qubits by its action on computational basis states ket J, where J is greater than or equal to 0 and less than or equal to 2n minus 1. Which gives equation 1.53. It can be checked that this information is unitary, and in fact can be realized as a quantum circuit. Moreover, if we write out its actions on superpositions, we see that it corresponds to a vector notation for the Fourier transform 1.52 for the case n equals 2 to the n, shown in the equation 1.54. How quickly can we perform the Fourier transform? Classically, the first Fourier transform takes roughly n log of n, which is equal to n2 of n, 2 to the power of n, steps to Fourier transform. Steps to Fourier transform n equals 2 to the power of n numbers. On a quantum computer, the Fourier transform can be accomplished using about log squared of n, which is equal to n squared steps, an exponential saving. The quantum circuit to do this is explained in Chapter 5. This result seems to indicate that quantum computers can be used to very quickly compute the Fourier transform of a vector of 2 to the power of n complex numbers, which would be fantastically useful in a wide range of applications. However, that is not exactly the case. The Fourier transform is being performed on the information hidden in the amplitudes of the quantum state. This information is not directly accessible to measurement. The catch, of course, is that if the output state is measured, it will collapse each qubit into a state ket0 or ket1, preventing us from learning the transformation result yk directly. This example speaks to the heart of the conundrum of devising a quantum algorithm. On the one hand, we can perform certain calculations on the 2 to the n amplitudes associated with n qubits far more efficiently than would be possible for a classical computer. But, on the other hand, the result of such a calculation are not available to us if we go about it in a straightforward manner. More cleverness is required in order to harness the power of quantum computation. Fortunately, it does turn out to be possible to utilize the quantum Fourier transform to efficiently solve the several problems that are believed to have no efficient solutions on a classical computer. These problems include Deutsch's algorithm and Shor's algorithms for discrete logarithm and factorizing. This line of thought culminated in Kitayev's discovery of a method to solve the abelian stabilizer problem, and the generalization to the hidden subgroup problem. Let f be a function from a finitely generated group G to a finite set X, such that f is a constant on the cosets of a subgroup K and distinct on each coset. Given a quantum black box for performing the unitary transform, U ket G ket H is equal to G ket G ket H plus f of G modulo 2 for G as a part of G and H as a part of X, and addition modulo 2 an appropriately chosen binary operation on X. Find a generating set for K. The Deutsch-Shor's algorithm, and related exponentially fast quantum algorithms can all be viewed as special cases of this algorithm. The quantum Fourier transform and its applications are described in Chapter 5. Quantum search algorithms. A completely different class of algorithms is presented by the quantum search algorithm, whose basic principles were discovered by Grover. The quantum search algorithm solves the following problem. Given a search space of size n and no prior knowledge about the structure of the information in it, we want to find an element for that search space satisfying a known property. How long does it take to find an element satisfying that property? Classically, the problem requires approximately n operations, as the quantum search algorithm allows it to be solved using approximately root n operations. The quantum search algorithm offers a quadratic speedup, as opposed to the more impressive exponential speedup offered by algorithms based on the quantum Fourier transform. However, the quantum search algorithm is still of great interest, since searching heuristics have a wider range of application than the problem solved using the quantum Fourier transform, and adaptations of the quantum search algorithm may have utility for a very wide range of problems. The quantum search algorithm and its applications are described in Chapter 6. Quantum simulation. Simulating naturally occurring quantum mechanical systems is an obvious candidate for a task at which quantum computers may excel, yet which is believed to be difficult on a classical computer. Classical computers have difficulty simulating general quantum systems, for much the same reasons they have difficulty simulating quantum computers. The number of complex numbers needed to describe a quantum system generally grows exponentially with the size of the system rather than linearly, as occurs in classical systems. In general, storing the quantum state of a system with n distinct components takes something like c to the power of n bits of memory on a classical computer, where c is a constant which depends upon details of the system being simulated and the desired accuracy of the simulation. By contrast, a quantum computer can perform the simulation using kn bits, where k is again a constant which depends upon the details of the system being simulated. This allows quantum computers to efficiently perform simulations of quantum mechanical systems that are believed not to be efficiently simulatable on a classical computer. A significant caveat is that even though a quantum computer can simulate many quantum systems far more efficiently than a classical computer, this does not mean that the fast simulation will allow the desired information about the quantum system to be obtained. When measured, a kn qubit simulation will collapse into a definite state using only kn bits of information. The c to the n bits of hidden information in the wave function is not entirely accessible. Thus, a crucial step in making quantum simulations useful is development of systematic means by which desired answers can be efficiently extracted. How to do this is only partially understood. Despite this caveat, quantum simulation is likely to be an important application of quantum computers. Simulation of quantum systems is an important problem in which many fields, notably quantum chemistry, where the computational constraints imposed by classical computers make it difficult to accurately simulate the behavior of even moderately sized molecules, much less the very large molecules that occur in many important biological systems. Obtaining faster and more accurate simulations for such systems may therefore have the welcome effect of enabling advances in other fields in which quantum phenomena are important. In the future, we may discover a physical phenomenon in nature which cannot be efficiently simulated on a quantum computer. Far from being bad news, this would be wonderful. At the least, it will stimulate us to extend our models of computation to encompass the new phenomenon and increase the power of our computational models beyond the existing quantum computing model. It also seems likely that very interesting new physical effects will be associated with any such phenomenon. Another application for quantum simulation is as a general method to obtain insight into other quantum algorithms. For example, in section 6.2, we explain how the quantum search algorithm can be viewed as the solution to a problem of quantum simulation. By approaching the problem in this fashion, it becomes much easier to understand the origin of the quantum search algorithm. Finally, the quantum simulation also gives rise to an interesting and optimistic quantum corollary to Moore's law. Recall that Moore's law states that the power of classical computation will double once every 2 years or so for constant cost. However, suppose Suppose we are simulating a quantum system on a classical computer and want to add a single qubit or a larger system to the system being simulated. This doubles or more the memory requirements needed for a classical computer to store a description of the state for the quantum system, with a similar or greater cost and time needed to simulate the dynamics. The quantum corollary to Moore's law follows from this observation, stating that quantum computers are keeping pace with classical computers, provided a single qubit is added to the quantum computer every 2 years. This corollary should not be taken too seriously, as the exact nature of the gain, if any, of quantum computation over classical is not yet clear. Nevertheless, this heuristic statement helps convey why we should be interested in quantum computers and hopeful that they will one day be able to outperform the most powerful classical computers, at least for some applications. The power of quantum computation. How powerful are quantum computers? What gives them their power? Nobody, nobody yet knows the answers to these questions, despite the suspicions fostered by examples such as factoring, which strongly suggest that quantum computers are more powerful than classic computers. It is still possible that quantum computers are no more powerful than classical computers, in the sense that any problem which can be efficiently solved on a quantum computer can also be efficiently solved on a classical computer. On the other hand, it may eventually be proved that quantum computers are much more powerful than classical computers. We now take a brief look at what is known about the power of quantum computation. Computational complexity theory is the subject of classifying the difficulty of various computational problems, both classical and quantum. And to understand the power of quantum computers, we will first examine some general ideas from computational complexity. The most basic idea is that of a complexity class. A complexity class can be thought of as a collection of computational problems, all of which share some common feature with respect to the computational resources needed to solve those problems. Two of the most important complexity cases go by the names P and NP. Roughly speaking, P is the class of computational problems that can be solved quickly on a classical computer. NP is the class of problems which have solutions which can be quickly checked on a classical computer. To understand the distinction between P and NP, consider the problem of finding prime factors of an integer. Problem of finding the prime factors of an integer n. So far as is known, there is no fast way of solving the problem on a classical computer, which suggests that the problem is not in P. On the other hand, if someone tells you that some number P is a factor of n, then we can quickly check that this is correct by dividing P into n. So factoring is a problem NP. It is clear that P is a subset of NP, since the ability to solve a problem implies the ability to check potential solutions. What is not clear is whether or not there are problems in NP that are not in P. Perhaps the most important unsolved problem is theoretical computer science, is to determine whether these two cases are different. Most researchers believe that NP contains problems that are not in P. In particular, there is an important subclass of the NP problems, the NP-complete problems, that are of special importance for two reasons. First, There are thousands of problems, many highly important, that are known to be NP-complete. Second, any given NP-complete problem is in some sense at least as hard as all other problems in NP. More precisely, an algorithm to solve a specific NP-complete problem can be adapted to solve any other problem in NP with a small overhead. In particular, if P does not equal NP, then it will follow that no NP-complete problem can be effectively solved on a classical computer. It is not known whether quantum computers can be used to quickly solve all the problems in NP, despite the fact that they can be used to solve some problems, like factoring, which are believed by many people to be in the NP but not NP. Note that factoring is not known to be NP-complete, otherwise we already know how to efficiently solve all problems in NP using quantum computers. It would certainly be very exciting if this were possible to solve all problems in NP efficiently on a quantum computer. There is a very interesting negative result known in this direction, which rules out using a simple variant of quantum parallelism to solve all problems in NP. Specifically, one approach to the problem of solving problems in NP on quantum computers is to try to use some form of quantum parallelism to search in parallel through all possible solutions to the problem. In section 6.6, we will show that no approach based on such a search-based methodology can yield an efficient solution to all the problems in NP. While it is disappointing that this approach fails, it does not rule out that some deeper structure exists in the problems in NP that will allow them all to be solved quickly using a quantum computer. P and NP are just two of a plethora of complexity classes that have been defined. Another important complexity class is P-space. Roughly speaking, P-space consists of those problems which can be solved using resources which are few in spatial size, that is, the computer is small. But not necessarily in time. Long computations are fine. P-space is believed to be strictly larger than both P and NP, although, again, this has never been proved. Finally, the complexity class BPP is the class of problems that can be solved using randomized algorithms in polynomial time. If a bounded probability of error, say 1/4, is allowed in the solution to the problem, BPP is widely regarded as being even more so than P, the class of problems which should be considered efficiently soluble on a classical computer. We have elected to concentrate here on P rather than BPP because P has been studied in more depth. However, many similar ideas and conclusions arise in connection with BPP. What of quantum complexity classes? We can define BQP to be the class of all quantum computational problems which can be solved effectively on a quantum computer, where a bounded probability of error is allowed. Strictly speaking, this makes BQP more analogous to the classical quantum complexity class BPP than to P. However, we will ignore this subtlety for the purpose of the present discussion and treat it as the analog of P. Exactly where BQP fits with respect to P, NP, and P-space is yet unknown. What is known is that quantum computers can solve all the problems in P efficiently, but that there are no problems outside of P-space which can solve efficiently. However, BQP lies somewhere between P and P-space, as illustrated in Figure 1.21. An important implication is that if it is proved that quantum computers are strictly more powerful than classical computers, then it will follow that P is not equal to P space. Proving this latter result has been attempted without success by many computer scientists, suggesting it to be non-trivial to prove that quantum computers are more powerful than classical computers. Despite much evidence in favor of this proposition. We won't speculate further on the ultimate power of quantum computation now, preferring to wait until after we have better understood the principles on which fast quantum algorithms are based, a topic which occupies us for most of part 2 of this book. What is already clear is that the theory of quantum computation poses interesting and significant challenges to the traditional notions. What is already clear is that the theory of quantum computation poses interesting and significant challenges to the traditional notions of computation. What makes this an important challenge is that the theoretical model for quantum computation is believed to be experimentally realizable, because, to the best of our knowledge, this theory is consistent with the way nature works. If this were not so, then quantum computation would be just another mathematical curiosity. 1.5 Experimental Quantum Information Processing. Quantum computation and quantum information is a wonderful theoretical discovery, but its central concepts, such as superpositions and entanglement, are counter to the intuition we gather from the everyday world around us. What evidence do we have that these ideas truly describe how nature operates? Will the realization of large-scale quantum computers be experimentally feasible? Or might there be some principle in physics which fundamentally prohibits their eventual scaling? In the next 2 sections, we address these questions. We begin with a review of the famous Stern-Gerlach experiment, which provides evidence for the existence of qubits in nature. We then widen our scope, addressing the broader problem of how to build practical quantum information processing systems. 1.51 The Stern-Gerlach experiment. The qubit is a fundamental element for quantum computation and quantum information. How do we know that systems with the properties of qubits exist in nature? At the time of writing, there is an enormous amount of evidence that this is so. But in the early days of quantum mechanics, the qubit structure was not all that obvious, and people struggled with phenomena that we may now understand in terms of qubits, that is, in terms of two-level quantum systems. A decisive and very famous early experiment indicating the qubit structure was conceived by Stern in 1921 and performed with Gerlach in 1922 in Frankfurt. In the original Stern-Gerlach experiment, hot atoms were beamed from an oven through a magnetic field, which caused the atoms to be deflected, and then the position of each atom was recorded, as illustrated in Figure 1.22. The original experiment was done with silver atoms, which have a complicated structure that obscures the effects we are discussing. What we describe below actually follows a 1927 experiment done using hydrogen atoms. The same basic effect is observed, but with hydrogen atoms, the discussion is easier to follow. Keep in mind, though, that this privilege wasn't available to people in the early 1920s, and they had to be very ingenious to think up explanations for the more complicated effects they observed. Hydrogen atoms contain a proton and an orbiting electron. You can think of this electron as a little electric current around the proton. This electric current causes the atom to have a magnetic field. Each atom has what physicists call a magnetic dipole moment. As a result, each atom behaves like a little bar magnet with an axis corresponding to the axis the electron is spinning around. Throwing little bar magnets through a magnetic field causes the magnets to be deflected by the field, and we expect to see a similar deflection of atoms in the Stern-Gerlach experiment. How the atom is deflected depends upon both the atom's magnetic dipole moment, the axis the electron is spinning around, the magnetic field generated by the Stern-Gerlach device, device. We won't go through the details, but suffice to say that by constructing the Stern-Gerlach device appropriately, we can cause the atom to be deflected by an amount that depends upon the z component of the atom's magnetic dipole moment, where z is some fixed external axis. Two major surprises emerge when this experiment is performed. First, since the hot atoms exiting the oven would naturally be expected to have their dipoles oriented randomly in every direction, it would follow that there would be a continuous distribution of atoms seen at all angles exiting from the Stern-Gerlach device. Instead, what is seen is atoms emerging from a discrete set of angles. Physicists were able to explain this by assuming the magnetic dipole moment of the atoms is quantized, that is, comes in discrete multiples of some fundamental amount. This observation of quantization in the Stern-Gerlach experiment was surprising to physicists of the late 1920s, but not completely astonishing because evidence for quantization effects in other systems was becoming widespread at the time. What was truly surprising was the number of peaks seen in the experiment. The hydrogen atoms being used were such that they would have zero magnetic dipole moment. Classically, this is surprising in itself, since it corresponds to no orbital motion of the electron, but based on what was known of quantum mechanics at the time, it was an acceptable notion. Since the hydrogen atom would therefore have zero magnetic moment, it was expected that only one beam of atoms would be seen, and this beam would not be deflected by the magnetic field. Instead, two beams were seen, one deflected up by the magnetic field and the other deflected down. The puzzling doubling was explained after considerable effort by positing that the electron in the hydrogen atom was associated with a quantity called spin. This spin is not in any way associated to the actual rotational motion of the electron around the proton. It is an entirely new quantity to be associated with an electron. The great physicist Heisenberg labeled the idea brave at the time it was suggested. And it is a brave idea since it introduces an essentially new physical quantity into nature. The spin of the electron is posited to make an extra contribution to the magnetic dipole moment of the hydrogen atom, in addition to the contribution due to the rotational motion of the electron. What is the proper description of the spin of an electron? At first guess, we might hypothesize that the spin is specified by a single bit, telling us the hydrogen atom to go up or down. Additional experimental results provide further useful information to determine if this guess needs refinement or replacement. Let's represent the original Stern-Gerlach apparatus as shown in figure 1.2.2. Its outputs are of two beams of atoms, which we shall call ket Z plus and ket Z minus Z. We're using suggestive notation which looks quantum mechanical, but of course you're free to use whatever notation you prefer. Now suppose we cascade two Stern-Gerlach apparatuses together, as shown in figure 1.23. We arrange it so that the second apparatus is tipped sideways, so that the magnetic field deflects atoms along the z-axis. In our thought experiment, we'll plug off the ket minus z output from the first Gerlach apparatus, while the ket plus z output is sent through a second apparatus orientated along the x-axis. A detector is placed at the final output to measure the distribution of atoms along the x-axis. A classical magnetic dipole pointed at the plus z direction has no net magnetic moment in the x direction, so we might expect that the final output would have one central peak. However, experimentally it is observed that there are two peaks of equal intensity. So perhaps these atoms are peculiar and have definite magnetic moments along each axis, independently. That is, maybe each atom passing through the second apparatus can be described as being a state we might write as ket plus z ket x plus, or ket plus z, ket x minus, to indicate the two values for spin that might be observed. Another experiment shown in figure 1.24 can test this hypothesis by sending one beam of the previous output through a second z-orientated Stern-Gerlach apparatus. If the atoms have retained their positive z orientation, then the output would also be expected to only have one peak at the ket plus z output. However, again two beams are observed at the final output of equal intensity. Thus, the conclusion would seem to be that contrary to classic expectations, a ket plus z state consists of equal proportions of ket x plus and ket x minus states, and a ket plus x state consists of equal proportions of ket plus z and ket minus z states. Similar conclusions can be reached if the Stern-Gerlach apparatus is aligned along some other axis, like the y-axis. The qubit model provides a simple explanation of this experimentally observed behavior. Let ket 0 and ket 1 be the states of a qubit, and make the assignments shown in equations 1.56 to 1.59. Then the results of the cascaded Stern-Gerlach experiment can be explained by assuming that the Z Stern-Gerlach apparatus measures the spin, that is, the qubit, in the computational bases ket 0 and ket 1, and the X Stern-Gerlach apparatus measures the spin with respect to the bases ket plus and ket minus. For example, in the cascades ZXZ experiment, if we assume that the spins are in the state plus ket plus Z is equal to ket 0, which is equal to ket plus, after exiting the first Stern-Gerlach experiment, then the probability of obtaining ket x plus out of the second apparatus is half, and the probability for ket x minus is half. Similarly, the probability of obtaining ket plus z out of the third apparatus is half, and a qubit model thus properly predicts the results from this type of cascaded Stern-Gerlach experiment. This example demonstrates how qubits could be a believable way of modeling systems in nature. Of course, it doesn't establish beyond all doubt that the qubit model is the correct way of understanding electron spin. Far more experimental corroboration is required. Nevertheless, because of many experiments like these, we now believe that electron spin is best described by the qubit model. What is more, we believe that the qubit model and generalizations of it to higher dimensions, quantum mechanics, in other words, is capable of describing every physical system. We now turn to the question of what systems are especially well adapted to quantum information processing. One point 5.2 Prospects for practical quantum information processing. Building quantum information processing devices is a great challenge for scientists and engineers of the third millennium. Will we rise to meet the challenge? Is it possible at all? Is it worth attempting? If so, how might this feat be accomplished? These are difficult and important questions, to which we essay brief answers to in this section, to be expanded upon throughout the book. The most fundamental question is whether there is any point of principle that prohibits us from doing one or more forms of quantum information processing. Two possible obstructions suggest themselves: that noise may place a fundamental barrier to useful quantum information processing, or that quantum mechanics may fail to be correct. Noise is without a doubt a significant obstruction to development of practical quantum information processing devices. It is a fundamentally irremovable obstruction that will forever prevent the development of large-scale quantum information processing devices. The theory of quantum error correcting codes strongly suggests that quantum noise is a practical problem that needs to be addressed. It does not present a fundamental problem of principle. In particular, there is a threshold theorem for quantum computation which states, roughly speaking, that provided the level of noise in a quantum computer can be reduced below a certain constant threshold value, quantum error correcting codes can be used to push it down even further, essentially ad infinitum, for a small overhead and complexity of the computation. The threshold theorem makes some broad assumptions about the nature and magnitude of the noise occurring in a quantum computer and the architecture available for performing quantum computation. However, provided those assumptions are satisfied, the effects of noise can be made essentially negligible for quantum information processing. Chapters 8, Chapters 10, and Chapters 12 discuss quantum noise, quantum error correction, quantum threshold, and the threshold theorem in detail. A second possibility that may prelude quantum information processing is if quantum mechanics is correct. Indeed, prohibiting the validity of quantum mechanics, both relativistic and non-relativistic, is one reason for being invested in building quantum information processing devices. Never before have we explored a regime of nature in which complete control has been obtained over large-scale quantum systems, and perhaps nature may reveal some new surprises in this regime which are not adequately explained by quantum mechanics. If this occurs, it will be a momentous discovery in the history of science, and can be expanded to have considerable consequences in other areas of science and technology, as did the discovery of quantum mechanics. Such a discovery might also impact quantum computation and quantum information. However, whether the impact would enhance, detract, or not affect the power of quantum information processing cannot be predicted in advance. Until and unless such effects are found to have no way of knowing. Until and unless such effects are found, we have no way of knowing how they might affect information processing, and so for the remainder of this book, we go with all the evidence to date and assume that quantum mechanics is a complete and correct description of the world. Given that there is no fundamental obstacle to building Quantum information processing devices. Why should we invest enormous amounts of time and money into attempting to do so? We have already discussed several reasons for wanting to do so: practical applications such as quantum cryptography and factorizing of large composite numbers, and the desire to obtain fundamental insight into nature and information processing. These are good reasons, and justify a considerable investment of time and money in the effort to build quantum information processing devices. However, it is fair to say that a clearer picture of the relative power of quantum and classical information processing is needed in order to assess their relative merits. To obtain such a picture requires further theoretical work on the foundations of quantum computation and quantum information. Of a particular interest is a decisive answer to the question, are quantum computers more powerful than classical computers? Even if the answer to such a question eludes us for the time being, it would be useful to have a clear path of interesting applications at varying levels of complexity to aid researchers aiming to experimentally realize quantum information processing. Historically, the advance of technology is often hastened by the use of short to medium-term incentives as a stepping stone to long-term goals. Consider that microprocessors were initially used as controllers for elevators and other simple devices before graduating to be fundamental components in normal computers, and then onto who knows what. Below we sketch out a path of short to medium-term goals for people interested in achieving the long-term goals of large-scale quantum information processing. Surprisingly, many small-scale applications of quantum computation and quantum information are known. Not all are flashy as cousins like the quantum factorizing algorithm, but, but, but the relative ease of implementing small-scale applications makes them extremely important as medium-term goals in themselves. Quantum state tomography and quantum process tomography are two elementary processes whose perfection is of great importance to quantum computation and quantum information, as well as being independent interest in their own right. Quantum state tomography is a method for determining the quantum state of a system. To do this, it has to overcome the hidden nature of the quantum state. Remember, the state can't be directly determined by a measurement, by performing repeated preparations of the same quantum state, which is then measured in different ways in order to build up a complete description of the quantum nature. Quantum process tomography is a more ambitious but closely related procedure to completely characterize the dynamics of a quantum system. Quantum process tomography can, for example, be used to characterize the performance of an alleged quantum gate or quantum communications channel, or to determine the types of magnitudes of different noise processes in a system. Besides obvious applications to quantum computation and quantum information, quantum process tomography can be expected to have significant applications as a diagnostic tool to aid in the evaluation and improvement of primitive operations in any field of science and technology where quantum effects are important. Quantum state tomography and quantum process tomography are described in more detail in Chapter 8. Various small-scale communications primitives are also of great interest. We have already mentioned quantum cryptography and quantum teleportation. The former is likely to be useful in practical applications, involving the distribution of a small amount of key material that needs to be highly secure. The uses of quantum teleportation are perhaps more open to question. We will see in Chapter 12 that teleportation may be an extremely useful primitive for transferring quantum states between distant nodes in a network in the presence of noise. The idea is to focus one's efforts on distributing EPR pairs between the nodes that wish to communicate. The EPR pairs may be corrupted during communication, but special entanglement distillation protocols can be used to clean up the EPR pairs, enabling them to be used to teleport quantum states from one location to another. In fact, protocols based upon entanglement distillation and teleportation and teleportation offer performance superior to more conventional quantum error correction techniques, enabling noise-free communication of qubits. What of the medium scale? A promising medium-scale application of quantum information processing is the simulation of quantum states. To simulate a quantum system consisting of a few dozen qubits, or the equivalent in terms of some other basic system, strains the resources of even the largest supercomputers. A simple calculation is instructive. Suppose we have a system containing 50 qubits. To describe the state of such a system requires 2 to the power of 50, or roughly equal to 10 to the 15 complex amplitudes. If the amplitudes are stored in 128 bits of precision, then it requires 256 bits, or 32 bytes, in order to store each amplitude, for a total of 32 times 10 to the 15 bytes of information, or about 32,000 terabytes of information, well beyond the capacity of existing supercomputers, and corresponding to about the storage capacity that might be expected to appear in supercomputers during the second decade of the 21st century, presuming that Moore's law continues on schedule. 90 qubits at the same level of precision requires 32 times 10 to the 27 bytes, which, even if implemented using single atoms to represent bits, would require kilograms or more of matter. How useful will quantum simulations be? It seems likely that conventional methods will still be used to determine elementary properties of materials such as bond strength and basic spectroscopic properties. However, once the basic properties are all well understood, it seems likely that quantum simulation will be of great utility as a laboratory for the design and testing of properties of novel molecules. In a conventional laboratory setup, many different types of hardware, chemicals, detectors, and so on may be required to test a wide variety of possible designs for a molecule. On a quantum computer, these less expensive and much faster On a quantum computer, these different types of hardware can all be simulated in software, which is likely to be much less expensive and much faster. Of course, final designs and testing must be performed with real physical systems. However, quantum computers may enable a much larger range of potential designs to be explored and evaluated en route to a better final design. It is interesting to note that such ab initio calculations to aid in the design of new molecules have been attempted on classical computers. However, they have met with limited success due to the enormous computational resources needed to simulate quantum mechanics on a classical computer. Quantum computers should be able to do much better in the relatively near future. What of large-scale applications? Aside from scaling up applications like quantum simulation and quantum cryptography, relatively few large-scale applications are known. The factoring of large numbers, taking discrete logarithms, and quantum searching interest in the first two of these derives mainly from the negative effects it would have of limiting the viability of existing public key cryptography systems. They might also be of substantial practical interest to mathematicians interested in these problems simply for their own sake. So it does not seem likely that factoring and discrete logarithm will be at all important as applications for the long run. Quantum search may be of tremendous use because of the wide utility of the search heuristic, and we discuss some possible applications in Chapter 6. What would really be superb are many more large-scale applications of quantum information processing. This is a great goal for the future. Given a path of potential applications for quantum information processing, how it can be achieved in real physical systems, at the small scale of a few qubits, there are already several working proposals for quantum information processing devices. Perhaps the easiest to realize are based upon optical techniques, that is, electromagnetic radiation, simple devices like mirrors and beam splitters can be used to do elementary manipulations of photons. Interestingly, a major difficulty has been producing single photons on demand. Experimentalists have instead opted to use schemes which produce single photons every now and then, at random, and wait for such an event to occur. Quantum cryptography and, and superdense coding and quantum teleportation have all been realized using such optical techniques. A major advantage of the optical techniques is that photons tend to be highly stable carriers of quantum mechanical information. A major disadvantage is that photons don't directly interact with one another. Instead, the interaction has to be mediated by something else, like an atom, which introduces additional noise and complications into the experiment. An effective interaction between two photons is set up, which essentially works in two steps. Photon number 1 interacts with the atom, which in turn interacts with the second photon, causing an overall interaction between the two photons. An alternative scheme is based upon methods for trapping different types of atom. Here is the ion trap, in which a small number of charged atoms are trapped in a confined space, and neutral atom traps for trapping uncharged atoms in a confined space. Quantum information processing schemes based upon atom traps use the atoms to store qubits. Electromagnetic radiation also shows up in these schemes, but in a rather different way, that is, than in what we refer to as the optical approach to quantum information processing. In these schemes, photons are used to manipulate information stored in the atoms themselves, rather than the place the information is stored. Single qubit quantum gates can be performed by applying appropriate pulses of electromagnetic radiation to individual atoms. Neighboring atoms can interact with one another via, for example, dipole forces that can enable quantum gates to be accomplished. Moreover, the exact nature of the interaction between neighboring atoms can be modified by applying appropriate pulses of electromagnetic radiation to the atoms. Given the experimentalist's control over what gates are performed in the system, finally quantum measurements can be accomplished in the system using the long-established quantum jumps technique, which implements with superb accuracy the measurements and the computational basis used for quantum computation. Another class of quantum information processing schemes is based upon nuclear magnetic resonance, often known by its initials NMR. These schemes store quantum information in the nuclear spin of atoms in a molecule, and manipulate that information using electromagnetic radiation. Such schemes pose special difficulties because in NMR it's not possible to directly access individual nuclei. Instead, a large number, typically around 10 to the 15, of essentially identical molecules are stored in solution. Electromagnetic pulses are applied to the sample, causing each molecule to respond in roughly the same way. You should think of each molecule as being an independent computer, and the sample as containing a huge number of computers, all running in parallel, classically. NMR, quantum information processing, faces three special difficulties that make it rather different from other quantum information processing schemes. First, the molecules are typically prepared by letting them equilibrate at room temperature, which is so much higher than typical spin flip energies that the spins become nearly completely randomly orientated. This fact makes this initial state rather more the initial state rather more noisy than is desirable for quantum information processing. How this noise may be overcome is an interesting story that we tell in Chapter 7. A second problem is that the class of measurements may be performed in NMR falls well short of the most general measurements we'd like to perform in quantum information processing. Nevertheless, for many instances of quantum information processing, the class of measurements allowed in NMR is sufficient. Third, because molecules cannot be individually addressed in NMR, you might ask how it is that individual qubits can be manipulated in an appropriate way. Fortunately, different nuclei in the molecule can have different properties that allow them to be individually addressed, or at least addressed at a sufficiently fine-grained scale, to allow the operations essential for quantum computation. Many of the elements required to perform large-scale quantum information processing can be found in existing proposals. Superb state preparation and quantum measurements can be performed on a small number of qubits in the ion trap. Superb dynamics can be performed in small molecules using NMR. Fabrication technology and solid-state systems allow designs to be scaled up tremendously. A single system having all these elements would be a long way down the road to a dream quantum computer. Unfortunately, all these systems are very different, and we are many years from having large-scale quantum computers. However, we believe that the existence of all these properties in existing, albeit different, systems does bode well for the long-term existence of large-scale quantum information processes. Furthermore, it suggests that there is a great deal of merit to pursuing hybrid designs which attempt to marry the best features of two or more existing technologies. For example, there is much work being done on trapping atoms inside electromagnetic cavities that enables flexible manipulation of the atom inside the cavity via optical techniques and makes possible real-time feedback control of the single atom in ways unavailable in conventional atom traps. To conclude, note that it is important not to assess quantum information processing as though it were just another technology for information processing. For example, it is tempting to dismiss quantum computation as yet another technological fad in the evolution of the computer that will pass in time, much as other fads have passed. For example, the bubble memories, widely touted as the next big thing in memory during the early 1980s. This is a mistake, since quantum computation is an abstract paradigm for information processing that may have many different implementations in technology. One can compare two different proposals of quantum computing as regards their technological merits. It makes sense to compare a good proposal to a bad proposal. However, even a very poor proposal for a quantum computer is of a different qualitative nature from a superb design for a quantum computer. 1.6 Quantum information. The term quantum information is used in two distinct ways in the field for quantum computation and quantum information. The first usage is a broad catch-all for all manner of operations that might be interpreted as related to information processing. Using quantum mechanics. This use encompasses subjects such as quantum computation, quantum teleportation, and the no-cloning theorem, and virtually all other topics in this book. The second use of quantum information is much more specialized. It refers to the study of elementary quantum information processing tasks. It does not typically include, for example, quantum algorithm design, since the details of specific quantum algorithms are beyond the scope of elementary. To avoid confusion, we will use the term quantum information theory to refer to this more specialized field, in parallel with the widely used term classical information theory to describe the corresponding classical field. Of course, the term quantum information theory has a drawback of its own. It might be seen as implying that theoretical considerations are all that matter. Of course, this is not the case. And experimental demonstrations of the elementary processes studied by quantum information theory is of great interest. The purpose of this section is to introduce the basic ideas of quantum information. The purpose of this section is to introduce the basic ideas of quantum information theory. Even with the restriction of elementary quantum information processing tasks, quantum information theory may look like a disordered zoo to the beginner, with many apparently unrelated subjects failing under the quantum information theory rubric. In part, that's because the subject is still under development and is not yet clear how all the pieces fit together. However, we can identify a few fundamental goals uniting work on quantum information theory. First, or 1, identify elementary causes of static resources in quantum mechanics. An example is the qubit. Another example is the bit. Classical physics arises as a special case of quantum physics, so it should not be surprising that elementary static resources appearing in classical information theory should also be of great relevance in quantum information theory. Yet another example of an elementary class of static resources is the Bell state shared between two distant parties. 2. Identify elementary cases of dynamical processes in quantum mechanics. A simple example is memory, the ability to store a quantum state over some period of time. Less trivial processes are quantum information transmission between two parties, Alice and Bob, copying or trying to copy a quantum state, and the process of protecting quantum information processing against the effects of noise. 3. Quantify resource trade-offs incurred performing elementary dynamical processes. For example, what is the minimal resource required to reliably transfer quantum information between two parties using a noisy communications channel? Similar goals define classical information theory. However, quantum information theory is broader in scope than classical information theory. For quantum information theory includes all the static and dynamic elements of classical information theory, as well as additional static and dynamic elements. The remainder of this section describes some examples of questions studied by quantum information theory, in each case emphasizing the fundamental static and dynamic elements under consideration and the resource trade-offs being considered. We begin with an example that will appear quite familiar to classical information theorists, the problem of sending classical information through a quantum tunnel. We then begin to branch out and explore some of the new static and dynamic processes present in quantum mechanics, such as quantum error correction, the problem of distinguishing quantum states, and entanglement transformation. The chapter concludes with some reflections on how the tools of quantum information theory can be applied elsewhere in quantum computation and quantum information. 1.6.1 Quantum Information Theory Example Problems. Classical information throughout quantum channels. The fundamental results of classical information theory are Shannon's noiseless channel coding theorem and Shannon's noisy channel coding theorem. The noiseless channel coding theorem quantifies how many bits are required to store information being emitted by a source of information, while the noisy channel coding theorem quantifies how much information can reliably how many the noiseless channel coding theorem quantifies how many bits are required to store information being emitted by a source of information, while the noisy channel coding theorem quantifies how much information can be reliably transmitted through a noisy communications channel. What do we mean by an information source? Defining this notation is a fundamental problem of classical and quantum information theory, one we will re-examine several times. For now, let's go with a provisional definition A classical information source is described as a set of probabilities, Pj, where j goes from 1 to d. Each use of the source results in the letter j being omitted, chosen at random with probability Pj independently of each use of the source. For instance, if the source were of English text, then the number j might correspond to letters of the alphabet and punctuation, with the probabilities Pj giving the relative frequencies with which the different letters appear in regular English text. Although it is not true that the letters in English appear in in an independent fashion, for our purposes, it will be a good enough approximation. Regular English text includes a considerable amount of redundancy, and it is possible to exploit that redundancy to compress the text. For example, the letter E occurs much more frequently in regular English text than the letter Z. A good scheme for compressing English text will therefore represent the letter E using fewer bits of information than it uses to represent Z. Shannon's noiseless channel coding theorem quantifies exactly how well such a compression scheme can be made to work. More precisely, the noiseless channel coding theorem tells us that a classical source described by probabilities Pj can be compressed so that, on average, each use of the source can be represented using h of Pj bits of information, where h of Pj is equal to the negative sum over j of Pj times log of Pj, and is a function of the source probability distribution known as Shannon's entropy. Moreover, the noiseless channel coding theorem tells us that to attempt to represent the source using fewer bits than this will result in a high probability of error when the information is decompressed. Shannon's noiseless channel coding theorem is discussed in much greater detail in Chapter 12. Shannon's noiseless coding theorem provides a good example where the goals of information theory listed earlier are all met. Two static resources are identified, goal number 1, and the bit and the information source. A two-stage dynamic process is identified, goal 2, compressing an information source and then decompressing to recover the information source. Finally, a quantitative criterion for determining the resources consumed, goal 3, by an optimal data compression scheme is found. Shannon's second major result, the noisy channel coding theorem, quantifies the amount of information that can be reliably transmitted through a noisy channel. In particular, suppose we wish to transfer the information being produced by some information source to another location through a noisy channel. That location may be at another point in space or another point in time. The latter is the problem of storing information in the presence of noise. The idea in both instances is to encode the information being produced using error-correcting codes, so that any noise introduced by the channel can be corrected by the other end of the channel. The way error-correcting codes achieve this is by introducing enough redundancy into the information sent through the channel so that even after some of the information has been corrupted, it is still possible to recover the original message. For example, suppose the noisy channel is for the transmission of single bits, and the noise of the channel is such that to achieve reliable transmission, each bit produced by the source must be encoded using 2 bits, therefore being sent through the channel. We say that such a channel has a capacity of half a bit. Since each use of the channel can be used to reliably convey roughly half a bit of information. Shannon's noisy channel coding theorem provides a general procedure for calculating the capacity of an arbitrarily noisy channel. Shannon's noisy channel coding theorem also achieves the 3 goals of information theory we stated earlier. 2 types of static resources are involved. Goal 1, the information source and the bits being sent through the channel. 3 dynamical processors are involved. Goal 2, the primary source is the noise in the channel. To combat this, the noise we perform the dual process of encoding and decoding the state in an error-correcting code. For a fixed noise model, Shannon's theorem tells us how much redundancy must be introduced by an optimal error correction scheme if reliable information transmission is to be achieved. Goal 3. For both the noiseless and the noisy channel coding theorems, Shannon restricted himself to storing the output from an information source in classical systems, bits and the like. An actual question for quantum information theory is what happens if the storage medium is changed so that classical information is transmitted using quantum states as the medium. For example, it may be that Alice wishes to compress some classical information produced by an information source, transmitting the compressed information to Bob, who then decompresses it. If the medium used to store the compressed information is a quantum state, then Shannon's noiseless channel coding theorem cannot be used to determine the optimal compression and decompression scheme. One might wonder, for example, if using qubits allows a better compression rate than is possible classically. We'll study this question in Chapter 12 and prove that in fact qubits do not allow any significant saving in the amount of communication required to transmit information over a noiseless channel. Naturally, the next step is to investigate the problem of transmitting classical information through a noisy quantum channel. Ideally, what we'd like is a result that quantifies the capacity of such a channel for the transmission of information. Evaluating the capacity is a very tricky job for several reasons. Quantum mechanics gives a huge variety of noise models, since it takes place in a continuous space. It is not at all obvious how to adapt classical error correction techniques to combat the noise. Might it be advantageous, for example, to encode the classical information using entangled states, which are then transmitted one piece at a time through the noisy channel? Or perhaps it will be advantageous to decode using entangled measurements. In Chapter 12, we'll prove the HSW Holevo-Schumacher-Westmoreland theorem, which provides a low bound to the capacity of such a channel. Indeed, it is widely believed that the HSW theorem provides an exact evaluation of the capacity, although complete proof of this is not yet known. What remains at issue is whether or not encoding using entangled states can be used to raise the capacity beyond the lower bound provided the HSW theorem. All evidence to date suggests that this doesn't help raise the capacity, but is still a fascinating open problem of quantum information theory to determine the truth or falsity of this conjecture. Quantum information through quantum channels. Classical information is, of course, not the only static resource available in quantum mechanics. Quantum states themselves are a natural static resource, even more natural than classical information. Let's look at different quantum analogues to Shannon's coding theorems, this time involving the compression and decompression of quantum states. To begin, we need to define some quantum notion of an information source, analogous to the classical definition of an information source. As in the classical case, there are several different ways of doing this, but for the sake of definiteness, let's make the provisional definition that a quantum source is described by a set of probabilities, Pj, and corresponding quantum states, ket psi of j, ket psi subscript j. Each use of the source produces a state ket psi j with probability pj, with different uses of the source being independent of one another. Is it possible to compress the output from such a small quantum mechanical source? Consider the case of the qubit source, which outputs the state ket0 with probability p and the state ket1 with probability 1 minus p. This is essentially the same as a classical source emitting a single bit, either 0 with probability p or 1 with probability 1 minus p. It is not surprising that similar techniques can be used to compress the source so that only Shannon entropy of p and 1 minus p qubits are required to store the compressed source, where h is the Shannon entropy function. What if the source had instead been producing the state ket0 with probability p and the state ket plus with probability 1 minus p? The standard techniques of classical data compression no longer apply, since in general it's not possible for us to distinguish the states of 0 and ket0 and ket plus. Might it still be possible to perform some type of compression operation? It turns out that a type of compression is still possible, even in this instance. What is interesting is that the compression may no longer be error-free, in the sense that the quantum states being produced by the source may be slightly distorted by the compression. By the compression-decompression procedure. Nevertheless, we require that this distortion ought to become very small and ultimately negligible in the limit of large blocks of source output being compressed. To quantify the distortion, we introduce a fidelity measure for the compression scheme, which measures the average distortion introduced by the compression scheme. The idea of quantum data compression is that the compressed data should be recovered with very good fidelity. Thanks to the fidelity as being analogous to the probability of doing the decompression correctly, in the limit of large block lengths, it should tend towards the no error limit of 1. Schumacher's noiseless channel coding theorem quantifies the resources required to do quantum data compression, with the restriction that it be possible to recover the source with fidelity close to 1. In the case of a source producing orthogonal quantum states Kep psi j with probabilities pj, Schumacher's theorem reduces to telling us that the source may be compressed down but not beyond the classical limit. H of pj classical limit h of pj. However, in the more general case of non-orthogonal states being produced by the source, Schumacher's theorem tells us that much a quantum source may be compressed, and the answer is not the Shannon entropy h of pj. Instead, a new entropic quantity, the von Neumann entropy, turns out to be the correct answer. In general, the von Neumann entropy agrees with the Shannon entropy if and only if the states Kep psi j are orthogonal. Otherwise, the von Neumann entropy for the source pj, Kep psi j, is generally strictly smaller than the Shannon entropy h of pj. Thus, for example, a source producing the state ket0 with probability p and ket plus with probability 1 minus p can be reliably compressed using fewer than h of p 1 minus p qubits per use of the source. The basic intuition for this decrease in resources required can be understood quite easily. Suppose the source emitting states ket0 with probability p and ket plus with probability 1 minus p is used a large number of n times, then by the law of large numbers with a high probability, the source emits about np copies of ket0 and n 1 minus p copies of ket plus. That is, it has the form given by equation 1.6. After reordering of the systems involved, suppose we expand the product of ket0 plus ket1 terms on the right-hand side. Since n times 1 minus p is large, we can again use the law of large numbers to deduce that terms in the product will be roughly 1/2 ket zeros and 1/2 ket ones. That is, the ket zero plus ket one product can be well approximated by superposition of the states of the form given by equation 1.61. Thus, the state emitted by the source can be approximated as a superposition of terms of the form given by equation 1.62. How many states of this form are there? Roughly, n choose n times 1 plus p over 2, which by Stirling's approximation is equal to n, identical to 2 to the power of n times the Shannon entropy of 1 plus p over 2, 1 minus p over 2. A simple compression method then is to label all states from the form equation 1.62 C1 ket C1 through ket Cn. It is possible to perform a unitary transform on the n qubits emitted from the source that takes ket Cj to ket j ket 0 superscript tensor n minus n times the Shannon entropy of 1 plus p over 2, 1 minus p over 2. Since j is an n times Shannon entropy of 1 plus p over 2, 1 minus p over 2 bit number, the compression operation is to perform this unitary transformation and then drop the final n minus n Shannon entropy of 1 plus p over 2 plus 1 minus p over 2 qubits, leaving a compressed state of n times Shannon entropy of 1 plus p over 2, 1 minus p over 2 qubits. To decompress, we append the state of ket 0 superscript tensor n minus n times the Shannon entropy of 1 plus p over 2, 1 minus p over 2 to the compressed state and perform the inverse unitary transformation. This procedure for quantum data compression and decompression results in a storage requirement of This procedure for quantum data compression and decompression results in a storage requirement of h of 1 plus p over 2, 1 minus p over 2 qubits per use of the source, which whenever p is greater than or equal to 1/3 is an improvement over the h p, 1 minus p qubits we might natively have expected from Shannon's noiseless channel coding theorem. In fact, Schumacher's noiseless channel coding theorem allows us to do somewhat better than this, as we will see in chapter 12. However, the essential reason is that the construction is the same as the reason we are able to compress it. We exploited the fact that ket 0 and ket plus are not orthogonal. Intuitively, the states contain some redundancy, since both have a component in the ket 0 direction, which result in more physical similarity than would be obtained from orthogonal states. And this redundancy that we have exploited the coding scheme just described, and which is used in the full proof of Schumacher's noiseless channel coding theorem. Note that the restriction p is greater than or equal to 1/3 arises because when p is less than 1/3, this particular scheme doesn't exploit the redundancy in the states. We end up effectively increasing the redundancy present in the problem. Of course, this is an artifact of the particular scheme we have chosen, and the general solution exploits the redundancy in a much more sensible way to achieve data compression. Schumacher's noiseless channel coding theorem is an analog of Shannon's noiseless channel coding theorem for the compression and decompression of quantum states. Can we find an analog of Shannon's noiseless channel coding theorem? Considerable progress on this important question has been made using their theory of quantum error correcting codes. However, a fully satisfactory analog has not yet been found. We review some of what is known about the quantum channel capacity in Chapter 12. Quantum distinguishability. Thus far, all the dynamical processes we have considered, compression, decompression, noising, encoding and decoding, error correcting codes, arise in both classical and quantum information theory. However, the introduction of new types of information, such as quantum states, enlarged the class of dynamical problems beyond those considered in classical information theory. A good example is the problem of distinguishing quantum states. Classically, we are used to being able to distinguish different items of information, at least in principle. In practice, of course, a smudged letter A written on a page may be very difficult to distinguish from a letter O, but in principle it is possible to distinguish between the two possibilities with perfect certainty. On the other hand, quantum mechanically, it is not always possible to distinguish between arbitrary states. For example, there is no process allowed by the quantum mechanics that will reliably distinguish between the states ket0 and ket+, providing this rigorously requires tools we don't presently have available if it is done in Chapter 2. But by considering examples, it's pretty easy to convince oneself that it is not possible. Suppose, for example, that we try to distinguish the two states by measuring in the computational basis. Then, if we have been given the state ket0, the measurement will yield 0 with probability 1. However, we will measure ket+, the measurement yields 0 with probability half and 1 with probability half. Thus, while a measurement result of 1 implies the state must have been ket+, since it couldn't have been ket0, we can't infer anything about the identity of the quantum state from a result of 0. This indistinguishability of non-orthogonal quantum states is at the heart of quantum computation and quantum information. It is the essence of our assertion that a quantum state contains hidden information that is not accessible to a measurement and thus plays a key role in quantum algorithms and quantum cryptography. One of the central problems of quantum information theory is to develop measures quantifying how well non-orthogonal quantum states may be distinguished, and much of chapters 9 and 12 is concerned with this goal. In this introduction, we'll limit ourselves to positioning out two interesting aspects of indistinguishability: a connection with the possibility of faster-than-light communication and an application to quantum money. Imagine for a moment that we could distinguish between arbitrary quantum states. We'll show that this implies the ability to communicate faster than light using entanglement. Suppose Alice and Bob share an entangled pair of qubits in the state ket00 plus ket11 over root 2. Then, if Alice measures in the computational basis, the post-measurement states will be ket00 with probability half and ket11 with probability half. Thus, Bob's system is either in the state ket0 with probability half or in the state ket1 with probability half. Suppose, however, that Alice has instead measured in the ket minus basis. Recall that 0 is ket plus and ket1 is ket minus. A little algebra shows that the initial state of Alice and Bob's system may be written as ket plus ket minus minus over root 2. Therefore, if Alice measures in the plus minus basis, the state of Bob's system after the measurement will be ket plus or ket minus with probability half each. So far, this is all basic quantum mechanics, but if Bob has access to a device that could distinguish the four states, ket 0, ket 1, ket plus, ket minus, from one another, then he could tell whether Alice had measured in the computational basis or in the plus-minus basis. Moreover, he could get information instantaneously as soon as Alice had made the measurement, providing a means by which Alice and Bob could achieve faster-than-light communication. Of course, we all know that this is not possible to distinguish non-orthogonal quantum states. This example shows that this restriction is also intimately tied to other physical properties which we expect the world to obey. The indistinguishability of non-orthogonal quantum states need not always be a handicap. Sometimes it can be a boon. Imagine that a bank produces banknotes imprinted with a classical serial number and a sequence of qubits each in either the state ket 0 or ket plus. Nobody but the bank knows that sequence of these two states is embedded in the note, and the bank maintains a list matching serial numbers to embedded states. The note is impossible to counterfeit exactly, because it is impossible for a would-be counterfeiter to determine with certainty the states of the qubits in the original note without destroying them. When presented with the banknote, a merchant of certifiable repute can verify if it is not a counterfeit by calling the bank, telling them the serial number, and then asking what sequence of states were embedded in the note. They can then check that the note is genuine by measuring the qubits in the computational basis or the plus-minus basis, as directed by the bank, with probability which increases exponentially, the one with the number of qubits checked. Any would-be counterfeiter will be detected at this stage. This idea is the basis for numerous other quantum cryptographic protocols and demonstrates the utility of the indistinguishability of non-orthogonal quantum states. Creation Exercise 1.2. Explain how a device which upon input of one of two non-orthogonal quantum states, ket psi or ket phi, correctly identified the state could be used to build a device which cloned the states ket psi and ket phi in violation of the no cloning theorem. Conversely, explain how a device for cloning could be used to distinguish non-orthogonal quantum states. Creation and transformation of entanglement. Entanglement is another elementary static resource of quantum mechanics. Its properties are amazingly different from those of the resources most familiar from classical information theory, and they are not yet understood. We have at best an incomplete collage of results related to entanglement. We don't yet have all the language needed to understand the solutions, but let's at least look at two information theoretic problems related to entanglement. Creating entanglement is a simple dynamical process of interest in quantum information theory. How many qubits must two parties exchange if they are to create a particular entangled state shared between them, given that they share no prior entanglement? A second dynamical process of interest is transforming entanglement from one form into another. Suppose, for example, that Alice and Bob share between them a Bell state and wish to transform it into some other type of entangled state. What resources do they need to accomplish this task? Can they do it without communicating? With classical communication only? If quantum communication is required, then how much communication is required? Answering these and more complex questions about the creation and transformation of entanglement forms a fascinating area of study in its own right, and also promises to give insights into tasks such as quantum computation. For example, a distributed quantum computation may be viewed as simply a method for generating entanglement between two or more parties. Lower bounds on the amount of communication that must be done to perform such a distributed quantum computation then follow from lower bounds on the amount of computation that must be performed to create appropriate entangled states. 1.6.2 Quantum Information in a Wider Context. We have given but the barest glimpse of quantum information theory. Part 3 of this book discusses quantum information theory in much greater detail, especially Chapter 11, which deals with fundamental properties of entropy in quantum and classical information theory, and Chapter 12, which focuses on pure quantum information theory. Quantum information theory is the most abstract part of the quantum computation and quantum information, yet in some sense it is also the most fundamental. The question driving quantum information theory and ultimately all of quantum computation and quantum information is what makes quantum information processing tick. What is it that separates the quantum and the classical world? What resources unavailable in the classical world are being utilized in quantum computation? As distant answers to these questions are foggy and incomplete, it is our hope that the fog may yet lift in the years to come, and we will obtain a clear appreciation for the possibilities and limitations of quantum information processing. Problem 1.1 Feynman-Gates Conversation. Construct a friendly imaginary discussion of about 2,000 words between Bill Gates and Richard Feynman, set in the present on the future of computation. Comment: You may like to try writing until you've read. You might like to try waiting until you've read the rest of the book before attempting this question. See the history and further reading section below for pointers to one possible answer for this question. Problem 1.2 What is the most significant discovery yet made in quantum computation and quantum information? Write an essay about 2,000 words for an educated lay audience about the discovery. Comment: As for the previous problem, you might like to try waiting until you've read the rest of the book before attempting this question. History and further reading. Skip. End of chapter 1. Chapter 2: Introduction to Quantum Mechanics. I ain't no physicist, but I know what matters. Popeye the Sailor. Quantum Mechanics. Real black magic calculus. Albert Einstein. Quantum mechanics is the most accurate and complete description of the world known. It is also the basis for an understanding of quantum computation and quantum information. This chapter provides all the necessary background knowledge of quantum mechanics needed for a thorough grasp of quantum computation and quantum information. No prior knowledge of quantum mechanics is assumed. Quantum mechanics is easy to learn despite its reputation as a difficult subject. The reputation comes from the difficulty of some applications, like understanding the structure of complicated molecules, which aren't fundamental to a grasp of the subject. We won't be discussing such applications. The only prerequisite for understanding is some familiarity with elementary linear algebra. Provided you have this background, you can begin working out simple problems within a few hours, even with no prior knowledge of the subject. Readers already familiar with quantum mechanics can quickly skim through this chapter to become familiar with our mostly standard notation conventions, and to assure themselves of familiarity with all the material. Readers with little or no prior knowledge should work through the chapter in detail, pausing to attempt the exercises. If you have difficulty with an exercise, move on and return later to make another attempt. The chapter begins with a review of some material from linear algebra in section 2.1. This section assumes familiarity with elementary linear algebra, but introduces the notation used by physicists to describe quantum mechanics, which is different to that used in most instructions on linear algebra. Section 2.2 describes the basic postulates of all quantum mechanics. Upon completion of the section, you will have understood all of the fundamental principles to quantum mechanics. This section contains numerous simple exercises designed to help consolidate your grasp of this material. The remaining sections of the chapter and this book elucidate upon this material without introducing fundamentally new physical principles. Section 2.3 explains superdense coding, a surprising and illuminating example of quantum information processing which combines many of the postulates of quantum mechanics in a simple setting. Section 2.4 and 2.5 develop powerful mathematical tools, the density operator, purifications, and the Schmidt decomposition, which are especially useful in the study of quantum computation and quantum information. Understanding these tools will also help you consolidate your understanding of elementary quantum mechanics. Finally, section 2.6 examines the question of how quantum mechanics goes beyond the usual classical understanding of the way the world works. 2.1 Linear Algebra. This book is written as much to disturb and annoy as to instruct. The first line of About Vectors by Banschen Hofmann. Life is complex. It has both real and imaginary parts. Anonymous. Linear algebra is the study of vector spaces and of linear operations on those vector spaces. A good understanding of quantum mechanics is based upon a solid grasp of elementary linear algebra. In this section, we review some basic concepts from linear algebra and describe the standard notations which are used for these concepts in the study of quantum mechanics. These notations are summarized in Figure 2.1 on page 62, with the quantum notation in the left column and the linear algebraic description in the right column. You may like to glance at the table and see how many of the concepts in the right column you recognize. In our opinion, the chief obstacle to the assimilation of the postulates of quantum mechanics is not the postulates themselves, but rather the large body of linear algebraic notations required to understand them, coupled with the unusual direct notation adopted by physicists for quantum mechanics. It can appear, falsely, quite fearsome. For these reasons, we advise the reader not familiar with quantum mechanics to quickly read through the material which follows, pausing mainly to concentrate on understanding the absolute basics of the notation being used, then proceed to a careful study of the main topic of the chapter, the postulates of quantum mechanics, returning to study the necessary linear algebraic notations and notations in more depth as required. linear algebraic notions and notations in more depth as required. The basic objects of linear algebra are vector spaces. The vector space of most interest to us is C to the n, the space of all n tuples of complex numbers z1 to zn. The elements of a vector space are called vectors, and we will sometimes use the column matrix notation as shown in equation 2.1. To indicate a vector, there is an additional operation defined which takes pairs of vectors to other vectors. In Cn, the addition operation for vectors is defined by equation 2.2, where the addition operator on the right are just ordinary additions of the complex numbers. Furthermore, in a vector space there is a multiplication by scalar operation. In C to the n, this operation is defined by equation 2.3. Where z is a scalar, that is, a complex number, and the multiplications on the right are ordinary multiplications of complex numbers. Physicists sometimes refer to complex numbers as C numbers. Quantum mechanics is our main motivation for studying linear algebra, so we will use the standard notation of quantum mechanics for linear algebraic concepts. The standard quantum mechanical notation for a vector in a vector space is the following, as shown in equation 2.4. Psi is a label for the vector. Any label is valid, although we prefer to use simple labels like psi and phi. The ket dot notation is used to indicate that the object is a vector. The entire object psi is sometimes called a ket. Ket psi is sometimes called a ket, although we won't use that terminology often. A vector space also contains a special zero vector, which we denote by 0. It satisfies the property that for any vector ket v plus 0 is equal to ket v. Note that we do not use the ket notation for the zero vector. It is the only exception we shall make. The reason for making the exception is because it's conventional to use the obvious notation for the zero vector, ket 0, to mean something else entirely. The scalar multiplication operation is such that z0 equals 0 for any complex number z. For convenience, we use the notation z1 to zn to denote column matrix with entries z1 to zn. In Cn, the zero element is 0 to 0. A vector subspace of vector space V is a subset W of V, such that W is also a vector space. That is, W must be closed under scalar multiplications and addition. 2.1.1 Bases and linear independence. A spanning set for a vector space is a set of vectors, ket v1 to ket vn, such that any vector v in the vector space can be written as a linear combination. A linear combination ket v is equal to the sum with regard to I of ai ket vi of vectors. In that set, for example, a spanning set of the vector space C2 is the set shown in equation 2.5, since any vector shown in equation 2.6 in C2 can be written as a linear combination ket v equals a1 ket v1 plus a2 ket v2 of the vectors ket v1 and ket v2. We say that the vectors ket v1 and ket v2 span the entire vector space C2. Generally, a vector space may have many different spanning sets. A second spanning set for the vector space C2 is the set shown in equation 2.7. Since an arbitrary vector v can be written as a linear combination of ket v1 and ket v2, as shown in equation 2.8, a set of non-zero vectors ket v1 to ket vn are linearly dependent if there exists a set of complex numbers a1 to an with ai not equal to 0 for at least one value of I, such that equation 2.9 is satisfied. A set of vectors is linearly independent if it is not linearly dependent. It can be shown that any two sets of linearly independent vectors which span a vector space V contains the same number of elements. We call such a set a basis for V. Furthermore, such a basis set always exists. The number of elements in the basis is defined to be the dimension of V. In this book, we will only be interested in finite dimensional vector spaces. There are many interesting and often difficult questions associated with infinite dimensional vector spaces. We don't need to worry about these questions. Exercise 2.1, linear dependence example. Show that minus 1, 1, 1, 1, 2, and 2, 1 are linearly independent. Linearly dependent. 2.1.2, linear operators and matrices. A linear operator between vector spaces V and W is defined to be any function A that is defined as V going to W, which is linear in its inputs, as shown in equation 2.10. Usually, we just write A ket V to denote A times ket V. When we say that a linear operator A is defined on a vector space V, we mean that A is a linear operator from V to V. An important linear operator on any vector space V is the identity operator, I of V, defined by the equation IV ket V is equal to V for all vectors V. There are no chance of confusion arises as we drop the subscript V and just write I to denote the identity operator. Another important linear operator is the zero operator, which we denote 0. The zero operator maps all vectors to the 0 vector. 0 ket V is equal to 0. It is clear from 2.10 that once the action of a linear operator A on a basis is specified, the action of A is completely determined on all inputs. Suppose V, W, and X are vector spaces, and A is defined as V mapped to W, and B is defined as W mapped to X, are linear operators. Then we use the notation BA to denote the composition of B with A, defined by B times A times ket V is equal to B times A ket V. Once again, we write BA ket V as an abbreviation for the previous B times A times ket V. The most convenient way to understand linear operators is in terms of their matrix representations. In fact, the linear operator and matrix viewpoints turn out to be completely equivalent. The matrix viewpoint may be more familiar to you. However, to see the connection, it helps to first understand that an m by n complex matrix A with entries A, I, J is in fact a linear operator sending vectors in the vector space Cn to the vector space Cm under matrix multiplication of the matrix A by a vector in Cn. More precisely, the claim that the matrix A is a linear operator just means that equation 2.11 is satisfied. It is true that an equation where the operation is matrix multiplication of A by column vectors, clearly this is true. We've seen that the matrices can be regarded as linear operators. Can linear operators be given a matrix representation? In fact, they can, as we now explain. This equivalence between the two viewpoints justifies our interchanging terms for matrix theory and operator theory throughout the book. Suppose A is defined V to W and its linear operator between vector spaces V and W. Suppose ket V1 to ket Vm is a basis for V, and ket W1 to ket Wn is a basis for W. Then for each j in the range 1 to m, there exists complex numbers a1j through a nj, such that equation 2.12 is satisfied. The matrix whose entries are the values A, I, J is said to form a matrix representation of the operator A. This matrix representation of A is completely equivalent to the operator A, and we will use the matrix representation and abstract operator viewpoints interchangeably. Note that to make the connection between matrices and linear operators, we must specify a set of input and output basis states with the input and output vector spaces of the linear operator. Exercise 2.2, matrix representation example. Suppose V is a vector space with the basis vectors ket0 and ket1, and A is a linear operator from V to V such that A ket0 is equal to ket1, and A ket1 is equal to ket0. Give a matrix representation for A with respect to the input bases ket0, ket1, and the output bases ket0, ket1. Find input and output bases which give rise to a different matrix representation for A. Exercise 2.3, matrix representation for operator products. Suppose A is a linear operator from vector space V to vector space W, and B is a linear operator from vector space W to vector space X. Let VI, ket WJ, and ket XK be bases for the vector spaces V, W, and X, respectively. Show that the matrix representation for the linear transformation BA is the matrix product of the matrix representation for B and A with respect to the appropriate basis. Exercise 2.4. Matrix representation for identity. Show that the identity operator on a vector space V has matrix representation which is 1 along the diagonal and 0 everywhere else, if the matrix representation is taken with respect to the same input and output bases. This matrix is known as the identity matrix. 2.1.3 The Pauli matrices. 4 extremely useful matrices, which we shall often have the occasion to use, are the Pauli matrices. These are 2x2 matrices which go by a variety of notations. The matrices and their corresponding notations are depicted in figure 2.2. The Pauli matrices are so useful in the study of quantum computation and information that we encourage you to memorize them by working through in detail the many examples and exercises based upon them in subsequent sections. Two point 1.4 Inner products. An inner product is a function which takes as input two vectors ket v and ket w from a vector space and produces a complex number as output. For the time being, it will be convenient to write the inner product of ket v and ket w as v, w. This is not the standard quantum mechanical notation. For pedagogical clarity, the dot comma dot notation will be useful occasionally in this chapter. The standard quantum mechanical notation for the inner product ket v, ket w is bra v ket w, where ket v and ket w are vectors in the inner product space, and the notation bra v is used for the dual vector to the vector ket v. The dual is a linear operator from the inner product space V to the complex numbers C defined by the following equations. We will see shortly that the matrix representation of dual vectors is just a row vector. A function dot comma dot from v to C is an inner product if it satisfies the requirements that 1. Dot comma dot is linear in the second argument, as shown in equation 2.13. 2. Ket v, ket w is equal to ket w, ket v complex conjugate. 3. Ket v comma cat v is greater than or equal to 0 with equality if and only if cat v is equal to 0. For example, Cn has an inner product defined by equation 2.14. We call the vector space equipped with an inner product an inner product space. Exercise 2.5. Verify that dot comma dot just defined is an inner product on Cn. Exercise 2.6. Show that any inner product dot comma dot is conjugate linear in the first argument, as shown in 2.15, equation 2.15. Discussions of quantum mechanics often refer to Hilbert space. In the finite dimensional complex vector spaces that come up in quantum computation and quantum information, a Hilbert space is exactly the same thing as an inner product space. From now on, we use the two terms interchangeably, preferring the term Hilbert space. In infinite dimensions, Hilbert spaces satisfy the additional technical restrictions above and beyond the inner product spaces, which we will not need to worry about. Vectors ket w and ket v are orthogonal if their inner product is 0. For example, ket w is defined as 1, 0, and ket v as 0, 1 are orthogonal with respect to their inner product defined by equation 2.14. We define the norm of vector ket v by equation 2.16. A unit vector is a vector ket v such that the norm is equal to 1. We also say that ket v is normalized if the norm is equal to 1. It is conventional to talk of normalizing a vector by dividing by its norm. Thus, ket v divided by its norm is the normalized form of ket v. For any non-zero vector ket v, a set ket I of vectors with index I is orthonormal if each vector is a unit vector and distinct vectors in the set are orthogonal. That is, bra I ket j is equal to delta ij, where I and j are both chosen from the index set. Kronecker delta ij. Exercise 2.7. Just delta ij. Exercise 2.7. Verify that ket w is equal to 1, 1 and ket v is equal to 1 minus 1 are orthogonal. What are the normalized forms of these vectors? Suppose ket w1 to ket wd is a basis set for some vector space V with an inner product. There is a useful method, the Gram-Schmidt procedure, which we can use to produce an orthonormal basis set ket v1 to ket vd for the vector space V. Define ket v1 as ket w1 divided by the norm of ket w1, and for 1 is less than or equal to k, which is less than or equal to d minus 1, define ket vk plus 1 inductively by the equation 2.17. It is not difficult to verify that the vectors ket v1 to ket vd form an orthonormal set which is also a basis of V. Thus, any finite dimensional vector space of dimension d has an orthonormal basis ket v1 and ket vd. Exercise 2.8. Prove that the Gram-Schmidt procedure produces an orthonormal basis for V. From now on, when we speak of a matrix representation for a linear operator, we mean a matrix representation with respect to orthonormal input and output bases. We also use the convention that if the input and output spaces for a linear operator are the same, then the input and output bases are the same unless noted otherwise. With these conventions, the inner product on Hilbert space can be given a convenient matrix representation. Let ket W equal to the sum over I of Wi ket I, and ket V equal to the sum over J of Vj ket J. Be representations of vectors ket W and ket V with respect to some orthonormal basis I. Then, since bra I ket J is equal to delta Ij, equation 2.18 follows, and so does equation 2.19. That is, the inner product of the two vectors is equal to the vector inner product between two matrix representations of those vectors. Provided the representations are written with respect to the same orthonormal basis, we also see that the dual vector bra v has a nice interpretation as the row vector, whose components are complex conjugates of the corresponding components of the column vector representation of ket v. There is a useful way of representing linear operators which makes use of the inner product, known as the outer product representation. Suppose ket v is a vector in an inner product space V, and ket w is a vector in an inner product space W. Define ket w bra v to be a linear operator from V to W, whose action is defined by equation 2.20. This equation fits beautifully into our notational conventions, according to which the expression ket w bra v ket v prime could potentially have one of two meanings. We will use it to denote the result when the operator ket w bra v acts on v prime, ket v prime, and it has an existing interpretation as the result of multiplying ket w by the complex number bra v ket v prime. Our definitions are chosen so that these two potential meanings coincide. Indeed, we define the former in terms of the latter. We can take linear combinations of outer product operators ket w bra v in the obvious way. By definition, sum over I of ai wi ket wi bra vi is the linear operator which, when acting on ket v prime, produces the output sum over I ai ket wi bra vi ket v prime as output. The usefulness of the operator product notation can be discerned from an important result known as the completeness relation for orthonormal vectors. Let ket I be any orthonormal basis for the vector space V, so that an arbitrary vector ket V can be written ket V is equal to sum over I vi over vi ket I for some set of complex numbers vi. Note that bra I ket V is equal to vi, and therefore equation 2.12 follows. Since the last equation is true for all ket v, it follows that equation 2.2 is true. This equation is known as the completeness relation. One application of the completeness relation is to give a means for representing any operator in the outer product notation. Suppose that A is defined as V to W in a linear operator, ket vi is an orthonormal basis for V, and ket v wj is an orthonormal basis for W. Using the completeness relation twice, we obtain equation 2.23. Followed by equation 2.24 and equation 2.25. Which is the outer product representation for A. We also see from this equation that A has matrix elements bra Wj, A, ket Vi in the ith column and jth row with respect to the input basis, ket Vi and the output basis, ket Wj. The second application illustrating the usefulness of the completeness relation is the Cauchy-Schwarz inequality. This important result is discussed in box 2.1 on this page. Box 2.1, the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality is an important geometric fact about Hilbert spaces. It states that for any two vectors, ket v and ket w, the magnitude of bra v times bra ket w squared is less than or equal to the inner product of the two v and w multiplied. To see this, use the Graham-Schmidt procedure to construct an orthonormal basis I for the vector space such that the first member of the basis I is W over the norm of W. Use the completeness relation and dropping some non-negative terms gives equation 2.26 to 2.28 as required. A little thought shows that equality occurs if and only if ket v and ket w are linearly related. That is, ket v is equal to z ket w, or ket w is equal to z ket v for some scalar z. 2.1.5 Eigenvectors and Eigenvalues. An eigenvector of a linear operator A on a vector space is a non-zero vector ket v such that A ket v is equal to v ket v, where v is a complex number known as the eigenvalue of a corresponding eigenvalue of A corresponding to ket v. It will often be convenient to use the notation v both as a label for the eigenvector and to represent the eigenvalue. We assume that you are familiar with the elementary properties of eigenvalues and eigenvectors, in particular how to find them by the characteristic equation. The characteristic function is defined to be c of lambda, which is defined as determinant of A minus lambda I, where the det is a determinant function. For matrices, it can be shown that the characteristic function depends only upon the operator A and not on the specific matrix representation used for A. The solution for the characteristic equation, C lambda, is 0 equals 0. The solutions for the characteristic equation C lambda equals 0 are the eigenvalues of the operator A. By the fundamental theorem of algebra, every polynomial has at least one complex root, so every operator A has at least one eigenvalue and a corresponding eigenvector. The eigenspace corresponding to an eigenvalue V is the set of vectors which have eigenvalue V. It is a vector subspace of the vector space on which A acts. A diagonal representation for an operator A on a vector space V is a representation A is equal to sum over I lambda I ket I bra I, where the vectors ket I form an orthonormal set of eigenvectors for A with corresponding eigenvalues lambda I. An operator is said to be diagonalizable if it has a diagonal representation. In the next section, we will find a simple set of necessary and sufficient conditions for an operator on a Hilbert space to be diagonalizable. As an example of a diagonal representation, note that the Pauli matrix Z may be written as ket 0 bra 0 minus ket 1 bra 1, as in equation 2.29. Where the matrix representation is with respect to orthonormal vectors ket 0 and ket 1, respectively. Diagonal representations are sometimes also known as orthonormal decompositions. When an eigenspace is more than one-dimensional, we say that it is degenerate. For example, the matrix A, defined by equation 2.30, has a two-dimensional eigenspace corresponding to the eigenvalue 2. The eigenvectors 1, 0, 0 and 1, 0, 1, 0 are said to be degenerate because they are linearly independent eigenvectors of A with the same eigenvalue. Two point 1.6 Joints and Hermitian operators. Suppose A is any linear operator on a Hilbert space, V. It turns out that there exists a unique linear operator, A dagger, on V such that for all vectors ket V, ket W as a part of V, as shown in equation 2.3.2, this linear operator is known as the adjoint or Hermitian conjugate of the operator A. From the definition, it is easy to see that the adjoint of A multiplied by B is the adjoint of B multiplied by the adjoint of A. By convention, if ket V is a vector, then we define the adjoint of V as the adjoint of ket V as bra V. With this definition, it's not difficult to see that A ket V adjoint is equal to bra A adjoint. In a matrix representation of an operator A, the action of the Hermitian conjugation operation is to take the matrix of A to the conjugate transpose matrix. So A dagger is defined as A complex conjugate transposed, where the star indicates complex conjugation and T indicates the transpose operation. For example, we have the equation 2.3.4. An operator A whose adjoint is A is known as the Hermitian or self-adjoint operator. An important class of Hermitian operators is the projectors. Suppose W is a k-dimensional vector subspace of the d-dimensional vector space V. Using the Graham-Schmidt procedure, it is possible to construct an orthonormal basis ket 1 to ket D for V such that ket 1 to ket K is an orthonormal basis for W. By definition, equation 2.35. Is the projector onto the subspace W. It is easy to check that this definition is independent of the orthonormal basis ket1 to ket k used for W. From the definition, it can be shown that ket v, bra v, is Hermitian for any vector ket v, so P is Hermitian. P dagger is equal to P. We will often refer to the vector space P as shorthand for the vector space onto which P is a projector. The orthogonal component of P is the operator Q, defined as I minus P. It is easy to see that Q is a projector onto the vector space spanned by k plus 1 to D, which we also refer to as the orthogonal complement of P and may be denoted by Q. An operator A is said to be normal if A dagger is equal to A dagger A. Clearly, an operator which is Hermitian is also normal. There is a remarkable representation theorem for normal operators known as the spectral decomposition, which states that an operator is a normal operator if and only if it is diagonalizable. This result is proven in box 2.2 on page 72, which you should read closely. A matrix U is said to be unitary if U dagger U is identity. Similarly, an operator U is unitary if U dagger U is identity. It is easily checked that an operator is unitary if and only if each of its matrix representations is unitary. A unitary operator also satisfies U dagger equals identity, and therefore U is normal and has a spectral decomposition. Geometrically, unitary operators are important because they preserve inner products between vectors. To see this, let ket v and ket w be any two vectors, and the inner product of U ket v and U ket w is the same as the inner product of ket v and ket w. As shown in equation 2.36, this result suggests that the following elegant outer product representation of any unitary U. Let ket vi be any orthonormal basis set. Define ket wi as uvi, so that ket wi is also an orthonormal basis set. Since unitary operators preserve inner products, note that U is a sum over I of ket wi bra vi. Conversely, if ket vi and ket wi are any two orthonormal bases, then it is easily checked that the operator U, defined by its previous definition, is a unitary operator. A special subclass of Hermitian operators is extremely important. This is the positive operators. A positive operator A is defined to be an operator such that for any vector ket v inner product A ket v is a real non-negative number. If the inner product ket v A ket v is strictly greater than 0 for all ket v not equal to 0, then we say that A is a positive definite. In exercise 2.24 on this page, you will show that any positive operators are automatically Hermitian, and therefore by the spectral decomposition has diagonal representation with non-negative eigenvalues lambda. 2.1.7 Tensor products. The tensor product is a way of putting vector spaces together to form larger vector spaces. This construction is crucial to understanding the quantum mechanics of multi-particle systems. The following discussion is a little abstract and may be difficult to follow if you're not already familiar with the tensor product, so feel free to skip ahead now and revisit later when you come to the discussion of tensor product in quantum mechanics. Suppose V and W are vector spaces of dimension m and n respectively. For convenience, we also suppose that V and W are Hilbert spaces. Then V tensor W is an n by m dimensional vector space. The elements of V tensor W The elements of V tensor W are linear combinations of tensor products ket V tensor ket W of elements ket V of V and ket W of W. In particular, if ket I and ket J are orthonormal bases of the vector spaces V and W, then ket I tensor ket J is a basis for V ket W. We often use the abbreviated notations ket V ket W, ket V, W, or even ket VW for the tensor product. For the tensor product, ket V tensor ket W. For example, if V is a two-dimensional vector space with basis vectors ket 0 and ket 1, then ket 0 tensor ket 0 plus ket 1 tensor ket 1 is an element of V tensor V. By definition, the tensor product satisfies the following basic properties. 1. For an arbitrary scalar z, an element ket V of V and ket W of W, equation 2.4.2 is true. For arbitrary ket V1 and ket V2 in V and ket W in W, equation 2.4.3 is true. For arbitrary V and V and ket W1 and ket W2 in W, equation 2.4.4 is true. What sort of linear operators act on the space V tensor W? Suppose ket V and ket W are vectors V and W, and A and B are linear operators on V and W respectively. Then we can define a linear operator A tensor B on V tensor W by the equation 2.45. By definition of A tensor B is then extended to all elements of V tensor W in the natural way to ensure linearity of A tensor B, that is, equation 2.46 is satisfied. It can be shown that the function so defined is a well-defined inner product. From this inner product, the inner product space V tensor W inherits the other structure we are familiar with, such as notions of an adjoint, unitary, normality, and hermiticity. All this discussion is rather abstract. It can be made much more concrete by moving to a convenient matrix representation shown as the Kronecker product. Suppose A is a m by n matrix and B is a p by q matrix. Then we have the matrix representation shown 2.50, equation 2.50. In this representation, terms like A11B denote p by q submatrices whose entries are proportional to B with overall proportionality constant A11, for example, the tensor product of the vectors 1, 2 and 2, 3 is the vector shown in equation 2.51. The tensor product of the Pauli matrices x and y is equation 2.51, 2.52. Finally, we mentioned the useful notation of psi ket to the power of tensor k, which means psi ket is tensored with k itself, which means kep psi is tensored with itself k times. For example, kep psi tensored to the power of tensor 2 is equal to kep psi tensor kep psi. An analogous notation is also used for operators on tensor product spaces. Sure, explicitly. 2.1.8 Operator functions. There are many important functions which can be defined for operators and matrices. Generally speaking, given a function f from the complex numbers to the complex numbers, it is possible to define a corresponding matrix function on normal matrices for some subclass such as the Hermitian matrices by the following construction. Let A equal the sum over A of A ket A bra A be a spectral decomposition for a normal operator A. Define f of A as the sum of over A of f of A ket A bra A. A little thought shows that f of A is uniquely defined. This procedure can be used, for example, to define the square root of a positive operator, the logarithm of a positive definite operator, or the exponential of a normal operator, as an example, equation 2.56. Since Z has eigenvectors get 0 and get 1, I guess. Another important matrix function is the trace of a matrix. The trace of A is defined to be the sum of its diagonal elements, as shown in equation 2.59. The trace is easily seen to be cyclic. Trace A of B is equal to trace B of A, and linear. Trace A plus B is trace A plus trace B. Trace ZA is equal to Z trace A, where A and B are arbitrary matrices and Z is a complex number. Furthermore, from the cyclic property, it follows that the trace of a matrix is invariant under the unitary similarity transformation A, that is U A U dagger, as trace UA U dagger is equal to trace U dagger U A, which equals to trace A. In light of this result, it makes sense to define the trace of an operator A to be the trace of any matrix representation of A. The invariance of the trace under unitary similarity transformations ensures that the trace of an operator is well defined. As an example of the trace, suppose kep psi is a unit vector and A is an arbitrary operator. To evaluate trace of A ket psi bra psi, use the Gram-Schmidt procedure to extend psi kep psi to an orthonormal basis I, which includes psi as the first element, and then we have equation 2.60 and 2.61. This result, that trace of A kep psi and bra psi is equal to bra psi A ket psi, is extremely useful in evaluating the trace of an operator. 2.1.9 The commutator and anti-commutator. The commutator between two operators, A and B, is defined to be as shown in equation 2.66. If the commutator A, comma B is equal to 0, that is, A times B is equal to B times A, then we say A commutes with B. Similarly, the anti-commutator of two operators A and B is defined by equation 2.67. We say that A anti-commutes with B if A anti-commutator B is 0. It turns out that many important properties of pairs of operators can be deduced from their commutator and anti-commutator. Perhaps the most useful relation is the following connection between the commutator and the property of being able to simultaneously diagonalize Hermitian operators A and B. That is, write A is equal to the sum over I of AI, ket I, bra I, and B is equal to the sum over I of BI, ket I, bra I, where ket I is some common orthonormal set of eigenvectors for A and B. Theorem 2.2 Simultaneous diagonalization theorem. Suppose A and B are Hermitian operators, then commutator AB is equal to 0 if and only if there exists an orthonormal basis such that both A and B are diagonal with respect to that basis. We say that A and B are simultaneously diagonalizable in this case. This result connects to the commutator of two operators, which is often easy to compute, to the property of being simultaneously diagonalizable, which is a priori rather difficult to determine. As an example, consider that equation 2.68 to 2.70. So x and y do not commute. X and y Pauli matrices do not commute. You have already shown in exercise 2.11 that x and y do not have common eigenvectors, as we expect from the simultaneous diagonalization theorem. Proof: you can and should easily verify that if A and B are diagonal in the same orthonormal basis, then A commutator B equals 0. To show the converse, let A, J be an orthonormal basis for the eigenspace VA of A with eigenvalue A. The index J is used to label possible degeneracies. Note that equation 2.17. And therefore, P of A, J is an element of the eigenspace VA. Let PA denote the projector onto the space VA and define B as PA. It is easy to see that the restriction of BA to the space VA is Hermitian on VA, and therefore has spectral decomposition in terms of A, B, K, where the indices A and B label the eigenvalues of A and BA, and K is an extra index to allow for the possibility of a degenerate BA. Note that BA, ket A, B, K, is an element of VA, so B ket A, B, K is equal to PA, B, ket, A, B, A. Moreover, we have PA, ket A, B, A is equal to ket A, B, A. So equation 2.72 is satisfied. It follows that A, B, K is an eigenvector of B with eigenvalue B, and therefore ket A, B, K is an orthonormal set of eigenvectors of both A and B, spanning the entire vector space on which A and B are defined. That is, A and B are simultaneously diagonalizable. 2.1.10 The polar and single value decompositions. The polar and singular value decompositions are useful ways of breaking linear operations up into simpler parts. In particular, these decompositions allow us to break general linear operators up into products of unitary operators and positive operators. While we didn't understand the structure of general linear algebra operators terribly well, we do understand unitary operators and positive operators in quite some detail. The polar and singular value decompositions allow us to apply this understanding to better understand the general linear operators. Theorem 2.3. Polar decomposition. Let A be a linear operator on a vector space V, where there exists unitary U and positive operators J and K, such that A equals Uj and equals Ku as shown in equation 2.79, where the unique positive operators J and K satisfying these equations are defined by J is equal to the square root of A dagger A and K is equal to the square root of A dagger. Moreover, if A is invertible, then U is unique. We call the expression A equals Uj the left polar decomposition of A, and A equals Ku the right polar decomposition of A. For both expressions with context indicating which is meant. Proof. J is equal to root A dagger A is a positive operator, so it can be given a spectral decomposition. That is, J is equal to sum over I, lambda I, ket I, bra I, where the eigenvalues lambda I are greater than or equal to 0. Define ket psi I as A ket I. From the definition, we see that bra psi I ket psi I is equal to lambda I squared. Consider for now only those I for which lambda I is not equal to 0. For those I, define ket ei, which is equal to ket psi I over lambda I, so that ket ei are normalized. Moreover, they are orthogonal, since if I is not equal to j, then e bra I ket ej is equal to bra I a dagger a ket j over lambda I lambda j, which is equal to ket I j squared bra j over lambda I lambda j equals 0. We have been considering I such that lambda I is not equal to 0. Now use the Graham-Schmidt procedure to extend the orthonormal set ket ei so it forms the orthonormal basis, which we also label ket ei. Define a unitary operator U is equal to the sum over I ket ei bra I. When lambda I is not equal to 0, we have Uji, which equals to lambda I ket ei equal to psi I equal to a ket I. When lambda I is equal to 0, we have Uj ket I is equal to 0 is equal to psi I. We have proved that the action of A and Uj agree on the basis of I, and thus that A equals Uj. Sure, J is unique, since multiplying A is equal to Uj on the left, and by the adjoint equation, A dagger equals to J U dagger gives J squared is equal to A dagger A, from which we see that J is equal to root A dagger A. Uniquely, a little thought shows that if A is invertible, then so is J. So U is uniquely determined by the equation U is equal to AJ minus 1. The proof of the right polar decomposition follows, since A is equal to Uj is equal to uj u dagger u equal to ku, where k is uj u dagger is a positive operator. Since a dagger is equal to k u dagger k, which equals k squared, we must have k equals to square root of a dagger as claimed. The singular value decomposition combines the polar decomposition as the spectral theorem. Corollary 2.4. Singular value decomposition. Let A be a square matrix, then there exists unitary matrices U and V and diagonal matrix D with non-negative entries such that A equals U dV, as shown in equation 2.80. The diagonal elements of D are called the singular values of A. I'm not reading that proof. I don't need proof. I need sleep. 2.2. The postulates of quantum mechanics. All understanding begins with our not accepting the world as it appears. Alan Kay. The most incomprehensible thing about the world is that it is comprehensible. Albert Einstein. Quantum mechanics is a mathematical framework for the development of physical theoretic theories. On its own, quantum mechanics doesn't tell you the laws of physical systems. On its own, quantum mechanics doesn't tell you what laws of physical systems must obey, but it does provide a mathematical and conceptual framework for the development of such laws. In the next few sections, we give a complete description of the basic postulates of quantum mechanics. The postulates of quantum mechanics were derived after a long process of trial and mostly error, which involved a considerable amount of guessing and fumbling by the originators of the theory. Don't be surprised if the motivation for the postulates is not always clear. Even to experts, the basic postulates of quantum mechanics appear surprising. What you should expect to gain in the next few sections is a good working grasp of the postulates, how to apply them, and when. 2.2.1 State space. The first postulate of quantum mechanics sets up the arena in which quantum mechanics takes place. The arena is our familiar friend from linear algebra, Hilbert space. Postulate 1. Associated to any isolated physical system is a complex vector space with inner product, that is, a Hilbert space, known as the state space of the system. The system is completely described by its state vector, which is a unit vector in the system's state space. Quantum mechanics does not tell us, for a given physical system, what the state space of that system is, nor does it tell us that the state vector of the system is. Figuring that out for a specific system is a difficult problem for which physicists have developed many intricate and beautiful rules. For example, there is the wonderful theory of quantum electrodynamics, often known as QED, which describes how atoms and light interact. One aspect of QED is that it tells us what state space to use to give quantum descriptions of atoms and light. We won't be much concerned with the intricacies of theories like QED, even insofar as they apply to physical realizations in Chapter 7, as we are mostly interested in the general framework provided by quantum mechanics. For our purposes, it will be sufficient to make some very simple and reasonable assumptions about the state spaces of the systems we are interested in, and stick with those assumptions. The simplest quantum mechanical system, and the system which we will most concerned with, is the qubit. A qubit has a two-dimensional state space. Suppose ket0 and ket1 form an orthonormal basis for that state space. Then an arbitrary state vector in the state space can be written as ket psi is equal to a ket0 plus b ket1, as in equation 2.82. State space can be written as equation 2.82, where a and b are complex numbers. Where a and b are complex numbers. The condition that ket psi be a unit vector is therefore equivalent to the magnitude of a squared plus magnitude of b squared equals 1. The condition bro psi ket psi equals 1 is often known as the normalization condition for state vectors. We will take the qubit as our fundamental quantum mechanical system. Later, in Chapter 7, we will see that there are real physical systems which may be described in terms of qubits. For now, though, it is sufficient to think of qubits in abstract terms. Without reference to a specific realization, our discussion of qubits will always be referred to some orthonormal set of basis vectors, ket0 and ket1, which should be thought of as being fixed in advance. Intuitively, the states ket0 and ket1 are analogous to the two values 0 and 1, which a bit may take. The way a qubit differs from a bit is that superpositions of these two states of the form a ket0 and b ket1 can also exist, in which it is not possible to say that the qubit is definitely in the state 0 or definitely in the state 1. We conclude with some useful terminology which is often used in connection with the description of quantum states. We say that any linear combination, sum over I, alpha I, psi, ket psi I, is a superposition of the states ket psi I with an amplitude alpha I for the states ket psi I. So, for example, the state shown in equation 2.83 is a superposition of the states ket0 and ket1 with amplitudes 1 over root 2 for the state 0 and amplitude minus 1 over root 2 for the state 1. 2.2.2 Evolution. How does the state ket psi of a quantum mechanical system change with time? The following postulate gives us a prescription for the description of such state changes. Postulate 2. The evolution of a closed quantum system is described by a unitary transformation, that is, the state ket psi of a system at time t1 is related to the state ket psi prime of the system at time t2 by a unitary operator u, which depends only on the times t1 and t2. As shown in equation 2.84. Just as quantum mechanics does not tell us the state space or quantum state of a particular quantum system, it does not tell us which unitary operators U describe real-world quantum dynamics. Quantum mechanics merely assures us that the evolution of any closed quantum system may be described in such a way. An obvious question to ask is, what unitary operators are natural to consider? In the case of single qubits, it turns out that any unitary operator at all can be realized in realistic systems. Let's look at a few examples of unitary operators on a single qubit which are important in quantum computation and quantum information. We have already seen several examples of such unitary operators, the Pauli matrices defined in section 2.1.3 and the quantum gates described in chapter 1. As remarked in section 1.3.1, the X matrix is often known as the quantum NOT gate by analogy to the classical NOT gate. The X and the Z Pauli matrices are also sometimes referred to as the bit flip and phase flip matrices. The X matrix takes ket 0 to ket 1 and ket 1 to ket 0, thus earning the name bit flip, and the Z matrix leaves ket 0 invariant and takes ket 1 to ket minus 1, with an extra factor of minus 1 added, known as the phase factor, thus justifying the term phase flip. We will not use the term phase flip for Z very often, since it is easily confused with the phase gate to be defined in chapter 4. Section 2.2.7 contains more discussion on the many uses of the term phase. Another interesting unitary operator is the Hadamard gate, which we denote H. This has the action H ket 0 as ket 0 plus ket 1 over root 2, or ket plus, and H ket 1 is ket 0 minus ket 1 over root 2, or ket minus, and corresponding matrix representation as shown in equation 2.85. Postulate 2 requires that the system being described be closed. That is, it is not interacting in any way with other systems. In reality, of course, all systems, except the universe as a whole, interact at least somewhat with other systems. Nevertheless, there are interactive systems which can be described to a good approximation as being closed, and which are described by unitary evolution to some good approximation. Furthermore, at least in principle, every open system can be described as a part of a larger closed system, the universe, which is undergoing unitary evolution. Later, we'll introduce more tools which allow us to describe systems which are not closed, but for now we'll continue with the description of the evolution of closed systems. Postulate 2 describes how the quantum states of a closed quantum system at two different times are related. A more refined version of this postulate can be given, which describes the evolution of a quantum system in continuous time. From this more refined postulate, we will recover postulate 2. Before we state the revised postulate, it is worth pointing out two things. First, a notational remark. The operator H appearing in the following discussion is not the same as the Hadamard operator, which we just introduced. Second, the following postulate makes use of the apparatus of different equations. Readers with little background in the study of differential equations should be reassured that they will not be necessary for much of the book, with the exception of parts of Chapter 7 on real physical implementations of quantum information processing. Postulate 2'. The time evolution of a state of a closed quantum system is described by the Schrödinger equation, given as equation 2.86. In this equation, h bar is a physical constant known as Planck's constant, whose value must be experimentally determined. The exact value is not important to us. In practice, it's common to absorb the factor h bar into h, effectively setting h bar equal to 1. H is a fixed Hermitian operator known as the Hamiltonian of the closed system. If we know the Hamiltonian of a system, then, together with the knowledge of h bar, we understand its dynamics completely, at least in principle. In general, figuring out the Hamiltonian needed to describe a practical physical system is a very difficult problem, with much of 20th century physics has been concerned with this problem, which requires substantial input from experiment in order to be answered. From our point of view, this is a problem of detail to be addressed by physical theories built within the framework of quantum mechanics. What Hamilton what Hamiltonian do we need to describe atoms in such and such configuration? And it's not a question that needs to be addressed by the theory of quantum mechanics itself. Most of the time, in our discussion of quantum computation and quantum information, we won't need to discuss Hamiltonians, and when we do, we simply just posit that some matrix is the Hamiltonian as a starting point, and proceed from there without attempting to justify the use of the Hamiltonian, because the Hamiltonian is a Hermitian operator. It has a spectral decomposition, as shown in equation 2.87, with the eigenvalues E and corresponding normalized eigenvectors ket E. The states ket E are conventionally referred to as energy eigenstates, or sometimes as stationary states, and E is the energy of the state ket E. The lowest energy is known as the ground state of the system, and the corresponding energy eigenstate, or eigenspace, is known as the ground state. The reason the states ket E are sometimes known as stationary states is because their only change in time is to acquire an overall numerical factor, as shown in 2.88. As an example, suppose a single qubit has Hamiltonian h equals h bar omega x, as shown in equation 2.89. In this equation, omega is a parameter that, in practice, needs to be experimentally determined. We won't worry about that parameter overly much here. The point is to give you a feel for the sort of Hamiltonians that are sometimes written down on the study of quantum computation and quantum information. The energy eigenstates of this Hamiltonian are obviously the same as the eigenstates of X, namely ket plus and ket minus, with corresponding energies h bar omega and minus h bar omega. The ground state is therefore ket minus, and the ground state energy is minus h bar omega. What is the connection between the Hamiltonian picture of dynamics, postulate 2', and the unitary operator picture, postulate 2? The answer is provided by writing down the solution to Schrödinger's equation, which is easily verified to be equation 2.90, where we define equation 2.91. You will show in the exercises that this operator is unitary, and furthermore that any unitary operator U can be realized in the form U equals exponential yk for some Hermitian operator k. There is therefore a one-to-one correspondence between the discrete time description of dynamics using unitary operators and the continuous time description using Hamiltonians. For most of the book, we use the unitary formulation of quantum dynamics. In quantum computation and quantum information, we often speak of applying a unitary operator to a particular quantum system. For example, In the context of quantum circuits, we may speak of applying the unitary gate X to a single qubit. Doesn't this contradict what we said earlier about unitary operators describing the evolution of a closed quantum system? After all, if we are applying a unitary operator, then what implies that there is an external we who is interacting with the quantum system, and the system is not closed. An example of this occurs when the laser is focused on an atom. After a lot of thought and hard work, it is possible to write down a Hamiltonian describing the total atom laser system. The interesting thing is that when we write down the Hamiltonian for the atom laser system and consider the effect on the atom alone, the behavior of the state vector on the atom turns out to be almost not quite perfectly described by another Hamiltonian, the atomic Hamiltonian. The atomic Hamiltonian contains terms related to laser intensity and other parameters of the laser, which we can vary at will. It is as if the evolution of the atom were being described by the Hamiltonian, which we can vary at will, despite the atom not being a closed system. More generally, for many systems like this, it turns out to be possible to write down a time-varying Hamiltonian for a quantum system, in which the Hamiltonian for the system is not a constant, but varies according to some parameters which are under an experimentalist control, and which may be changed during the course of an experiment. The system is not therefore closed, but it does evolve according to Schrödinger's equation, with a time-varying Hamiltonian to some good approximation. The upshot is that to begin, we will often describe the evolution of quantum systems, even systems which aren't closed, using unitary operators. The main exception to this quantum measurement will be described in the next section. Later on, we will investigate in more detail possible derivations from unitary evolutions due to the interaction with other systems, and understand more precisely the dynamics of realistic quantum systems. 2.2.3 Quantum measurement. We postulated that closed quantum systems evolve according to unitary evolution. The evolution of systems which don't interact with the rest of the world is all very well, but there must also be times when the experimentalist and their experimental equipment going on inside their experimental equipment, an external physical system, in other words, observes the system to find out what is going on inside the system, an interaction which makes the system no longer closed, and thus not necessarily subject to unitary evolution. To explain what happens when this is done, we introduce postulate 3, which provides a means for describing the effect of measurement on quantum systems. Postulate 3. Quantum measurements are described by a collection, set MM, of measurement operators. These are operators acting on the state space of the system being measured. The index M refers to the measurement outcomes that may occur in the experiment. If the state of the quantum system is kept psi immediately before the measurement, then the probability that results M occurs is given by equation 2.92. And the state of the system after the measurement is equation 2.93. The measurement operators satisfy the completeness equation 2.94, and the completeness equation expresses the fact that probabilities sum to 1, 2.95. This equation being satisfied for all kept psi is equivalent to the completeness equation. However, the completeness equation is much easier to check directly, so that's why it appears in the statement of the postulate. A simple but important example of the measurement is the measurement of a qubit and the computational basis. This is a measurement on a single qubit with two outcomes defined by the two measurement operators. M0 is equal to ket 0 bra 0, and 1 is equal to ket 1 bra 1. Observe that each measurement operator is Hermitian, and that m squared 0 and m0 m1 squared equals m1. Thus the completeness relation is obeyed. Unity is equal to m0 dagger m0 plus m1 dagger m1, which equals to m0 plus m1. Suppose the state being measured is psi cap psi. Suppose suppose the state being measured is cap psi and a ket 0 plus b ket 1. Then the probability of obtaining measurement outcome 0 is as shown in equation 2.96. Similarly, the probability of obtaining the measurement outcome 1 is p of 1 is equal to magnitude b squared. The state after measurement in the two cases is therefore as shown in equation 2.97 and 2.98. We will see in section 2.27 that multipliers like a over magnitude of a, which have modulus 1, can effectively be ignored. So the two post-measurement states are effectively ket 0 and ket 1, just as described in chapter 1. The status of postulate 3 is a fundamental postulate that intrigues many people. Measuring devices are quantum mechanical systems, so the quantum system being measured and the measuring device together are part of a larger, isolated quantum mechanical system. It may be necessary to include quantum systems other than the system being measured and the measuring device to obtain a completely isolated system. But the point is that this can be done. According to postulate 2, the evolution of this larger isolated system can be described by unitary evolution. Might it be possible to derive postulate 3 as a consequence of this picture? Despite considerable investigation along these lines, there is still disagreement between physicists about whether or not it is possible. We, however, are going to take a very pragmatic approach that in practice it is clear when to apply. Postulate 2 and when to apply postulate 3 and not worry about deriving one postulate from the other. Over the next few sections, we apply postulate 3 to several elementary but important measurement scenarios. Section 2.2.4 examines the problem of distinguishing a set of quantum states. Section 2.25 explains the second case of postulate 3. The projective, or the von Neumann measurements, section 2.2.6, explains another special case of postulate 3, known as POVM measurements. Many introductions to quantum mechanics only discuss projective measurements, omitting a full discussion of postulate 3, or POVM elements. For this reason, we have included box 2.5 on page 91, which comments on the relationship between the different classes of measurement we describe. 2.2.4 Distinguishing quantum states. An important application of postulate 3 is the problem of distinguishing quantum states in the classical world. Distinct states of an objective are usually distinguishable, at least in principle. For example, we can always identify whether a coin has landed heads or tails, at least in the ideal limit. Quantum mechanically, the situation is more complicated. In section 1.6, we gave a plausible argument that non-orthogonal quantum states cannot be distinguished. With postulate 3 as a firm foundation, we can now give a much more convincing demonstration of this fact. Distinguishability, like many ideas in quantum computation and quantum information, is most easily understood using the metaphor of a game involving two parties, Alice and Bob. Alice chooses a state, ket psi I, where I is greater than equal to 1 and less than equal to n. From some fixed set of states known to both parties, she gives the state kep psi I to Bob, whose task is to identify the index I of the state Alice has given him. Suppose that the states kep psi I are orthonormal, then Bob can do quantum measurement to distinguish these states using the following procedure. Define measurement operators. Mi is equal to kep psi I bra psi I, 1 for each possible index of I. An additional measurement operator m0 defined as the positive square root of the positive operator identity minus sum over I not equal to 0 of kep psi I bra psi I. These operators satisfy the completeness relation, and if the state kep psi I is prepared, then pi is equal to bra psi I mi kep psi I, which equals 1. So result I occurs with certainty. Thus, it is possible to reliably distinguish the orthonormal states kep psi I. By contrast, if the states kep psi I are not orthonormal, then we can prove that there is no quantum measurement capable of distinguishing the states. The idea is that Bob will do a measurement described by measurement operators mj with outcome j. Depending on the outcome of measurement, Bob tries to guess what the index I was using some rule. I equals fj, where f dot represents the rule he uses to make the guess. The key to why Bob can't distinguish non-orthonormal states kep psi I and kep psi 2 is the observation that kep psi 2 can be decomposed into a non-zero component parallel to kep psi I and the component orthogonal to kep psi 1. Suppose j is a measurement outcome such that f of j equals 1, that is, Bob guesses that the state was j1 kep psi 1, then he observes j when he observes j. But because of the component of kep psi 2 parallel to kep psi 1, there's a non-zero probability of getting outcome j when kep psi 2 is prepared. So sometimes Bob will make an error identifying which state was prepared. A more rigorous argument that non-orthogonal states can't be distinguished is given in the box 2.3, but this captures the essential idea. 2.2.5 Projective measurements. In this section, we explain an important special case of the general measurement postulate, postulate 3. This special class of measurements is known as projective measurements. For many applications of quantum computation and quantum information, we will be concerned primarily with projective measurements. Indeed, projective measurements actually turn out to be equivalent to the general measurement postulate when they are augmented with the ability to perform unitary transformations as described in postulate 2. We will explain this equivalence in detail in section 2.2.8 as the statement of the measurement postulate for projective measurements is superficially rather different from the general postulate, postulate 3. Projective measurements. A projective measurement is described by an observable M, a Hermitian operator on the state space of the system being observed. The observable has spectral decompositions. M is equal to the sum of sum over M of MPM as shown in equation 2.102, where Pm is the projector in the eigenspace of M with eigenvalue M. The possible outcomes of the measurement correspond to the eigenvalues M of the observable. Upon measuring the state kep psi, the probability of getting result M is given by equation 2.103. Given the outcome M occurred, Given that outcome M occurred, the state of the quantum system immediately after the measurement is shown as equation 2.104. Projective measurements can be understood as a special case of postulate 3. Suppose the measurement operators in postulate 3, in addition to satisfying the completeness relationship sum over M of M dagger M, M dagger MM is equal to identity, also satisfies the condition that MM are orthogonal projectors. That is, the MM are Hermitian, and MM prime is equal to delta M prime MM. With these additional restrictions, postulate 3 reduces to a projective measurement as just defined. Projective measurements have many nice properties. In particular, it's very easy to calculate average values for the projective measurements. By definition, the average, see Appendix 1 for elementary definitions, and results in probability theory. Value of the measurement is equation 2.110 to 2.113. This is a useful formula which simplifies many calculations. The average value of the observable M is often written M is equal to psi M bra psi M cap psi M bra psi M cap psi. From this formula, for the average follows a formula for the standard deviation associated to observables of M, as shown in equation 2.114 and 2.115. The standard deviation is a measure of the typical spread of the observed values upon measurement of M. In particular, if we perform a large number of experiments in which the state cap psi is prepared and the observable M is measured, then the standard deviation delta M of the observed values is determined by the formula delta M is equal to the square root of expectation value M squared minus expectation value squared of M. This formulation of measurement and standard deviations in terms of observables derives in an elegant way to results such as the Heisenberg uncertainty principle, see box 2.4. Two widely used nomenclatures for measurements deserve emphasis. Rather than giving an observable to describe a projective measurement, often people simply list a complete set of orthogonal projectors Pm satisfying the relation that sum over M Pm is equal to identity, and that P of M times P of M prime is equal to delta M prime times P of M. A corresponding observable implicit at this usage is M is equal to the sum over M of M Pm. Another widely used phrase to measure in a basis ket M, where ket M form an normal basis, simply means to perform the projective measurement with projectors Pm is equal to ket M bra M. Let's look at an example of a projective measurement on a single qubit. First is the measurement of the observable Z. This has eigenvalues +1 and -1 with corresponding eigenvectors ket0 and ket1. Thus, for example, measurement of Z on the side cap psi is equal to cap plus gives a result +1 with probability of 1/2. And similarly, the result -1 with probability 1/2. More generally, suppose V is any real three-dimensional unit vector that we can define an observable as shown in equation 2.116. Measurement of this observable is sometimes referred to as the measurement of spin along the v-axis. For historical reasons, the following two exercises encourage you to work out some elementary but important properties of such a measurement. 2.2.6 POVM measurements. The quantum measurement postulate, postulate 3, involves two elements. First, it gives a rule describing the measurement statistics, that is, the repetitive probabilities of the different possible measurement outcomes. Second, it gives a rule describing the post-measurement state of the system. However, for some applications, the post-measurement state of the system is of little interest, with the main item of interest being the probabilities of the respective measurement outcomes. This is the case, for example, is an experiment where the system is measured only once. Upon conclusion of the experiment, in such instances, there is a mathematical tool known as the POVM formalism, which is especially well adapted to the analysis of measurements. The acronym POVM stands for Positive Order Valued Measure, a technical term whose historical origins we won't worry about. This formalism is a simple consequence of the general description of measurements introduced in postulate 3, but the theory of POVMs is so elegant and widely used that it merits a separate discussion here. Suppose a measurement described by measurement operators M is performed upon a quantum state in the state kept psi, then the probability of outcome M is given by Pm is equal to bra psi M dagger sub M sub M ket psi. Suppose we define Em as M dagger M as shown in equations 2.117. And then from postulate 3 and elementary linear algebra, Em is a positive operator such that sum over Em is unitary, and Pm is equal to bra psi Em ket psi. Thus, the set of operators Em are sufficient to determine the probabilities of the different measurement outcomes. The operators Em are known as the POVM elements associated with the measurement. The complete set of set Em is known as a POVM. As an example of a POVM, consider a projective measurement described by measurement operators Pm, where the Pm are projectors such that Pm prime is delta Pm prime Pm, and the sum of M Pm is identity. In this instance, and only this instance, all the POVM elements are the same as the measurement operators themselves, since Em is equal to Pm dagger Pm, which is equal to Pm. Above, we notice that the POVM operators are positive and satisfy sum over M Em is equal to identity. Suppose now that set EM is some arbitrary set of positive operators, such that set EM is equal to I. We will show that there exists a set of measurement operators, M of M, defining a measurement described by the P of EM, set EM, defining MM is equal to root EM. We see that the sum over M of M dagger M, MM, is equal to sum over M, E of M is equal to unity. And therefore the set MM describes the measurement with P of EM, set EM. For this reason, it is convenient to define a P of EM to be a set of operators, set EM, such that A, each operator EM is positive, and B, the completeness relationship is obeyed, expressing the fact that probabilities sum to 1. To complete the description of P of EMs, we note that again, given a P of EM, set EM, the probability of outcome M is given by P of M, which is equal to br psi E of M cap psi. We've looked at projective measurements as an example of the use of P of EMs, but it wasn't very exciting since we didn't learn much that was new. The following more sophisticated example illustrates the use of the P of EM formalism as a guide for our intuition in quantum computation and quantum information. Suppose Alice gives Bob a qubit prepared in one of two states, cap psi 1 is equal to psi 0, or cap psi 2 is equal to psi plus, as cap plus. As explained in section 2.2.4, it is impossible for Bob to determine whether he was given psi 1 or psi 2 with perfect reliability. However, it is possible for him to perform a measurement which distinguishes the states from some of the time, but never makes an error of misidentification. Consider a P of EM containing three elements as shown in equations 2.18 to 2.12. Equations 2.118 to 2.120. It is straightforward to verify that these are positive operators which satisfy the completeness relationship and therefore form a legit P of EM. Suppose Bob is given the state cap psi 1 equal to state cat 0. He performs the measurement described by the P of EM, set E1, E2, E3. There is zero probability that he will observe the result E1 since E1 has been clearly chosen to ensure that the expectation value of E1 is 0. Therefore, if the result of his measurement is E1, then Bob can safely conclude that the state he received must have been psi 2. A similar line of reasoning shows that if the measurement outcome E2 occurs, then it must have been the state psi 1 that Bob received some of the time. However, Bob will obtain the measurement outcome E3, and he can infer nothing about the identity of the state he was given. The key point, however, is that Bob never makes a mistake identifying the state that he was given. This infallibility comes at the price that sometimes Bob obtains no information about the identity of the state. A simple example demonstrates the utility of the P of EM formalism as a simple and intuitive way of gaining insight into quantum measurements, at instances where only the measurement statistics matter. In many instances later in the book, we will only be concerned with the measurement statistics and will therefore use the P of EM formalism rather than the more general formalism for measurements described in postulate 3. Phase 2.2.7 Phase. Phase is a commonly used term in quantum mechanics with several different meanings dependent upon context. At this point, it is convenient to view a couple of these meanings. Consider, for example, the state e to the I theta cap psi, where cap psi is a state vector and theta is a real number. We can say that the state e to the I theta cap psi is equivalent to cap psi up to the global phase vector e to the I theta. It is interesting to note that the statistics of measurement predicted for these two states are the same. To see this, suppose mm is a measurement operator associated to some quantum measurement, and note that the respective probabilities for outcome m occur are the expectation are Brab psi m dagger m cap psi and Brab psi e to the minus I theta m dagger m e to the I theta Brab psi cap psi, which is equal to the first equation. Therefore, from an observational point of view, these two states are identical. For this reason, we may ignore global phase factors as being irrelevant to the observed properties of the physical system. There is another kind of phase known as the relative phase, which has quite a different meaning. Consider the states K plus and K minus, as shown in equation 2.121. In the first state, the amplitude of Ket1 is 1 over root 2. For the second state, the amplitude is minus 1 over root 2. In each case, the magnitude of the amplitudes is the same, but they differ in sign. More generally, we say that the two amplitudes A and B differ by a relative phase if there is a real theta such that A is exponential I theta B. More generally still, two states are said to differ by a relative phase More generally still, two states are said to differ by a relative phase in some bases if each of the amplitudes in that basis is related by such a phase factor. For example, the two states displayed above are the same up to a relative phase shift because the Ket0 amplitudes are identical, a relative phase factor of 1, and the Ket1 amplitudes differ only by a relative phase factor of minus 1. The difference between the relative phase factors and global phase factors is that for relative phase, the phase factors vary from amplitude to amplitude. This makes the relative phase and a basis-dependent concept, unlike global phase. As a result, states which differ only by relative phases in some bases give rise to physically observable differences in measurement statistics, and it is not possible to regard these states as physically equivalent, as we do with states differing by a global phase factor. 2.28 Composite systems. Suppose we are interested in a composite quantum system made up of two or more distinct physical systems. How would we describe these states of the composite system? The following postulate describes how the state space of a composite system is built up from the state space of the component system. Postulate 4. The state space of a composite physical system is the tensor product of the state space of the component physical systems. Moreover, if we have systems numbered 1 through n and system number I is prepared in the state Ket psi I, then the joint state of the total system is Ket psi I tensor Ket psi 2 tensor all the way to tensor Ket psi n. Why is the tensor product the mathematical structure used to describe the state space of a composite physical system? At one level, we can simply accept it as a basic postulate, not reducible to something more elementary, and move on. After all, we certainly expect that there are some canonical way of describing composite systems in quantum mechanics. Is there some other way we can arrive at this postulate? Here is one heuristic that is sometimes used. Physicists like to speak of the superposition principle of quantum mechanics, which state that if ket x and ket y are two states of a quantum system, then any superposition alpha ket x plus beta ket x should also be an allowed state of a quantum system. Then any superposition alpha ket x plus beta ket y should also be allowed state of a quantum system where magnitude alpha squared plus magnitude beta squared is equal to 1 for composite systems. It seems natural that if ket A is a state of system A and ket B is a state of system B, then there should be some corresponding state which we might denote ket A ket B. If the joint system AB, applying the superposition principle to product states of this form, we arrive at the tensor product postulate given above. This is not a derivation, since we are not taking the superposition principle as a fundamental part of our description of quantum mechanics, but it gives you the flavor of the various ways in which these ideas are sometimes reformulated. A variety of different notations for composite systems appear in the literature. Part of the reason for this postulation is that different notations are better adapted for different applications. We will also find it convenient to use some specialized notations on occasion. At this point, it suffices to mention a useful subscript notation to denote states and operators on different systems when it is not clear from context. For example, in a system containing 3 qubits, x subscript 2 is the Pauli sigma x operator acting on the second qubit. In section 2.25, we claim that projective measurements together with unitary dynamics are sufficient to implement a general measurement. The proof of this statement makes use of composite quantum systems and is a nice illustration of postulate 4 in action. Suppose we have a quantum system with state space Q. We want to perform a measurement described by measurement operators MM on the system Q. To do this, we introduce an ancillary system with state space M having an orthonormal basis ket M in one-to-one correspondence with the possible outcomes of the measurement we wish to implement. This ancillary system can be regarded as merely a mathematical device appearing in the construction, or it can be interpreted physically as an extra quantum system introduced into the problem, which we assume has a state space with the required properties. Letting ket 0 be any fixed state of M, define an operator U on products ket psi ket naught of states ket psi from Q with state ket naught by equation 2.122 using the orthonormality of states M and the completeness relationship. Sum over M of M dagger M, MM is equal to unity, or identity, not unity. We can see that U preserves inner products between states of the form ket psi ket naught, as shown by equations 2.123 to 2.125. By the results of exercise 2.67, it follows that U can be extended to a unitary operator on the space Q tensor M, which we also denote by U. Next, suppose we perform a projective measurement on the two systems described by projectors P of M, defined by identity Q tensor ket M bra M. Outcome M occurs with probability, given by equations 2.127 to 2.129, just as given in postulate 3. The joint state of the system, Qm after measurement, conditional on result M occurring is given by equation 2.130. It follows that the state of the system M after measurement is ket M, and the state of the system Q is given by equation 2.131, just as described by postulate 3. Thus, unitary dynamics, projective measurements, and the ability to induce ancillary systems together allow any measurement of the form described in postulate 3 to be realized. Postulate 4 also enables us to define one of the most interesting and puzzling ideas associated with composite quantum systems: entanglement. Consider the 2-qubit state shown in equation 2.132. This state has the remarkable property that there are no single qubit states, ket A and ket B, such that ket psi is equal to ket A tensor ket B, a fact which you should now convince yourself of. We say that a state of composite system having this property, that it can't be written as a product of states of its component systems, is an entangled state. For reasons which nobody fully understands, entangled states play a crucial role in quantum computation and quantum information, and arise repeatedly throughout the remainder in this book. We have already seen entanglement play a crucial role in quantum teleportation, as described in section 1.3.7. In this chapter, we give two examples of the strange effects enabled by entangled quantum states. Superdense coding, section 2.3, and the violation of Bell's inequality, section 2.6. 2.2.9, quantum mechanics, a global view. We have now explained all the fundamental postulates of quantum mechanics. Most of the rest of the book is taken up with deriving consequences of these postulates. Let's quickly review the postulates and try to place them in some type of global perspective. Postulate 1. Set the reason for quantum mechanics by specifying how the state of an isolated quantum system is to be described. Postulate 2 tells us that the dynamics of closed quantum systems are described by the Schrödinger equation, and thus by unitary evolution. Postulate 3 tells us how to extract information from our quantum systems by giving a prescription for the description of measurement. Postulate 4 tells us how the state spaces of different quantum systems may be combined to give a description of the composite system. What's odd about quantum mechanics, at least by our classical lights, isn't that we can't directly observe the state vector. It's a little bit more a game of chess, where you can never find out exactly where each piece is, but only know the rank of the board they are on. Classical physics and our intuition tells us that the fundamental properties of an object, like energy, position, and velocity, are directly accessible to observation. In quantum mechanics, these quantities no longer appear as fundamental, being replaced by the state vector, which can't be directly observed. It is as though there is a hidden world in quantum mechanics, which we can only indirectly and imperfectly access. Moreover, merely observing a classical system does not necessarily change the state of the system. Imagine how difficult it would be to play tennis if each time you looked at the ball, its position changed. But according to postulate 3, observation in quantum mechanics is an invasive procedure that typically changes the state of the system. What conclusions should we draw from these strange features of quantum mechanics? Might it be possible to reformulate quantum mechanics in a mathematically equivalent way so that it had a structure more like classical physics? Section 2.6 will prove Bell's inequality. A surprising result that shows any attempt at such a reformulation is doomed to failure. was struck with the counterintuitive nature of quantum mechanics. Of course, the proper reaction to this is glee, not sorrow. It gives us an opportunity to develop tools of thought that make quantum mechanics intuitive. Moreover, we can exploit the hidden nature of the state vector to do information processing tasks beyond what is possible in the classical world. Without this counterintuitive behavior, quantum computation and quantum information would be a lot less interesting. We can also turn this discussion about and ask ourselves, if quantum mechanics is so different from classical physics, then how come the everyday world looks so classical? Why do we see no evidence of a hidden state vector in our everyday lives? It turns out that the classical world we see can be derived from quantum mechanics as an approximate description of the world that will be valid on the sort of time, length, and mass scales we commonly encounter in our everyday lives. Explaining the details of how quantum mechanics gives rise to the classical physics is beyond the scope of this book. But the interested reader should check out the discussion in this topic in History and Further Reading at the end of Chapter 8. Chapter 2.3 Application Superdense Coding. Superdense coding is a simple yet surprising application of elementary quantum mechanics. It combines in a concrete, non-trivial way all the basic ideas of elementary quantum mechanics, as covered in the previous sections, and is therefore an ideal example of the information processing tasks that can be accomplished using quantum mechanics. Superdense coding involves two parties, conventionally known as Alice and Bob, who are a long way away from one another. Their goal is to transmit some classical information from Alice to Bob. Suppose Alice is in possession of two classical bits of information which she wishes to send Bob, but is only allowed to send a single qubit to Bob. Can she achieve her goal? Superdense coding tells us that the answer to this question is yes. Suppose Alice and Bob initially share a pair of qubits in the entangled state, as given by equation 2.133. Alice is initially in possession of the first qubit, while Bob has possession of the second qubit, as illustrated in figure 2.3. Note that cap psi is a fixed state. There is no need for Alice to have sent Bob any qubits in order to prepare this state. Instead, some third party may prepare the entangled state ahead of time, sending one of the qubits to Alice and the other to Bob. Okay. By sending the single qubit in her possession to Bob, it turns out that Alice can communicate two bits of classical information to Bob. Here is the procedure she uses. If she wishes to send the bit string 00 to Bob, then she does nothing at all to her qubit. If she wishes to send 01, then she applies the phase flip Z to her qubit. If she wishes to send 10, then she applies the quantum NOT gate X to her qubit. If she wishes to send 11, then she applies the Y gate to her qubit. The four resulting states are easily seen, as we noted in section 1.3.6, are easily seen to be equations 2.134 through 2.137. As we noted in section 1.3.6, these four states are known as the Bell basis, Bell states, or EPR pairs, in honor of the several of the pioneers who first appreciated the novelty of entanglement. Notice that the Bell states form an orthonormal basis and can therefore be distinguished by an appropriate quantum measurement. If Alice sends her qubit to Bob, giving Bob possession of both qubits, then by doing the measurement in the Bell basis, Bob can determine which of the four possible bit strings Alice sent. Summarizing, Alice, interacting with only a single qubit, is able to transmit 2 bits of information to Bob. Of course, 2 qubits are involved in the protocol, but Alice never interacted with the second qubit. Classically, the task Alice accomplishes would have been impossible had she only transmitted a single classical bit. As we will show, oh, as we will show in chapter 12, as we will show in chapter 12. Yikes. Furthermore, this remarkable superdense coding protocol has received partial verification in the laboratory. See history and further reading for references to the experimental verification. In later chapters, we will see many other examples, some of them much more spectacular than superdense coding, of quantum mechanics being harnessed to perform information processing tasks. However, a key point can already be seen in this beautiful example. Information is physical, and surprising physical theories such as quantum mechanics may predict surprising information processing abilities. 2.4. The density operator. We have formulated quantum mechanics using the language of state vectors. An alternate formulation is possible using a tool known as the density operator or density matrix. This alternate formulation is mathematically equivalent to the state vector approach, but it provides a much more convenient language for thinking about some commonly encountered scenarios in quantum mechanics. The next 3 sections describe the density operator formulation of quantum mechanics. Section 2.4.1 introduces the density operator using the concept of an ensemble of quantum states. Section 2.4.2 develops some general properties of the density operator. Finally, section 2.4.3 describes an application where the density operator really shines as a tool for the description of individual subsystems of a composite quantum system. Examples of quantum systems. The density operator language provides a convenient means for describing quantum systems whose states is not completely known. More precisely, suppose a quantum system is one of the number of states ket psi I, where I is an index. With respective probabilities pi, we shall call set pi, set ket psi I an ensemble of pure states. The density operator for the system is defined by the equation 2.138. The density operator is often known as the density matrix. We will use the two terms interchangeably. It turns out that all the postulates of quantum mechanics can be reformulated in terms of the density operator language. The purpose of this section and the next is to explain how to perform this reformulation and explain what it is useful. Whether one uses the density operator language or the state vector language is a matter of taste, since both give the same results. However, it is sometimes much easier to approach problems from one point of view rather than the other. Suppose, for example, that the evolution of a closed quantum system is described by the unitary operator U. If the system was initially in the state ket psi I with probability pi, then after the evolution has occurred, the system will be in the state U ket psi I with probability pi. Thus, the evolution of the density operator is described by the equation 2.139. Measurements are also easily described in the density operator language. Suppose we perform a measurement described by the measurement operators m. If the initial state was ket psi I, then the probability of getting result m is as shown in equation 2.140, where we have used equation 2.61 to obtain the last equality. By the law of total probability, see Appendix 1, for an explanation of this and other elementary notations of probability theory, the probability of obtaining result m is as shown by equations 2.141 through 2.143. What is the density operator of the system after obtaining the measurement result m? If the initial state was kept psi I, then the state after obtaining the result m is given by the equation 2.144. Thus, after a measurement which yields the result m, we have an ensemble of states kept psi I superscript m, with respective probabilities p I bar m, I pipe m. The corresponding density operator Pm is therefore given by the equation 2.145. But by elementary probability theory, Pi pipe m is equal to Pm, I divided by Pm. Which equals to Pm given I, Pi over Pm. Substituting from equation 2.143 and equation 2.140, we obtain equation 2.146 and 2.147. What we have shown is that the basic postulates of quantum mechanics related to unitary evolution and measurement can be rephrased in the language of density operators. In the next section, we complete this rephrasing by giving an intrinsic characterization of the density operator that does not rely on the idea of a state vector. Before doing so, however, it is useful to introduce some more language and one more fact about the density operator. First, the language. A quantum system whose state kept psi is known exactly is said to be in a pure state. In this case, the density operator is simply rho is equal to kept psi bra psi. Otherwise, rho is in a mixed state. It is said to be in a mixture of the different pure states in the ensemble for rho. In the exercises, you will be asked to demonstrate a simple criterion for demonstrating whether a state is pure or mixed. A pure state satisfies trace of rho squared is equal to 1, while a mixed state satisfies that trace of rho squared is less than 1. A few words of warning about the nomenclature. Sometimes people use the term mixed state as a catch-all to include both pure and mixed quantum states. The origin for this usage seems to be that it implies that the writer is not necessarily assuming that a state is pure. Second, the term pure state is often used in reference to a state vector kept psi to distinguish it from a density operator rho. Finally, imagine a quantum system is prepared in the state P rho of I with probability Pi. It is not difficult to convince yourself that the system may be described by the density matrix sum over I P of Pi rho I. A proof of this is to suppose that rho I arises from some ensemble. Note that I is fixed for pure states. A proof of this is to suppose that rho I arises from some ensemble set Pij, ket psi ij. Note that I is fixed for pure states, so the probability of being in the state ket psi ij is Pi Pij, and the density matrix for the system is thus given by equation 2.148 and 2.149. There we have it, where we have used the definition that rho I is equals to the sum over j of Pij ket psi ij bra psi ij. We say that rho is a mixture of states P rho I with probabilities Pi. Thus, this concept of mixture comes up repeatedly in the analysis of problems like quantum noise, where the effect of the noise is to introduce ignorance into our knowledge of the quantum state. A simple example is provided by the measurement scenario described above. Imagine that for some reason, our record of the result M of the moment was lost. We would have a quantum system in the state ρm with probability P of M, but would no longer know the actual value of M. The state of such a quantum system would therefore be described by the density operator, as shown in equation 2.150 through 2.152. A nice compact formula which may be used as the starting point for analysis of further operations on the system. 2.4.2 General properties of the density operator. The density operator was introduced as a means of describing ensembles of quantum states. In this section, we move away from this description to develop an intrinsic characterization of density operators that does not rely on an ensemble interpretation. This allows us to complete the program of giving a description of quantum mechanics that does not take as its foundation the state vector. We also take the opportunity to develop numerous other elementary properties of the density operator. The class of operators that are density operators are characterized by the following useful theorem. Theorem 2.5. Characterization of density operators. An operator ρ is the density operator associated to some ensemble set P of I, ket psi I, if and only if it satisfies the conditions. 1. Trace condition, ρ has trace equal to 1. 2. Positivity condition, ρ is a positive operator. Poof. Suppose that ρ is equal to sum over I of Pi, ket psi I, br psi I is a density operator. Then, by equation 2.153, the trace condition is satisfied, such that the trace of ρ is equal to 1. Suppose ket phi is an arbitrary vector in state space. Then, the positivity condition is satisfied as shown in equations 2.154 through 2.156. Conversely, suppose ρ is any operator satisfying the trace and positivity conditions. Since ρ is positive, it must have a spectral decomposition, as shown in equation 2.157, where the vectors ket j are orthogonal and lambda j are real non-negative eigenvalues of ρ. From the trace condition, we can see that the sum over j of lambda j is equal to 1. Therefore, a system in the state ket j with probability lambda j will have the density operator ρ. That is, the ensemble set lambda j, ket j is an ensemble of states giving rise to a density operator ρ. This theorem provides a characterization of density operators that is intrinsic to the operator itself. We can define a density operator to be a positive operator ρ which has trace equal to 1, making this definition allow us to reformulate the postulates of quantum mechanics in the density operator picture. For ease of reference, we state all the reformulated postulates here. Postulate 1. Associated to any isolated physical system is a complex vector space with inner product, that is, a Hilbert space, known as the state space of the system. The system is completely described by its density operator, which is a positive operator ρ with trace 1, acting on the state space of the system. If a quantum system is in the state ρi with probability Pi, then a density operator for the system is sum over I of Pi ρi. Postulate 2. The evolution of a closed quantum system is described by a unitary transformation. That is, the state ρ of the system at time t1 is related to the state ρ prime of the system at time t2 by a unitary operator u, which depends only on the times t1 and t2, as shown in Equation 2.158. Postulate 3. Quantum measurements are described by a collection, set MM, of measurement operators. These are the operators acting on the state space of the system being measured. The index M refers to the measurement outcomes that may occur in the experiment. If the state of the quantum system is ρ immediately before the measurement, then the probability that result M occurs is given by equation 2.159, and the state of the system after the measurement is equation 2.160. The measurement operators satisfy the completeness equation as shown in equation 2.161. Postulate 4. The state space of a composite physical system is the tensor product of the state space of the component physical systems. Moreover, if we have the systems numbered 1 through n, and the system number I is prepared in the state space ρi, then the joint state of the total system is ρi tensor ρ2 tensor all the way up to ρn. These reformulations of the fundamental postulates of quantum mechanics in terms of the density operator are of course mathematically equivalent to description in terms of the state vector. Nevertheless, as a way of thinking about quantum mechanics, the density operator approach really shines for two applications: the description of quantum systems, whose state is not known, and the description of subsystems of a composite quantum system. As will be described in the next section, for the remainder of this section we flesh out the properties of the density matrix in more detail. It is a tempting and surprisingly common fallacy to suppose that the eigenvalues and eigenvectors of a density matrix have some special significance with regard to the ensemble of quantum states represented by that density matrix. For example, one might suppose that a quantum system with density matrix, as shown by equation 2.162, must be in the state ket 0 with probability 3/4, and in the state ket 1 with the probability 1/4. However, this is not necessarily the case. Suppose we define ket A and ket B as given by equations 2.163 and 2.164 respectively, and the quantum system is prepared in the state ket A with probability half and the state ket B with probability half. Then it is easily checked that the corresponding density matrix is given by equation 2.165. That is, these two different ensembles of quantum states give rise to the same density matrix. In general, the eigenvectors and eigenvalues of a density matrix just indicate one of many possible ensembles that may give rise to a specific density matrix, and there is no reason to suppose it is an especially privileged ensemble. A natural question to ask in the light of this discussion is what class of ensembles does give rise to a particular density matrix? The solution to this problem, which we now give, has surprisingly many applications in quantum computation and quantum information, notably in the understanding of quantum noise and quantum error correction, chapters 8 and 10. For the solution, it is convenient to make use of the vectors ket psi squiggle I, which may not be normalized to unit length. We say the set ket psi squiggle I generates the operator ρ, defined by the sum over I of ket psi squiggle I br psi squiggle I, and thus the connection to the usual ensemble picture of density operators is expressed by the equation ket psi squiggle I is equal to the square root of pi ket psi I, when do two sets of vectors ket psi squiggle I and ket pi squiggle j generate the same operator ρ. The solution to this problem will enable us to answer the question of what ensembles give rise to a given density matrix. Theorem 2.6. Unitary freedom in the ensemble for density matrices. The sets ket psi squiggle I and ket phi squiggle I generate the same density matrix if, and only if, psi squiggle I is equal to the sum over j of uij ket phi squiggle j, as shown in equation 2.166, where uij is a unitary matrix of complete numbers with indexes I and j, and we paired whichever set of vectors ket psi squiggle I or ket phi squiggle I j is smaller with additional vector zeros, so that the two sets have the same number of elements. As a consequence of the theorem, note that rho is equal to sum I over p of I, ket psi I, br psi I, which is equal to the sum of j over qj, ket phi j, br phi j for normalized states, ket psi I and ket phi j, and probability distributions pi and qi if and only if the condition in equation 2.167 is met. For some unitary matrix uij, we may pad the smaller ensemble with entries having probability 0 in order to make the two ensembles the same size. Thus, theorem 2.6 characterizes the freedom in ensembles set pi, ket psi I, giving rise to a given density matrix rho. Indeed, it is easily checked that our early example of a density matrix with two different decompositions in equation 2.162 arises as a special case of this general result. Let us now turn to the proof of the theorem. Proof. Suppose ket psi wiggle I is equal to the sum over j of uij ket phi squiggle j for some unitary uij, then equations 2.168 through 2.171, which shows that ket psi squiggle I and ket phi squiggle j generate the same operator. Conversely, suppose that A is defined as in equation 2.172, let A is equal to the sum over k of lambda k, ket k, br k, be a decomposition for A such that the states k are orthonormal and lambda k are strictly positive. Our strategy is to relate the states ket psi squiggle I to the states ket squiggle k as defined by root lambda k ket k, and similarly relate the states ket phi jiggle j, phi squiggle j to the states ket squiggle k. Combining the two relations will give us the result. Let ket psi be any vector orthonormal to the space spanned by the ket squiggle k, so that the inner product of psi and squiggle k times the inner product of k squiggle k and psi is equal to 0 for all k, and thus we see that equation 2.173 holds. Thus, br psi ket squiggle psi I is equal 0 for all I and all theta and all psi orthonormal to the space spanned by the k psi ket k wiggle squiggle. It follows that each ket psi I wiggle can be expressed as a linear combination of the ket k squiggle, comma ket psi squiggle I, which is equal to the sum over k of Cik ket squiggle k. Since A is equal to as previously defined, we see that equation 2.174 holds. The operators ket k squiggle, bra j, bra l squiggle are easily seen to be linearly independent, and thus it has to be that sum I Cik C complex conjugate IL is equal to delta KL. This ensures that we may append extra columns to C to obtain a unitary matrix V such that psi squiggle I is equal to sum over K of Vik ket squiggle K, where we have appended zero vectors to the list of squiggle K. Similarly, we can find a unitary matrix W such that ket phi squiggle j is equal to sum of k w j k ket squiggle k. Thus, that equation holds. Uh, 2.4.3, the reduced density operator. Perhaps the deepest application of the density operator is as a descriptive tool for subsystems of a composite quantum system. Such a description is provided by the reduced density operator, which is the subject of this section. The reduced density operator is so useful as to be virtually indispensable as the analysis of composite quantum systems. Suppose we have physical system A and B, whose state is described by a density operator rho AB. The reduced density operator for a system A is defined as rho to the power of A, which is equal to the trace subscript B of rho to the superscript AB, as defined in equation 2.177, where trace subscript B is a map of operators known as the partial trace over system B. The partial trace is defined as shown in equation 2.178, where A1 and A2 are two vectors in the state space of A, and B1 and B2 are two vectors in the state space of B. The trace operation appearing on the right-hand side is the usual trace operation for a system B. Okay. Yeah, man. trace operation, appearing on the right-hand side, is the usual trace operation for system B, so that trace of ket B1 bra B2 is equal to bra B2 ket B1. We have defined the partial trace operation only on a spatial subclass of operators on AB. The specification is completed by requiring an addition to equation 2.178 that the partial trace be linear in its input. It is not obvious that the reduced density operator for the system A is in any sense a description for the state of the system A. The physical justification for making this identification is that the reduced density operator provides the correct measurement statistics for measurements made on system A. This is explained in more detail in box 2.6 on page 107. The following simple example calculations may also help understand the reduced density operator. First, suppose a quantum system is in the product state rho superscript AB, which equals rho tensor sigma, where rho is the density operator for system A and sigma is the density operator for system B. Then, equation 2.184, which is the result we intuitively expect. Sure we do. Similarly, rho B is equal sigma for this state. A less trivial example is the Bell state, which has density operator shown in equation 2.185 and 2.186. Tracing out the second qubit, we find the reduced density operator for the first qubit, as shown in equations 2.187 through 2.198. Notice that the state is a mixed state, since the trace is less than 1. This is quite a remarkable result. The state of the joint system of 2 qubits is a pure state, that is, it is known exactly. However, the first qubit is in a mixed state, that is, the state about which we apparently do not have maximal knowledge. This strange property, that the joint state of a system can be completely known, yet a subsystem be a mixed state, is another hallmark of quantum entanglement. Quantum teleportation and the reduced density operator. A useful application of the reduced density operator is to the analysis of quantum teleportation. Recall from section 1.3.7, the quantum teleportation is a procedure of sending quantum information from Alice to Bob, given that Alice and Bob share an EPR pair and have a classical communications channel. At first sight, it appears as though teleportation can be used to do faster-than-light communication, a big no-no according to the theory of relativity. We surmised in section 1.37 that what prevents faster-than-light communication is the need for Alice to communicate her measurement results to Bob. The reduced density operator allows us to make this rigorous. Recall that immediately before Alice makes her measurement, the quantum state of the 3 qubits in equation 1.32 is as shown in equation 2.192. Measuring analysis computational basis, the state of the system after the measurement is given as equation 2.193 through 2.196. The density operator of the system is thus given as equation 2.197. Tracing out Alice's system, we see that the reduced density operator of Bob's system is given by equation 2.198 through 2.201, where we have used the completeness relation in the last line. Thus, the state of Bob's system after Alice has performed the measurement, but before Bob has done the measurement, result is I/2. The state has no dependence upon the state ket psi being teleported, and thus any measurement performed by Bob will contain no information about ket psi, thus preventing Alice from using teleportation to transmit information to Bob faster than light. 2.5. The Schmidt decomposition and purifications. Density operators and the partial trace are just the beginning of a wide array of tools useful for the study of composite quantum systems, which are at the heart of quantum computation and quantum information. Two additional tools of great value are the Schmidt decomposition and purifications. In this section, we present both these tools and try to give the flavor of their power. Theorem 2.7. Schmidt decomposition. Suppose that ket psi is a pure state of a composite system, A times B. Then there exists orthonormal states, ket IA for system A, and orthonormal states, ket IB for system B, such that psi is equal to the sum over I of lambda I, ket IA, and times ket IB, as displayed in equation 2.202, where lambda I are non-negative real numbers satisfying the sum over I of lambda I squared is equal to 1, known as the Schmidt coefficients. This result is very useful. As a taste of its power, consider the following consequence. Let ket psi be a pure state of a composite system, AB. Then, by the Schmidt decomposition, rho A is equal to sum over I of lambda squared I, ket IA, bra IA, and rho B is the equivalent, but the indices replaced with B. So the eigenvalues of rho A and rho B are identical, namely lambda squared I for both density operators. Many important properties of quantum systems are completely determined by the eigenvalues of the reduced density operator of the system. So for a pure state of a composite system, such properties will lead to the same thing for both systems. As an example, consider the state of two qubits. Ket 00 plus ket 01 plus ket 11 over root 3. This has no obvious symmetry property, yet if you calculate trace of rho A squared and trace of rho B squared, you will discover that they have the same value, 7 over 9 in each case. This is but one small consequence of this Schmidt decomposition. Skip proof. Bases, ket IA and ket IB are called the Schmidt bases for A and B, respectively, and the number of non-zeros and the number of non-zero elements. I is called the Schmidt number for the state ket psi. The Schmidt number is an important property of a composite quantum system, which which in some sense quantifies the amount of entanglement between systems A. To get some idea of why this is the case, consider the following. Consider the following obvious but important property. The Schmidt number is preserved under unitary transformations on a system A or system B alone. To see this, notice that if sum over I of lambda I ket IA ket IV is the Schmidt decomposition for ket psi, then the previous equation multiplied by U is the Schmidt decomposition for U ket psi, where U is a unitary operator acting on a system A. Algebraic invariance properties of this type make the Schmidt number a very useful tool. The second related technique for quantum computation, quantum information, is purification. Suppose we are given a state, rho A, or superscript A, of a quantum system A. It is possible to introduce another system which we denote R and define a pure state, ket AR, for the joint system AR, such that rho to the power of A is equal to the trace subscript R of ket AR bra AR. That is, the pure state ket AR reduces to rho to the power of A when we look at a system A alone. This is purely mathematical procedure known as purification, which allows us to associate pure states with mixed states. For this reason, we call the system R a reference system. It is a fictitious system without a direct physical significance. To prove that the purification can be done for any state, we explain how to construct a system R and purification ket AR for rho to the power of A. Suppose rho to the power of A has orthonormal decomposition. Rho to the power of A is equal to sum over I of pi ket I to the power of A rho I to the power of A. To purify rho A, we introduce a system R, which has the same state space as system A, with orthonormal basis states ket I to the power of R, and define a pure state for the combined system. This is shown in equation 2.207. We now calculate the reduced density operator for a system A corresponding to the state ket AR, as shown in equations 2.208 and 2.20 through 2.2011. Thus, ket AR is a purification of rho to the power of A. Notice the close relationship of the Schmidt decomposition to purification. The procedure used to purify a mixed state of a system A is to determine a pure state whose Schmidt basis for a system A is just the basis in which the mixed state is diagonal, with the Schmidt coefficients being the square root of the eigenvalues of the density operator being purified. In this section, we've explained two tools for studying composite quantum systems, the Schmidt decomposition and purifications. These tools will be indispensable to the study of quantum composition, quantum computation, and quantum information, especially quantum information, which is the subject of part 3 of this book. (2.6) EPR and the Bell equality. Anybody who is not shocked by quantum theory has not understood it. Niels Bohr. I recall that during one walk, Einstein suddenly stopped, turned to me and asked whether I really believe that the moon exists only when I look at it. The rest of this walk was devoted to a discussion of what a physicist should mean by the term "to exist." Abraham Pies. Quantum phenomena do not occur in a Hilbert space, they occur in a laboratory. Asher Perez. What is proved by impossibility proofs is lack of imagination. John Bell. This chapter has focused on introducing the tools and mathematics of quantum mechanics. As these techniques are applied in the following chapters of this book, an important recurring theme is the unusual non-classical properties of quantum mechanics. But what exactly is the difference between quantum mechanics and the classical world? Understanding this difference is vital in learning how to perform information processing tasks that are difficult or impossible with classical physics. This section concludes the chapter with a discussion of Bell inequality, a compelling example for an essential difference between quantum and classical physics. Then we speak of an object such as a person or a book. We assume that the physical properties of that object have an existence independent of observation, that is, measurement merely acts to reveal such physical properties. For example, a tennis ball has one of its physical properties, its position, which we typically measure using light scattered from the surface of the ball. As quantum mechanics was being developed in the 1920s and 1930s, a strange point of view arose that differs markedly from the classical view. As described earlier in the chapter, according to quantum mechanics, an unobserved particle does not possess physical properties that exist independent of observation. Rather, such physical properties arise from a consequence of measurement performed upon the system. For example, according to quantum mechanics, a qubit does not possess definite properties of spin in the z direction, sigma z, and spin in the x direction, sigma x, each of which can be revealed by performing an appropriate measurement. Rather, quantum mechanics gives a set of rules which specify, given the state vector, the probabilities of the possible measurement outcomes. Then the observable sigma z is measured when the observable sigma x is measured. Many physicists rejected this view of nature. The most prominent objector was Albert Einstein. In the famous EPR paper co-authored with Nathan Rosen and Boris Podolsky, Einstein proposed a thought experiment which he demonstrated that quantum mechanics is not a complete theory of nature. The essence of EPR argument is as follows. EPR were interested in the way that they termed elements of reality. Their belief was that any such element of reality must be represented in any complete physical theory. The goal of the argument was to show that quantum mechanics is not a complete physical theory by identifying elements of reality that were not included in quantum mechanics. The way they attempted to do this was by introducing what they claimed was a sufficient condition for a physical property to be an element of reality, namely, that it be possible to predict with certainty that the value that property will have immediately before measurement. Consider, for example, an entangled pair of qubits belonging to Alice and Bob, respectively, as shown in equation 2.218. Suppose Alice and Bob are a long way away from one another. Alice performs a measurement of spin along the v-axis, that is, she measures the observable v dot sigma. defined in equation 2.116 on page 90. Suppose Alice receives the result plus 1, then a simple quantum mechanical calculation given in box 2.7 shows that she can predict with certainty that Bob will measure -1 on his qubit if he also measures spin along the v-axis. Similarly, if Alice measured -1, then she can predict with certainty that Bob will measure +1 on his qubit, because it is always possible for Alice to predict the value of the measurement result recorded when Bob's qubit is measured. For the v-direction, that physical property must correspond to an element of reality by the EPR criterion and should be represented in any complete physical theory. However, standard quantum mechanics, as we have presented it, merely tells one how to calculate the probabilities of the respective measurement outcomes if v.sigma is measured. Standard quantum mechanics certainly does not include any fundamental element intended to represent the value of v.sigma for all unit vectors v. The goal of EPR was to show that quantum mechanics is incomplete by demonstrating the quantum mechanics like some essential element of reality by their criterion. They hope to force a return to a more classical view of the world, one in which system could be ascribed properties which existed independently of measurements performed on those systems. Unfortunately for EPR, most physicists did not accept the above reasoning as convincing. The attempt to impose on nature by fiat properties which she must obey seems a most peculiar way of studying her laws. Indeed, nature has had the last laugh on EPR. Nearly 30 years after the EPR paper was published, an experimental test was proposed that could be used to check whether or not that picture of the world which EPR was hoping to force a return to is valid or not. It turns out that nature experimentally invalidates that point of view while agreeing with quantum mechanics. Dang. The key to this experimental invalidation is a result known as Bell's inequality. Bell's inequality is not a result about quantum mechanics. So the first thing we need to do is to momentarily forget all our knowledge of quantum mechanics. To obtain Bell's inequality, we're going to do a thought experiment, which we will analyze using our common sense notions of how the world works. The sort of notions Einstein and his collaborators thought nature ought to obey. After we have done the common scene analysis, we will perform a quantum mechanical analysis, which we can show is not consistent with common sense analysis. Nature can then be asked by means of a real experiment to decide between our common sense notions of the world, of how the world works, and quantum mechanics. Imagine we perform the following experiment, illustrated in figure 2.4. Charlie prepares two particles. It doesn't matter how he prepares the particles, just that he is capable of repeating the experimental procedure which he uses. Once he has performed the preparation, he sends one particle to Alice and the second particle to Bob. Once Alice receives her particle, she performs a measurement on it. Imagine that she has available two different measurement apparatuses, so she could choose to do one of the two different measurements. These measurements are physical properties which she shall label PQ and PR, respectively. Alice doesn't know in advance which measurements she will choose to perform. Rather, when she receives the particle, she flips a coin. or uses some other random method to decide which measurement to perform. We suppose for simplicity that the measurement can each have one of two outcomes, +1 or -1. Suppose Alice's particle was valid Q for the property PQ. Q is assumed to be an objective property of Alice's particle, which is merely revealed in the measurement. Much as we imagine the position of a tennis ball to be revealed by the particles of light being scattered off it, similarly let R denote the value revealed by the measurement of the properties of PR. Similarly, suppose that Bob is capable of measuring one of two properties, PS or PT, once again revealing an objectively existing value S or T for the property, each taking value +1 or -1. Bob does not decide beforehand which property he will measure, but waits until he has received the particle and then chooses randomly. The timing of the experiment is arranged so that Alice and Bob do the measurements at the same time, or, to use the more precious language of relativity, in a causally disconnected manner. Therefore, the moment which Alice performs cannot disturb the result of Bob's measurement, or vice versa, since physical influences cannot propagate faster than light. We are going to do some simple algebra with the quantity Qs plus Rs plus Rt minus Qt. Notice that equation 2.219 because Q equals +-1 follows that either Q plus R S equals 0 or Q minus RT equals 0. In either case, it is that easy to see from 2.219 that Qs plus Rs plus Rt minus Qt equals ±2. Suppose next that in a state where Q equals Q, R equals R, S equals S, and T equals T, these properties may depend on how Charlie performs his preparation, and on experimental noise, letting E dot denote the mean value of quantity. We have equations 2.200 and 2.2222. Also, equations 2.223 through 2.224. Comparing 2.222 and 2.224, we obtain the Bell quantity, that is 2.225. This result is also often known as the CH-SH inequality, after the initials of its four discoverers. It is part of the larger set of inequalities known generically as Bell inequalities, since the first was found by John Bell. By repeating the experiment many times, Alice and Bob can determine each quantity on the left-hand side of the Bell inequality. For example, after finishing a set of experiments, Alice and Bob get together to analyze their data. They look at all the experiments where Alice measured PQ and Bob measured PS. By multiplying the results of their experiments together, they get a sample of values for QS. By averaging over this sample, they can estimate EQS prime to an accuracy, just EQS, to an accuracy only limited by the number of experiments which they perform. Similarly, they can estimate all the other quantities on the left-hand side of the Bell inequality and thus check to see whether it is obtained in a real experiment. It's time to put some quantum mechanics back in the picture. Imagine we perform on the following quantum mechanical experiment. Charlie prepares a quantum system of two qubits in the state shown by equation 2.226. He passes the first qubit to Alice and the second qubit above, they perform measurements from the following observables, shown in 2.227 and 2.228. Simple calculation shows that the average value for these observables, written in the quantum mechanical dot notation, are as shown by equation 2.229, thus equation 2.230. But hold on, we learned back in 2.225 that the average value of QS plus the average value of RS plus the average value of RT minus the average value of QT can never exceed 2. Yet here, quantum mechanics predicts that the sum of averages yields 2 root 2. Fortunately, we can ask nature to resolve the apparent paradox for us. Clever experiments using photons, particles of light, have been done to check the prediction of 2.230 of quantum mechanics versus the Bell quantity 2.225, which we were led to by our common sense reasoning. The details of the experiments are outside the scope of the book, but the results were resoundingly in favor of the quantum mechanical prediction. The Bell inequality 2.225 is not obeyed by nature. What does this mean? It means that one or more of the assumptions that went into the derivation of the Bell inequality must be incorrect. Vast tomes have been written analyzing the various forms in which the type of arrangement can be made, and analyzing the subtly different assumptions which must be made to reach Bell-like inequalities. Here we merely summarize to the main point. There are two assumptions made in the proof of 2.225 which are questionable. 1. The assumption that the physical properties PQ, PR, PS, PT have definite values Q or ST, which exist independent of observation. This is sometimes known as the assumption of realism. The assumption that Alice, performing her measurement, does not influence the result of Bob's measurement. This is something known as the assumption of locality. The two assumptions together are known as the assumptions of local realism. They are certainly intuitively plausible assumptions, but how about how the world works, and they fit in our everyday-to-day experience. Yet the Bell inequality show that at least two of the assumptions is not correct. At least one of these assumptions is not correct. What can we learn from Bell inequality? For physicists, the most important lesson is that their deeply held common sense institutions about how the world works are wrong. Intuitions. The world is not locally realistic. Most physics takes the point of view that is the assumption of realism, which needs to be dropped from our worldview in quantum mechanics, although others have argued that the assumption of locality should be dropped instead. Regardless, Bell inequality, together with the substantial experimental evidence, now points to the conclusion that either both of locality and realism must be dropped from our view of the world if we are to develop a good intuitive understanding of quantum mechanics. What lessons can the field of quantum computation and quantum information learn from Bell's equality? Historically, the most useful lesson has perhaps also been the most vague. There is something profoundly up with entangled states like EPR state. A lot of mileage in quantum computation, and especially quantum information, has come from asking the simple question, what would some entanglement by me in this problem. As we saw in teleportation and superdense coding, as we saw in teleportation and superdense coding, and as we will see repeatedly later in this book, by throwing some entanglement into the problem, we open up a new world of possibilities unimaginable with classical information. The bigger picture is that Bell's inequality teaches us that entanglement is a fundamental new resource in the world that goes essentially beyond classical resources, into the classical world's Bronze Age. A major task of quantum computation and quantum information is to exploit this new resource to do information processing tasks impossible or much more difficult with classical resources. Chapter 3 End. Chapter 2 End.